In this first lesson, we will look at the primary requirements of all aeroplanes and introduce the four forces acting on an aeroplane in flight. From some of the very first aeroplanes to today, the primary requirements of an aeroplane have remained the same. These are a force, lift, which enables the aeroplane to fly in the air, a safe and protective space in which to carry the payload and crew, stability, enabling the aeroplane to naturally continue in the same direction, control, to change the aeroplane's direction and position in the air, and a force, thrust, which can propel the aeroplane forwards for the required length of time. These are therefore the 5 primary requirements that must be met by all powered aeroplanes. To meet these basic requirements, all powered aeroplanes have the same primary components. These components are the wings, which generate lift, enabling the aeroplane to fly and remain in the air, the fuselage, which safely carries the payload and crew, tail surfaces, which are designed to give the aeroplane stability, ensuring that the aeroplane naturally flies in a constant direction, control surfaces, to change the direction of the aeroplane's flight and, when required, its position in the air, and engines to produce thrust, propelling the aeroplane forwards for the required duration of the flight. The 5 primary requirements of an aeroplane are therefore met by these 5 primary components: the wings, fuselage, tail surfaces, control surfaces, and engines. Although all powered aeroplanes have the same primary components for flight, we notice that the actual design of these components is quite different. Looking at one component, the wings, they may be mounted at the top of the fuselage or close to the middle or towards the bottom of the fuselage. The wings may be straight and perpendicular to the fuselage or be swept backwards, be angled upwards towards the wingtips, which is called dihedral, downwards towards the wingtip, which is called anhedral, or be straight with no slope. Each aeroplane type has a combination of the wing designs outlined above. The actual wing design depends on the aeroplane's role rather than artistic style. A design feature that enables an aeroplane to fly faster will also have disadvantages. Similarly, a wing design that enables a heavily laden aeroplane to take off and land from a relatively short runway will have different disadvantages. Ultimately, every wing design is a compromise. Similarly, the design of the other aeroplane components is also a compromise. Notice how the fuselage, tail surfaces, controls and engine type and placement differs between the aeroplanes shown on the screen. These 3 aeroplanes, the now retired Concorde, the A340 and the PA-28, all have very different designs. Let us now consider how the design of the primary aeroplane components varies between these aeroplanes. Notice the different design of the wings, their shape and position, the fuselage shape and cross-section to length, the size, shape and presence of tail surfaces, the variation in size and location of control surfaces, and the location and number of engines. Study and consider the very different component designs of these 3 aeroplanes. Each design has advantages and disadvantages, and the final design is a role-centered compromise. Look for and consider these differences before moving on. At the beginning of this lesson, you were introduced to lift and thrust as 2 of the primary requirements for a powered aeroplane, the others being stability, control, and space for the payload and crew. We will now look at the 4 forces acting on an aeroplane whilst flying and their fundamental relationship. Whether on the ground or in the air, an aeroplane has mass, which due to the acceleration due to gravity results in a force, weight, which always acts or pulls the aeroplane vertically straight down, and weight increases as the mass of the aeroplane increases. When the aeroplane is on the ground, the surface provides a reaction, which equals the aeroplane's weight. The aeroplane is supported by and does not sink into the paved surface. However, when the aeroplane is in the air, the reaction from the ground is no longer present, and to prevent the aeroplane being pulled vertically down towards the Earth's surface, a force, lift, must be produced. This lift force must equal the force of weight if the aeroplane is to fly level. And the heavier the aeroplane, the greater the size of the required lift force. However, whenever there is relative motion and/or lift is produced, there will always be a force, drag, pulling backwards on the aeroplane. And the greater the lift, the greater the drag. In level flight, this drag force would slow the aeroplane down. If the aeroplane is to remain at the same speed in level flight, the drag must be balanced by a force, thrust, pulling the aeroplane forwards. We can now see that all four forces are related, and if an aeroplane is to fly level at a constant speed, a heavier aeroplane will require more lift, produce more drag, and therefore require more thrust. Similarly, a lighter aeroplane will have smaller lift, drag and thrust forces to maintain the same speed in level flight. To summarize, all powered aeroplanes have the same requirements, which are provided by the same aeroplane primary components. But the design of these components varies between aeroplane types. It is the role, and therefore the requirements of the aeroplane, that determine the design of these components, and that design will always be a compromise. Finally, we introduced the four forces acting on an aeroplane in flight, and saw that these forces are related. The forces lift, drag and thrust will be greater for a heavier aeroplane and less for a lighter aeroplane. During this lesson, we introduce you to some of the units, definitions and calculations used in principles of flight. Good understanding is essential before progressing through the course, so replay scenes that cover material you are less familiar with and make summary notes. Mass is the quantity of matter in a body. In aviation, the term body could mean a volume of liquid, such as fuel, or gas, such as air, or a solid object, such as an aeroplane. In standard international SI units, mass is measured in kilograms, designated by the letters kg. All bodies on or close to the Earth are affected by the Earth's gravitational field. All objects with mass, be they aeroplanes or air molecules, are attracted towards the Earth. The Earth's gravity vector points towards the centre of the Earth, which is locally straight down. Although gravity reduces very slightly as altitude increases, for practical purposes this is ignored. The gravity constant is 9.81 meters per second squared. The examining body uses a gravity constant of 10 meters per second squared, and this will be stated in the question. Weight is the force that a mass exerts when it is in the gravitational field. Weight acts parallel to the gravity vector and is locally taken to act straight down. The SI unit for weight is the Newton, designated by the symbol N. Weight can be calculated by multiplying the body's mass by the acceleration due to gravity, which is 10 meters per second squared. This means that a mass of 1 kilogram has a weight of 10 newtons on Earth, and a 60,000 kilogram aeroplane has a weight of over 500,000 newtons. The force of weight is taken to act from a single point within the body, which is called the centre of gravity. An aircraft's weight acts from its centre of gravity. For an aeroplane to maintain stable flight and have sufficient control, the aeroplane's centre of gravity must be within a safe narrow range. In flight, an aeroplane rotates about its centre of gravity. This means that the aeroplane always rolls around its centre of gravity. When the aeroplane's nose moves up or down, it is pitching around the centre of gravity. and when the aeroplane's nose moves left or right, it is yawing around the centre of gravity. We will now look at the unit of distance used in principles of flight. The SI unit for distance is the metre, designated by the letter M. But aviation mixes the metric units with the older imperial units of the foot, statute mile, and the nautical mile. You must memorize that there are 6,080 feet in 1 nautical mile, 5,280 feet in 1 statute mile, and 3.28 feet in 1 metre, together with the other probably more familiar conversions shown. Due to the constant mix between SI and other distance units, a pilot must have the ability to convert between these units quickly and accurately. Look at and check your workings. If unsure, repeat this section before continuing. Having conquered the various units of distance, we can now look at speed. Speed is the rate of covering distance, so speed is distance divided by time. Some of you may already be familiar with the distance-speed-time triangle. Taking the horizontal line as a divide, it reminds you that speed is distance divided by time. The SI unit of speed is meters per second, which is used in aviation in some countries. In the UK and many other countries, horizontal speed is measured in knots, which is nautical miles per hour, and vertical speed in feet per minute. In aviation, it is important to be able to convert between these speeds roughly in your head. 2 knots is roughly 1 metre per second. This means, to find the approximate speed in meters per second, you halve the number in knots. For example, an aeroplane flying at 300 knots true airspeed is therefore flying at approximately 150 meters per second. Conversely, 1 meter per second is roughly 2 knots. So, if you were given a wind speed in meters per second, you would double it to get an approximate wind speed in knots. So, for example, a wind of 10 meters per second is approximately 20 knots. A force is a push or a pull in a defined direction, and is measured in newtons. In the first lesson, we introduced the forces acting on an aeroplane, which were lift, weight, drag, and thrust. A force can cause a mass to accelerate, and these 3 terms are related by the equation F equals ma. A force is said to do work when it moves an object a distance. The amount of work done depends on the size of the applied force and the distance it moves the object. The unit of work is the joule. Work is found by multiplying the size of the force by the distance the force moves the object. However, no work is done when a force does not move an object. Prior to the takeoff run, when the engines are spooling up and the aeroplane is held on the brakes, there is considerable thrust, but because the aeroplane is stationary, there is no work done. Power is the rate of doing work, and is therefore expressed in an equation as power equals work divided by time. The unit of power is the watt, which is designated by the letter W. Returning to our previous example of an aeroplane on a runway with 150,000 newtons of thrust, calculate the power to cover 50 meters in 5 seconds. Power is found by dividing the work done by the time it was achieved in. Because power is the rate of doing work, if no distance is covered, there is no power. The last part of this lesson looks at energy and Newton's laws of motion. We will first look at energy, which is measured in joules. There are many forms of energy, but it is kinetic energy that we will look at in more depth for principles of flight. Kinetic energy is the energy a body has because of its motion, and depends on the mass of the body and the square of its speed. air density at mean sea level on an average day is 1.225 kilograms per cubic meter. Although we rarely think about it in our day-to-day lives, a cubic meter of air is therefore approximately 1.225 kilograms. This means that when air moves, or there is relative motion between it and an aeroplane, it has considerable kinetic energy. The kinetic energy is found by squaring the air's speed in meters per second by the mass of the cube of air, and then halving it. Therefore, a cube of air travelling at 30 knots, which is 15.45 meters per second, has 146 joules of energy. Now let's consider the relative motion between still air and a flying aeroplane. Relative to an aeroplane flying at 100 knots, which is 51.5 meters per second, a cubic meter of air has 1,625 joules of kinetic energy. However, because kinetic energy varies with speed squared, at 200 knots, which is 103 meters per second, the same cubic meter of air would have 6,498 joules of kinetic energy. Notice that when the speed doubles, there is 4 times the kinetic energy. We will now look at Newton's laws of motion and give examples of why they are relevant to principles of flight. The first law is that a body will remain at rest or in uniform motion in a straight line, unless acted on by an external force. It is highly relevant when looking at an aeroplane in steady straight flight, because to fly in a straight line at the same speed, the opposing forces must be equal. Newton's first law helps us to recognize that an aeroplane has inertia. When stationary, it resists moving, and once moving, resists stopping, moving faster, or changing direction. The magnitude of this inertia depends on the body's mass, with a heavier object having more inertia. A heavier body is therefore harder to start or stop moving. Newton's second law shows that when a force is applied to a body, its acceleration is proportional to the size of the force and inversely proportional to the object's mass, because a heavier object has more inertia. Newton's second law has obvious implications on takeoff, as the aeroplane must accelerate to reach its takeoff speed, and will do so quicker if the engine thrust is greater, or if the aeroplane has less inertia because it is lighter. Newton's third law of motion states that every action has an equal and opposite reaction. It is the reason why a rocket or jet engine, which forces air backwards, gives the rocket or aeroplane a thrust force forwards. Look again at the distance and speed conversions. There are 5,280 feet in a statute mile and 6,080 feet in 1 nautical mile. As an approximation, halve the knots to find meters per second. You were then introduced to Newton's 3 laws of motion. By the end of this lesson, you should be able to understand the characteristics of the atmosphere and how they change with altitude. You will also learn about static and dynamic pressure, temperature, density, and the International Standard Atmosphere, commonly referred to as ISA. The lesson concludes with explanations of airspeed and its various categories. The atmosphere is the medium in which aircraft operate. It is the properties of the atmosphere, that is, the mixture of gases which comprise air, that generate the required lift force when it is acted on by the shape of a wing. The most important property of air is its density. If air density decreases, the mass of air flowing over an aircraft in a given time will decrease. The concept of mass flow is a useful one to keep in the back of your mind when considering principles of flight, as thinking of airflow in terms of kilograms per second can help with understanding. Thus, if a given mass flow is generating the required lift, then a drop in density will reduce the mass flow and the lift. To maintain the required lift if density is decreased, the speed of the aircraft through the air must be increased, and the increased speed of the airflow over the wings can restore the mass flow in the lift to its previous value. We have already talked about mass flow of air. Air may not have a great deal of mass compared to, say, metal, or even a human body, but it is significant. A mass of moving air has considerable kinetic energy. Think of the damage done by hurricane force winds or tornadoes. Air is also a compressible fluid, and is able to flow or change its shape when subjected to even small pressure changes. Being fluid, air will always flow from high to low pressure. Like a tube of toothpaste, even with the cap on, squeeze the middle and the toothpaste moves to the ends where you're not squeezing it. Another example is air being released from a toy balloon. Unlike toothpaste, though, the viscosity of air is very low, and even small forces are easily able to move the molecules relative to each other. The part of the atmosphere in which most aircraft fly, that is up to about 40,000 feet, undergoes gradual changes in its characteristics with height. Since air is compressible, the lower layers contain by far the greater part of the atmosphere's mass. Atmospheric pressure, referred to as static or ambient pressure, decreases steadily with increasing altitude, but temperature falls progressively only to about 36,000 feet, above which it remains more or less constant throughout the stratosphere. Static pressure is the pressure exerted by the air of the atmosphere on any object anywhere in the atmosphere, and can act in any direction. Static pressure is measured in newtons per square metre, and for these lessons is given the symbol lowercase p. Key points about static pressure are that static pressure is the result of the weight of the atmosphere pressing down on the air beneath. Static pressure will exert the same force per square metre on all surfaces of an aeroplane. The lower the altitude, the greater the force per square metre. It is called static pressure because of the air's stationary or static presence. An aircraft always has static pressure acting on it. Newtons per square metre is the SI, for Système International, unit of pressure. 1 Newton per square metre is called a Pascal, but since this is rather a small unit, the hectopascal is used in aviation and meteorology. Hecto is from the Greek for 100, and 1 hectopascal equals 1 millibar. Static pressure at any particular altitude will vary from day to day, and averages about 1,000 hectopascals at sea level. In some countries, notably the USA and Canada, pressure and altimeter settings are given in inches of mercury, and the equivalent sea level pressure is 30 inches. The unit for temperature is the degree Celsius, if measured relative to the freezing point of water, or temperature Kelvin, if measured relative to absolute zero, which equates to minus 273 degrees Celsius. 0 degrees Celsius, or centigrade, is thus equivalent to 273 Kelvin. On some older aircraft, some instrumentation may be calibrated in degrees Fahrenheit, a scale in which freezing point is 32 degrees and boiling point 212 degrees. The unit of density is kilograms per cubic metre, and the symbol used for density is the Greek letter rho. Density can be defined as mass per unit volume, or you could think of it as the number of air particles in a given space. Density varies with static pressure, temperature, and humidity. Density decreases if static pressure decreases, if temperature increases, and if humidity increases. This last factor will be considered later. The first two factors can be otherwise expressed in accordance with the ideal gas law, that density is proportional to pressure and inversely proportional to temperature. The formula states that pressure over temperature times density is a constant, or, to rearrange it, density is proportional to pressure over temperature. Density decreases with increasing height because of diminishing static pressure. The drop in temperature with height will tend to increase density, but the pressure-related decrease is dominant. The values of temperature, pressure and density are never constant in any given layer of the atmosphere. So, to enable accurate comparison of aircraft performance and the calibration of pressure instruments, a standard set of values has been adopted. This standard atmosphere represents mean or average properties and is defined by the International Civil Aviation Organization, ICAO. The International Standard Atmosphere, or ISA, assumes the following mean sea level values: temperature 15 degrees Celsius, pressure 1013.25 hectopascals, commonly referred to as 1013, density 1.225 kilos per cubic meter, and a uniform temperature lapse rate of 1.98 degrees C per 1,000 feet, up to 11,000 meters, or 36,090 feet, with a constant temperature of -56.5 above that level. A tabulated version of ISA is shown on the screen. As we have established, air has mass, and since it has mass, it will possess kinetic energy when in motion. Air in motion will exert a force per square meter on any object in its path. The formula for kinetic energy is half the mass times the square of the speed. This force per unit area is called dynamic pressure, because the air is moving in relation to the object being considered, in this case an aircraft. The dynamic pressure is proportional to the density of the air and the square of the speed of the air flowing over the aircraft, and is denoted by the symbol Q, in either upper or lower case. An aircraft in a moving airflow will therefore experience both static and dynamic pressure, as static pressure is always present. Let us consider the kinetic energy of 1 cubic meter of air moving at a stated speed. It is the product of the local air density, ρ, and the square of the speed in meters per second, divided by 2. If this cubic meter of air is completely trapped and brought to rest by an open-ended tube, the total energy will remain constant, but by virtue of being brought completely to rest, the kinetic energy is converted to pressure energy. This pressure energy is, for practical purposes, equal to half the density times the square of the speed, usually referred to as half rho v squared newtons per square meter. Let us consider an airflow of 100 knots, which is 52 meters per second, at ISA density of 1.225 kilos per cubic meter. Dynamic pressure is half rho v squared. That is 0.5 times 1.225 times 52 times 52, which equals 1,656 newtons per square meter, or 16.56 hectopascals. If the speed is doubled, dynamic pressure will be 4 times greater, as the factor in the equation is speed squared. Half times 1.225 times 104 times 104 equals 6,625 newtons per square meter, or 66.25 hectopascals. In a tube of an area of 1 square meter, a force of half rho v squared newtons will be generated. Regardless of the actual numbers involved in this example, it is important to remember the proportions. If speed is doubled, the pressure is quadrupled. If speed is trebled, the pressure increases by 9 times, and so on. If speed is halved, pressure reduces to a quarter of its previous value. Dynamic pressure is common to all aerodynamic forces and determines the air loads imposed on an aeroplane moving through the air. It is well worth remembering a few key facts about dynamic pressure. A pilot needs to know how much dynamic pressure is being generated, but it cannot be measured on its own, as static pressure is always present. In this context, the sum of the two pressures is known as total pressure. Other terms for total pressure are stagnation, or more usually, pitot pressure. The equation total pressure equals static pressure plus dynamic pressure can be rearranged to show that dynamic pressure equals total pressure minus static pressure. The significance of dynamic pressure in understanding the principles of flight cannot be overemphasized. Because dynamic pressure is dependent on air density and aircraft speed, you need to appreciate fully the factors which affect air density. So, to reiterate the points covered earlier in the lesson, increasing temperature decreases air density. Decreasing static pressure decreases air density. Increasing humidity decreases air density. The reason for this is that water vapor is about 5/8 the density of dry air. Humidity is most significant for takeoff and landing performance, but is actually not factored when considering aircraft performance. Increasing altitude will decrease density, because the effect of decreasing pressure is more dominant than that of decreasing temperature. All aerodynamic forces acting on an aircraft are determined by dynamic pressure, so it is essential to have a way of measuring it and presenting the information to the pilot in the required manner. A sealed tube, open at the forward end, is located to face into the airflow created when the aircraft is moving. The pressure in the tube, which is known as the pitot tube after its inventor, 18th century French hydraulic engineer Henri Pitot, is dynamic plus static, and in this context is called pitot pressure. A way of subtracting the static pressure from the total has to be found, and this is achieved by way of one or more vents located on a surface parallel to the airflow, usually on the fuselage, which will sense static pressure. If you look at the diagram on the screen, you will see that pressure from the pitot tube is fed to one side of a diaphragm inside a sealed case, and static pressure to the other. The two static pressures, essentially the same pressure, cancel each other out, and the diaphragm will sense only dynamic pressure. Movement of the diaphragm moves a pointer over a scale, so that the changes in dynamic pressure caused by changes in airspeed can be observed by the flight crew. But the instrument is calibrated to ISA sea level density, so will only give a true indication of airspeed when the density is 1.225 kilos per cubic meter. At any constant density, the faster the aircraft moves through the air, the greater will be the dynamic pressure. This isn't a problem, since the pilot needs an indication of dynamic pressure, which is what the instrument, the airspeed indicator or ASI, provides, being made in such a way that it indicates the square root of the dynamic pressure in nautical miles per hour, known as knots, or in some old aircraft, in statute miles per hour. So if this indicated airspeed is doubled, the speed of the aircraft through the air will also have doubled. There are, perhaps rather confusingly until you are familiar with them, several different categories of airspeed. The simplest is the indicated airspeed, IAS, which, as its name implies, is the airspeed shown on the ASI. Calibrated airspeed is an accurate measurement of the dynamic pressure of significance when the aircraft is flying slowly. The position of the pitot tube and static vents, and the aircraft's undercarriage and flap position, or configuration and attitude, will all affect the pressures that are sensed, particularly those at the static vents. Under these conditions, a false dynamic pressure will be sensed, resulting in a false IAS display. When IAS is corrected for this error, which is known as position or pressure error, the resultant speed is calibrated airspeed, CAS. The error may be placarded in the cockpit or in the flight manual, and will include known instrument error. Equivalent airspeed, or EAS, is the corrected airspeed achieved by allowing for the compressibility of air at high speed, usually only significant above 300 knots. Air is compressed in the pitot tube, giving a false, higher IAS. At a given density, the amount of compression depends on the speed of the aircraft. EAS allows for both position and compressibility errors. True airspeed is the actual speed of the aircraft through the air, and is the only real speed of those considered so far, all the others being dynamic pressures. The ASI is merely a pressure gauge calibrated to read as speed. TAS is EAS divided by the square root of the relative density. That is the ambient density as a proportion of the ISA sea level density. The ASI is calibrated to ISA sea level, so it will only read TAS if the density is 1.225. Thus, at 40,000 feet, where the density is close to 1/4 of the sea level value, the aircraft will be moving through the air twice as fast as at sea level to maintain the same EAS. The speed of sound, which is symbolized by a lowercase a, varies with temperature. Sound waves are weak pressure waves, which propagate from their source spherically through the atmosphere. The speed at which these sound waves travel is proportional to the square root of the absolute temperature of the air. The lower the temperature, the lower the speed of sound. On a standard day at sea level, the speed of sound is about 660 knots, or 340 meters per second. At high true airspeeds and/or high altitudes, it is essential for the pilot to know his speed relative to the local speed of sound. This relationship is called the Mach number, symbolized by a capital M. The formula for Mach number is TAS divided by A, the local speed of sound. For example, if the aircraft's TAS is 4/10 of the speed at which sound pressure waves propagate through the air around the aircraft, the Mach meter will register Mach 0.4. How the Mach meter works is covered in the instruments syllabus. If an aircraft's speed approaches the speed of sound, there will be a Mach number at which the speed of the airflow over some parts of the airframe, usually the point of maximum thickness of the aerofoil, first reaches the speed of sound. This Mach number is called the critical Mach number, or M-crit. Certain operating or limiting speeds that are significant in the operation of an aeroplane are given abbreviations for easy reference, known collectively as V-speeds. There are many of them, covering the entire flight envelope. For example, VS, stalling speed, VR, rotate speed, and VY, best rate of climb speed. All the above-mentioned speeds are calibrated airspeeds, as they relate to operations at low speed. Maximum operating, VMO, is an equivalent airspeed because it is a high speed. However, all the speeds quoted in the flight manual are adjusted to indicated airspeeds, since this is what the pilot will see on his ASI, which may have coloured arcs around the outer edge to indicate some of the main limit speeds. The atmosphere is the element in which aircraft operate, and it is important that you understand how the properties of the air, pressure, temperature and density change throughout the part of the atmosphere in which you fly. It is particularly important that you understand the concept of dynamic pressure and how it is involved in many of the aspects of the principles of flight. The next lesson deals with basic aerodynamic theory, in which you will see the application of some of the facts you have just learned. This lesson will examine the basic laws and principles of physics which govern aerodynamics. One of these fundamental laws is that energy and mass can be neither created nor destroyed, but only changed from one form to another. This is the basis of the principle of continuity, and to demonstrate its effect on aerodynamic theory, we will consider a stream of air flowing through a tube which has a reduced cross-sectional area in the middle. The air's mass flow, or mass per unit time, will be the product of the cross-sectional area of the tube, A, the velocity, v, and the air density, ρ. The mass flow will remain constant at all points along the tube. The equation of continuity is A times v times ρ equals constant. Because air is a compressible fluid, any pressure change in the flow will affect the air density. However, at low subsonic speeds, less than Mach 0.4, density changes are insignificant and can be disregarded. The equation of continuity can now be simplified to A times v equals constant, or, when we rearrange it, velocity equals constant divided by area. Because the mass flow must remain constant, it can be seen from the equation of continuity that the reduction in the tube's cross-sectional area results in an increase in velocity, and vice versa. The equation of continuity enables the velocity changes of airflow around a given shape to be predicted mathematically for speeds below Mach 0.4, which is around 260 knots at sea level. Associated with the principle of continuity is Bernoulli's theorem, propounded by 18th century Dutch-Swiss mathematician Daniel Bernoulli. His theorem states that, in the steady flow of an ideal fluid, the sum of the pressure and kinetic energy per unit volume remains constant, or, more concisely, the sum of the energies present remains constant. In this context, an ideal fluid is both incompressible and has no viscosity. The theorem can be expressed as pressure plus kinetic energy equals constant, or P plus half rho v squared equals K. Let us consider a mass of air at ISA conditions, moving at 100 knots or 52 meters per second. Static pressure is 101,325 newtons per square meter, density 1.225, giving a dynamic pressure of 1656 newtons per square meter. Pressure energy 101,325 plus kinetic energy 1656 equals a constant 102981 newtons per square meter. Because the velocity of the airflow at the throat has doubled, its dynamic pressure has risen by a factor of 4, and the static pressure has decreased. But the total pressure, the sum of static and dynamic, has remained constant. This constant can be referred to as total pressure, stagnation pressure, or pitot pressure, according to context. The tubes used in the diagrams just shown are used only to demonstrate the principle of continuity and Bernoulli's theorem, and are not devices which could make an aeroplane fly. However, an aerodynamic force to oppose and exceed the weight of an aircraft can be generated by a specially shaped body called an aerofoil. The airflow over the top surface of a lifting aerofoil will be at a greater velocity than that beneath, so that the pressure differential will result in a net upwards force per unit area. The bigger the surface area, the larger the force generated. Next, we shall see the similarity between the flow over the aerofoil and the flow through the tube used in describing the principle of continuity and Bernoulli's theorem, and that these fundamentals still apply to aerofoils. A streamline is the path followed by a particle of air in a steady airflow, and one streamline cannot cross another. When they are shown close together, it indicates increased velocity, and when wide apart, decreased velocity. When streamlines diverge, it indicates decelerating airflow and the associated rise in pressure. And converging lines, acceleration with decreasing pressure. A stream tube is an imaginary tube made up of streamlines. There is no flow into or out of the stream tube through the imaginary walls, only a flow along the tube. This concept will help you to visualize the airflow around an aerofoil. To grasp the basic principles of aerodynamics, you will need to understand the principle of continuity and Bernoulli's theorem. We can summarize the relevant elements as follows. By the principle of continuity, air accelerates when the cross-sectional area of a streamline flow is reduced, and decelerates when it increases. By Bernoulli's theorem, if a streamline flow of air accelerates, its kinetic energy will increase and its static pressure will decrease. Conversely, if air decelerates, the kinetic energy will decrease and the static pressure will increase. Additionally, it should be remembered that these pressure changes will not affect air density at speeds below Mach 0.4. By using these effects, an aerofoil can generate the aerodynamic forces required for flight. Following on from basic aerodynamic theory, this lesson on subsonic airflow will cover the principal definitions and terminology concerning aerofoils and the airflow around them, and how changes in airflow affect the resultant forces. The aerofoil can be defined as a shape capable of producing lift with relatively high efficiency. As air flows over an aerofoil at a sufficient speed, it will have certain effects on the static pressure surrounding the aerofoil, as propounded by the principle of continuity and Bernoulli's theorem in the last lesson. Even before the airflow reaches the aerofoil, the pressure drop over the upper surface will cause the flow to rise towards it. This is known as upwash. At a point on the lower side of the leading edge, the airflow will be brought to a halt at a point called the stagnation point, where the airflow separates to pass over or under the wing. As the air flows back over the aerofoil, it will tend to slow down in accordance with the basic principles, flowing against the adverse pressure gradient as the higher pressure air below the aerofoil tries to go from high to low pressure, that is, forward from the trailing edge to the low pressure area on top. The pressure distribution is shown here, with the highest pressure concentrated around the stagnation point and the low pressure extending up and forward to a peak above the aerofoil, with the pressure differential creating the lift force indicated. Also shown is the force, drag, which acts against the forward movement of a wing and is caused partly by the lift itself. Lift and drag are fully covered in subsequent lessons in the syllabus. Having introduced the basic characteristics of the airflow around an aerofoil, we shall now look at the terminology and definitions associated with aerofoils. The chord line is a straight line joining the centers of curvature of the leading and trailing edges of an aerofoil. The chord is the distance between the leading and trailing edges, measured along the chord line. The angle of incidence is the angle between the wing root chord line and the longitudinal axis of the aircraft. This is fixed for the wing, but may be variable for the tailplane. The mean camber line, also known as the mean line or camber line, is a line joining the leading and trailing edges equidistant from the upper and lower surfaces. Maximum camber is the greatest distance of the mean camber line from the chord line, and is expressed as a percentage of the chord, and its location along the chord line as a percentage of the chord measured from the leading edge. When the camber line is above the chord line, the aerofoil is said to have positive camber, and when it is below, negative camber. A symmetrical aerofoil has no camber, as chord and camber lines are coincident. Thickness-chord ratio is the maximum thickness or depth of an aerofoil section, expressed as a percentage of the chord from the leading edge. The thickness and thickness distribution of an aerofoil section have a significant effect on its airflow characteristics. Leading edge radius is the radius of the curvature of the leading edge, which can significantly affect the initial airflow characteristics of the aerofoil. Basically, the smaller the radius, the sharper the leading edge. Relative airflow, or relative wind, or free stream flow, is the direction of the airflow produced by the movement of the aircraft through the air, and has three characteristics. First, its direction is opposite and parallel to the flight path, which is the direction taken by the centre of gravity. The aircraft's attitude is not a factor. Secondly, its condition is that it is air close to but unaffected by the presence of the aircraft. That is, its temperature, pressure and velocity are not changed by the aircraft's passage through it. Thirdly, the relative airflow's magnitude is the speed of the aircraft through the air, the true airspeed. If the airflow does not possess all of these three characteristics, it is referred to as effective airflow. Total reaction is the resultant of all the forces acting on the aerofoil section, namely lift and drag. The centre of pressure, or CP, is the point on the chord line through which lift is considered to act. Lift is the aerodynamic force generated by the aerofoil, which acts at 90 degrees to the relative airflow. Drag is the aerodynamic force which acts parallel to and in the same direction as the relative airflow, that is, opposite to the flight path. Angle of attack is the angle between the chord line and the relative airflow. It is often referred to as alpha, written as the Greek letter. An alternative but less used term is aerodynamic incidence. The angle of attack between the chord line and the effective airflow is referred to as the effective angle of attack. When we are considering airflow velocity, it makes no difference to the pressure pattern created by the flow over an aerofoil if the aircraft is moving through the air or the air is moving over the aircraft. It is the relative velocity which is the most important factor. For example, an aircraft flying level at 80 knots will produce about the same lift as it would stationary on the ground, facing into an 80-knot wind, depending on angle of attack. To promote full understanding, we will be referring to both situations, either where air flows over a wind tunnel model, or aircraft in flight moving through stationary air. Three-dimensional airflow is the true airflow over an aircraft and consists of a two-dimensional flow, modified by various pressure differentials. This will be examined later in the syllabus. For now, we will consider two-dimensional airflow. Two-dimensional airflow assumes a wing with the same aerofoil section along its entire span, with no span-wise pressure differential or flow. This concept is used to illustrate the basic principles of the generation of aerodynamic force. As air flows towards an aerofoil, it will be turned upwards towards the lower pressure over the upper surface. This is termed upwash. After passing over the aerofoil, the flow returns to its original flow level and state. This is termed downwash. On the screen, you can see an aerofoil at a representative angle of attack, subject to a given dynamic pressure or IAS. The pressure distribution showing that if the static pressure on one side of a body is reduced more than on the other side, a pressure differential will exist. If the same angle of attack is maintained, and the IAS, and thus the dynamic pressure, is increased, the pressure differential will increase. The pressure differential acting on the surface area will produce an upward acting force. So, if dynamic pressure increases, the upwards force increases. At a constant dynamic pressure, increasing the angle of attack, or alpha, will also increase the pressure differential, but will also alter its distribution pattern. The aerofoil profile presented to the airflow will determine the distribution of velocity change, and hence the pressure pattern over the surface. This pattern is determined by the aerofoil's geometry, that is, the thickness and its distribution, which are fixed, the camber and its distribution, which are assumed to be fixed for now, and by the alpha, which is variable. The greatest positive pressure occurs at the stagnation point, where the relative flow velocity is 0. This point is somewhere near the leading edge. As the alpha increases from -4, it moves from the upper surface around the leading edge to the lower surface. The stagnation point is where the airflow divides over the upper and lower surfaces, and pressure here is static plus dynamic. The flow over the top accelerates rapidly around the leading edge and over the front portion of the wing, creating a substantial static pressure drop. The rate of acceleration increases with alpha, up to about 16 degrees. The pressure reduces continuously from stagnation value, through free stream pressure, to a position on the top surface where a peak value is reached. From there, the airflow decelerates progressively, and the pressure rises back to free stream near the trailing edge. It should be noted that any imperfections on the upper leading edge surface, such as dents, dirt and insects, ice or frost, etc., can seriously disrupt the flow acceleration in this critical area. At alphas less than 8 degrees, the underside flow is much less accelerated, and reduces pressure to only a small negative value. The pressure differential between the stagnation point and the lower pressure at the trailing edge creates a backwards acting force called form or pressure drag, which is covered later in the syllabus. We can now examine what happens to the pressure pattern as the angle of attack changes, starting with low angles. With an alpha of -4 degrees, the drop in pressure is the same above and below the section. There is no differential, and therefore no lift. This is known as the zero lift angle of attack. At 0 degrees alpha, there is a pressure decrease over the upper surface compared with free stream flow, with a smaller decrease on the underside. Even at small angles of attack, between -4 and 0, a positively cambered section will produce lift. The positive pressure at the leading edge is dynamic, or, in this context, stagnation pressure. As angle of attack is increased, here to around 4 degrees, the lift force is increased because of the greater acceleration of the upper surface flow in the reduced cross-sectional area of the local stream tube. The low pressure peak moves forward as the angle of attack increases. At 8 degrees, the peak is higher and further forward, and nearly all the lift is from the upper surface. But the increased frontal area means that stagnation pressure is adding to the rearward force. At about 14 degrees, the low pressure peak is well forward, and the high pressure area under the wing is greater, adding to both lift and drag. The contribution to the rearwards force is due to the pressure gradient, which is a change in pressure over distance. The greater the pressure difference, the steeper the gradient. As air tries to flow from high to low pressure, a favourable gradient is one in which the pressure is falling in the direction of the airflow. And an adverse gradient is one in which it is rising in the flow direction, such as between the point of minimum pressure over the aerofoil and the trailing edge. The gradient increases with angle of attack. As the angle of attack reaches about 16 degrees, the adverse pressure gradient is such that the air is trying to flow forward from the trailing edge against the airflow, preventing the previously smooth streamline flow from following the surface of the aerofoil, and causing the low pressure area over the upper surface to collapse suddenly. Any pressure differential remaining is due to the pressure increase on the underside only. This condition is known as the stall, described fully in a later lesson. The whole surface of the aerofoil contributes to lift, but the point along the chord where the lift is effectively concentrated is termed the centre of pressure. The location of the centre of pressure, or CP, is a function of camber and lift coefficient, which depends partly on angle of attack. As the alpha increases from 0 to 16 degrees, the upper peak of low pressure, or suction, will move forward, taking the point of concentration of lift, the CP, with it. The magnitude of the lift force also increases with alpha, until the stall is reached, at which point the lift force decreases abruptly, and the CP moves back along the chord. Note that the CP is at its most forward point, where lift is at its maximum, just before the stall. A coefficient is a number, without unit or dimension, expressing a degree of magnitude. An aerodynamic force coefficient is a common denominator for all aircraft, regardless of weight, size or speed, and is a ratio between the average aerodynamic pressure and the airstream dynamic pressure. By this definition, a lift coefficient, or CL, is the ratio between lift divided by wing planform area, or lift pressure, and dynamic pressure. A drag coefficient, CD, is the ratio between drag divided by wing area and dynamic pressure. As speed increases, assuming a constant density, CD will remain constant, since drag pressure and dynamic pressure are increasing in the same proportion. We need to use coefficients of aerodynamic force, as they provide an index of the force, independent of area, air density or velocity, being derived from the relative pressure and velocity distribution. They are influenced only by the shape of the surface and angle of attack, since it is principally these factors that determine the pressure distribution. The last section of this lesson covers aerodynamic pitching moments. To refresh your memory, a moment is defined as the product of a force and the distance through which it acts. In the case in which we are considering the moment, it is purely a leverage, and no movement is involved. The distribution of pressure over a surface is the source of aerodynamic moments as well as forces. There are two ways of considering the effects of a changing angle of attack on the pitching moment of an aerofoil. Either by measuring the changes in magnitude of lift through a moving centre of pressure, or, more simply, through a fixed aerodynamic centre. You know from the previous parts of this lesson that as the angle of attack increases, the CP moves forward and the magnitude of lift increases, and vice versa. This results in a changing force with a changing point of application. The aerodynamic centre, or AC, is a fixed point on the chord line, and can be defined as the point where all changes in the magnitude of lift effectively take place, and the point about which the pitching moment will remain constant at normal angles of attack. For subsonic airflows of less than Mach 0.4, the AC is located at the 25% chord point, regardless of camber, thickness or angle of attack. The AC is an aerodynamic reference point, which is used for examination of the theory of incompressible airflow, and is most directly applicable to longitudinal stability, as you will see later in the syllabus. There is a nose-down pitching moment about the AC, which is a product of the lift force at the CP and the arm between the CP and the AC. Since an increase in alpha will not only increase the lift force, but also shorten the lever arm as the CP moves forward towards the AC, the moment about the AC remains the same at any angle of attack within the normal flight range. With a symmetrical aerofoil at 0 alpha, the upper and lower forces are equal and symmetrically distributed. With an increasing angle of attack, the upper surface force increases and the lower force decreases. A change in the magnitude of the lift forces has taken place without a change in the position of the centre of pressure, which is a characteristic of symmetrical aerofoils. Thus, the pitching moment about the aerodynamic centre will be 0 at normal angles of attack, which is one of the big advantages of such aerofoils. To summarise the significant points of this lesson, we can start with the main things affecting airflow pattern, and consequently lift and drag. It will depend on angle of attack, airflow cross-sectional area change, aerofoil shape, that is, thickness and camber, again, airflow cross-section, air density, air mass flow decreasing with greater altitude, and velocity, air mass flow, changing with TAS. The lift force is the result of the pressure differential between the upper and lower surfaces of an aerofoil. The greatest contribution comes from the top surface. Any contamination, particularly ice, or deformation of the upper leading edge surface can seriously disrupt the airflow acceleration, and hence the magnitude of the lift force. An increase in dynamic pressure with indicated airspeed will increase the lift force, and vice versa. An increase in angle of attack, alpha, will increase the lift force, and vice versa, over the normal flight range of 0 to 16 degrees. The centre of pressure of a cambered aerofoil moves forward as alpha increases, whereas the CP of a symmetrical aerofoil does not, within the normal range. Throughout the normal alpha range, the aerofoil's pitch-down moment about the aerodynamic centre, or AC, will remain constant. The AC is at the quarter chord position for subsonic flow of less than Mach 0.4. The coefficient of lift is the ratio between lift per unit wing area and dynamic pressure. As alpha increases from -4 degrees, the leading edge stagnation point moves from the upper surface around the leading edge to the lower surface. The greatest positive pressure occurs at the leading edge stagnation point, where the relative flow velocity is 0. Form or pressure, drag, is the result of the pressure differential between the leading and trailing edges of the aerofoil. An increase in dynamic pressure, that is, indicated airspeed, will increase form drag, and vice versa. The coefficient of drag is the ratio between drag per unit wing area and dynamic pressure. You learned in the last lesson how the airflow over an aerofoil produces both lift and drag. In this and the following lessons, we shall examine in greater detail lift and the factors affecting it. The aerodynamic forces of both lift and drag depend on the combined effect of many variables, the most important being the airstream velocity v, which, when combined with the air density ρ, determines dynamic pressure, the formula for which is half ρv squared. This is the common denominator of aerodynamic forces, and is a major factor, since the magnitude of a pressure distribution depends on the energy given to the airflow. Kinetic energy equals half the mass times the velocity squared. The shape or profile of the aerofoil and the angle at which the airflow meets it, the angle of attack, together determine the pressure distribution around the aerofoil, and thus the coefficient of lift and drag. The surface area, S, and its condition will also have a direct effect on the amount of lift produced. The larger the surface area for a given pressure differential, the greater the force generated. Compressibility, which only starts to become significant above 300 knots, will be covered in later lessons. Any aerodynamic force can thus be represented as a product of the three major factors, which are the dynamic pressure of the airflow, half rho v squared, or Q, the coefficient of force determined by the relative pressure distribution, that is, the coefficient of lift, CL, or drag, CD, and the surface area of the object. The relationship of these three factors is expressed in the equation F equals Q times CF times S, where F is the aerodynamic force, either lift or drag, Q is the dynamic pressure, half rho v squared, CF is the coefficient of aerodynamic force, and S is the surface area. Lift is defined as the net force generated normal to, or at right angles to, the relative airflow or flight path of the aircraft. The aerodynamic force of lift is the result of the pressure differential between the upper and lower surfaces of the wing, and for an aircraft to fly straight and level, lift must be constant and balance weight exactly. Several factors will affect the amount of lift generated. First, air density, denoted by the symbol ρ. Next, the aircraft's true airspeed, or TAS, enters the equation as V. The next factor is the coefficient of lift. The final factor is the wing area. Dynamic pressure depends on air density and TAS, and is related to the kinetic energy of the airflow. So the formula is based on half the density and the square of the TAS. Remember that for straight and level flight, lift must remain constant. It is important to remember this formula. L equals half rho v squared times CL times S. During this examination of the lift formula, we are taking it for clarity that the CL is determined by angle of attack, which is true, but CL is also affected by changes in wing shape or profile and some other factors, which are explained in a later lesson. There is a direct relationship between density and the TAS that an aircraft will achieve for a given IAS, usually in connection with a change in altitude, since density decreases as altitude increases. Considering the ICAO standard atmosphere, or ISA, in which the density at 40,000 feet is a quarter of that at mean sea level, we can see the changes in relationship that occur between TAS and IAS because of density change. To maintain constant lift as density decreases, any of the elements of the equation could be changed. But it is impractical to change wing area, and inefficient to change CL from the best lift-drag ratio at 4 degrees angle of attack. So since the dynamic pressure must be maintained, if one element drops, the density, the other, the TAS, must rise, in this case to twice the sea level value. Because of the square function of the TAS, doubling it would increase dynamic pressure by 4, compensating for the 4-fold drop in density. So, since IAS is proportional to the square root of the dynamic pressure, maintaining a constant IAS will maintain constant lift. The lift formula can also be used to look at the relationship between speed and angle of attack at a constant altitude. As before, if one element of the equation is increased, another must be reduced. As speed rises, the CL must be reduced to maintain the same total lift, normally by reducing the angle of attack. If indicated airspeed is doubled, here from 150 knots to 300, the TAS also doubles, increasing dynamic pressure by 4. If dynamic pressure is increasing by a factor of 4, then to maintain lift at a constant, the CL must be reduced by the same factor. In other words, to a quarter of its previous value. By reducing the angle of attack appropriately to keep the aircraft at a constant height. To make this principle easy to understand, we can say that TAS will change in proportion to IAS at a constant altitude. This is, however, not true of speeds above Mach 0.4. The lift formula can be transposed in several ways to calculate variables which may be of interest to a professional aviator. For example, if speed is increased in level flight by 30% from the minimum level flight speed, we can calculate the new CL as a percentage of CL max. L equals half rho V squared times CL times S, when transposed, becomes CL equals L over half rho V squared S. Since density, lift and wing area are constant, this can be written as CL is proportional to 1 over V squared. 30% above can be written as 1.3, so 1 over V squared becomes 1 over 1.3 squared. This equals 1 over 1.69, which is 0.59 or 59%. So, while flying at 30% above minimum level flight speed Vs, the CL will be 59% of CL max. To review what has been covered so far on the subject of lift. Lift must balance weight in straight and level flight. So at any given time, both weight and lift required are constant. To maintain constant lift, if density varies with altitude, a constant IAS must be maintained. With a constant IAS, if altitude increases, density decreases and TAS increases, and vice versa. To maintain constant lift, if speed is changed at constant altitude or density, the angle of attack, or alpha, must be adjusted. If speed is increased, alpha must be decreased. If speed is doubled, alpha must decrease to make CL 1/4 of its previous value. If speed is decreased, alpha must be increased. If speed is halved, alpha must increase to make CL 4 times its previous value. Generally, a cruise speed is derived so that an aircraft operates at its optimum angle of attack, with maximum lift-drag ratio, typically around 4 degrees.
It is important to understand the relationship between the velocity used in the aerodynamic force equations and dynamic pressure. The velocity being the speed of the aircraft relative to the air through which it is moving, the true airspeed, or TAS. At a given angle of attack, a constant dynamic pressure must be maintained to maintain a constant lift force. When an aircraft is flying at an altitude where the air density is other than sea level density, the TAS must vary in proportion to the air density change. With increasing altitude and decreasing density, the TAS will increase if the indicated airspeed, IAS, and thus dynamic pressure are maintained. Air density at the time of takeoff and landing can significantly affect aircraft. For example, if air density is low, a longer takeoff run will be needed. Air density is a product of pressure, temperature, and humidity. Humidity actually reduces density because the density of water vapour is about 5/8 of that of dry air. Low pressures and high temperatures also reduce density. On an airfield at sea level with standard pressure, if 1013, 1013 millibars or hectopascals is set on the altimeter, it will read 0. This is known as pressure altitude, which is what will be indicated whenever 1013 is set, regardless of ambient pressure, and is used for performance calculations. You can think of it as altitude relative to standard pressure. If in this case, with a pressure altitude of 0, the temperature is above the ISA sea level standard of plus 15 degrees, the density of the air will be less, and perhaps a lot less, with no direct indication to the pilot. If the temperature is plus 25, it would be 10 degrees above standard, or what is referred to as ISA plus 10. The density would be that which would exist at a higher altitude, and would be referred to as a high-density altitude. In practical terms, this means that the aircraft would need a higher TAS for a given dynamic pressure, and thence a longer takeoff run to achieve the necessary rotate IAS. To remember what a high-density altitude means, just think of it as high-density altitude.
The lift curve is a convenient way to illustrate the properties of an aerofoil under various conditions and in various configurations. The curve plots coefficient of lift, CL, against angle of attack, alpha. You may deduce from looking carefully at this curve that it is for a symmetrical aerofoil, since it starts with zero lift at the axis origin. The curve for a positively cambered aerofoil would actually have its zero lift point to the left of the CL axis, since the zero lift alpha for such an aerofoil is typically minus 4 degrees. The CL increases with angle of attack up to a maximum CL max, which corresponds to the critical angle of attack, above which lift decreases sharply, a phenomenon known as the stall, which will be covered in detail in a subsequent lesson. There are several important facts that become evident from study of the lift curve in association with the lift equation. To maintain a constant lift force, any change in dynamic pressure must be accompanied by an adjustment in angle of attack. For a constant lift force, each dynamic pressure requires a specific angle of attack. Minimum dynamic pressure is determined by CL max, which occurs at a specific angle of attack, the critical angle, which is between 14 and 16 degrees, depending on the aerofoil. The angle of attack for CL max is a constant for a given configuration. If more lift is required because of greater weight, a greater dynamic pressure, that is, more speed, is required at a given angle of attack. The greater the weight, the higher is the minimum dynamic pressure or speed required for level flight. The lift formula can be used to obtain data which can then be used to apply to the lift curve. But this can only properly be done if the specific values to be used are converted to SI units. To calculate speeds, we need to rearrange the lift formula to read velocity equals the square root of lift over half rho times CL times S. If the aircraft's mass is 60,000 kilograms, we need to multiply that by the force of gravity, 9.81 meters per second squared, to achieve a weight, which will be the same as the lift balancing it. The result is 588,600 newtons. If we convert the other elements, assuming ISA sea level density of 1.225 and a wing area of 105 square meters, using the CL max of 1.532, we now have the equation looking like this. When the calculation is done, the answer comes out as 77.3 meters per second. We need this speed in knots, so we multiply it by 3.28, which is feet per meter, giving 253.5 feet per second. To convert this to knots, we need to make it into feet per hour, which is 912,600. and then divide by the number of feet per nautical mile, 6,080, giving the final answer 150 knots. The same result can be arrived at rather more simply by dividing meters per second by 0.514 to get knots, but we include the steps to show you the logic. Thus, it can be seen that the angle of attack at CL max corresponds to a speed of 150 knots. This method can be used to ascertain the speed that applies to any CL or angle of attack, with a reduction of CL and angle of attack giving a higher speed. Aerofoils of differing sections and thicknesses will produce different lift curves. A symmetrical section of 12% thickness will give a curve that starts from 0 on both axes. In comparison, the curve for a symmetrical aerofoil of 6% thickness shows that it will produce less lift at any given angle of attack, and reach its CL max at a lower angle of attack and at a much lower value than the 12% section, which has a CL max some 70% greater. If the 12% section were to be cambered, its curve would move up and to the left. Up meaning that its CL max would be higher. The reason for this is that the section's stream tube has a smaller cross-section, giving greater acceleration and thus higher pressure differential. The curve's move to the left indicates that, at 0 degrees angle of attack, the aerofoil is producing lift. Zero lift is achieved typically at around -4 degrees with a cambered aerofoil. The reason for this is that, even below 0 alpha, the camber creates a smaller stream tube cross-section than a symmetrical section, and therefore generates a small amount of lift. The different types of aerofoil sections we have just looked at have various advantages and disadvantages. We have already seen that CL max may be increased by both camber and thickness. The importance of CL max is obvious. The greater it is, the lower is the minimum flight speed or stall speed, Vs. However, the thickness and camber required for the low Vs will also produce more form drag and larger twisting moments at high speed. A high CL max is only one of the requirements for an aerofoil section, but its main point is that it gives a low minimum flight speed. With the low Vs comes the penalty of a low efficient cruise speed, because of the excessive drag generated. It is thus better to use an aerofoil that is efficient at a high cruise speed, with the ability to increase camber temporarily when it is necessary to fly slowly, such as on the approach. This can be achieved by the use of hinge sections of the wing trailing and leading edges, collectively known as flaps. The lift curve can be used to gain useful information about an aerofoil's characteristics, and, when used in conjunction with the lift formula, can give further useful data. The lift curve will be seen again soon in the lift lesson, but in combination with its counterpart, drag curve. As you will see, drag is inseparable from lift. Drag is an aerodynamic force that acts parallel to and in the direction of the relative airflow and opposes the aircraft's forward motion. This lesson only considers drag in conjunction with lift, as drag is dealt with in detail later in the syllabus. As with other aerodynamic forces, drag forces can be expressed in the form of a coefficient, which is independent of dynamic pressure and surface area. Drag is the product of dynamic pressure, drag coefficient, and surface area. The drag coefficient, CD, being the ratio of drag per unit wing area to dynamic pressure. If the CD of a representative wing were to be plotted against angle of attack, alpha, the result would typically be a curve as shown on the screen. At low alphas, CD is low, and changes of alpha produce only small changes in CD. At higher alphas, however, the CD increase is exponential. Beyond the stalling or critical angle of attack at CL max, there is a further large increase in CD. The efficiency of the production of lift can be gauged from studying the ratio between lift and drag, a high lift-drag ratio being more efficient. The proportions of CL and CD can be calculated for any angle of attack. The graph on the screen shows that the lift-drag ratio increases up to a maximum at about 4 degrees, which is known as the optimum angle of attack. Above this angle of attack, the lift-drag ratio then decreases until CL max is reached. You should note that the plots of lift-drag and lift-drag ratio shown on this graph are to different scales, and thus the points of intersection of the curves are of no particular significance. The maximum lift-drag ratio, LD max, of a given aerofoil section will occur at one specific angle of attack, and if the aircraft is operated in steady level flight at this optimum angle of attack, it will generate the least possible drag for the amount of lift required. Any angle of attack higher or lower than that required for LD max will reduce the lift-drag ratio, and will thus increase the drag for the required lift. If an aircraft's weight changes, it will still be possible to achieve LD max at the same angle of attack as previously, but a change in weight requires a change in IAS to support the weight at the same angle of attack. The lower the weight, the lower the IAS required to stay at the LD max angle of attack, and vice versa. Changes in weight in a given configuration, or airframe contamination state, or at speeds below Mach 0.4, will not change LD max. The type of role an aircraft is designed for will, to a large extent, dictate the range of lift-drag ratios in which its LD max will fall. For example, a high-performance sailplane or glider will have an LD max between 25 and 60. For an airliner, it will be from 12 to 20, and for a single piston trainer, from 10 to 15. To sum up the main points about lift-drag ratio, it will be at its maximum at one specific angle of attack, known as the optimum angle of attack. This is typically about 4 degrees. Flight at any other angle of attack will give a lower lift-drag ratio, with more drag for the lift required. Changes in weight in a given configuration or airframe contamination state, or at speeds below Mach 0.4, will not change LD max. A given aerofoil section will always stall at the same angle of attack, its critical angle, but aircraft weight will affect the IAS at which this occurs. The reasons for this are explained fully elsewhere in the syllabus, but briefly, at a lower weight and a given angle of attack, the aircraft will require less speed to produce the lift needed to balance the lower weight. It's worth remembering then that the heavier the aircraft is, the higher will be its stalling speed, and that large modern jet transport aircraft may be carrying around half of their gross takeoff weight as fuel. Stalling speed will thus vary over a long flight, being considerably higher at takeoff than at landing. Surface irregularities, especially near the leading edge, have a considerable effect on the characteristics of aerofoil sections. CL max in particular is sensitive to leading edge roughness. The revised lift curve on the screen shows the effect of a rough leading edge compared to a smooth surface. CL max will decrease progressively with increasing roughness, because of the reduced acceleration of air over the rough section, and the consequent drop in the pressure differential. Roughness further aft of about 20% chord will have little effect on CL max or the lift curve slope. Frost, snow and even rainwater can significantly increase roughness. Dirt or slush picked up from contaminated parking areas, taxiways and runways, will also have a serious effect. In-flight airframe icing will accumulate on leading edges and can also disrupt the airflow and reduce CLmax. Depending on the type of ice and the rate of accretion, airframe icing can cause a serious loss of lift and a drop in CLmax. One of the most potentially dangerous consequences of such a situation is an unknown increase in stalling speed. When we compare the lift curve of a clean wing, that is, with all high lift devices up, with that of the same wing with flaps down, it can be seen that the lift curve moves up and to the left. This has the effect of increasing CLmax and slightly reducing the critical angle and the angle of attack for any given lift coefficient. The benefit of the increased CLmax is to reduce minimum flight speed or stall speed, VS, and thus allow lower speeds and shorter field lengths for takeoff and landing. The lift that a wing produces will vary greatly under different conditions of weight, surface contamination, and configuration. The appropriate lift curves can provide useful information about an aircraft's performance. So far in these lessons on lift, we have considered only two-dimensional airflow, and a sound understanding of this is the foundation for a full appreciation of the actual pattern of airflow around an aircraft. Even small changes of pressure will modify the airstream direction by inducing flow towards any region of lower pressure. This three-dimensional airflow can modify the angle of attack, creating an effective angle of attack. It may increase drag and alter stalling characteristics, and can even influence the control and stability of the aircraft. From now on, instead of just the aerofoil section, we will be considering the entire wing. And as a precursor to the next few lessons, you will need to be familiar with the terminology associated with wings. The wing area is the planned surface area of the wing and has the symbol S for surface. It is deemed to include any part of the wing covered by engine nacelles and the part of the fuselage in line with the wing, since the pressure pattern carries over these areas, allowing them to be legitimately considered as part of the entire area. The wing's span, lowercase b, is the distance from wingtip to wingtip, usually now quoted in meters. The chord is the distance from leading edge to trailing edge, and the average chord, lowercase c, is the geometric average. The product of the span and average chord is the wing area. The aspect ratio, or AR, is the proportion of the span and the average chord. That is, B over C. If the plan form is curved, for example like the Spitfire's elliptical wing, an alternative way of determining the aspect ratio is span squared over area. This assumes, of course, that you have a figure for the wing area. The aspect ratio of the wing determines the aerodynamic characteristics and structural weight. For example, a wing area of 100 square meters could be arranged in a high aspect ratio, here 51, or a low aspect ratio of, say, 3. Typical ARs vary from this value for a modern combat aircraft, through 12 for a high-speed jet transport, to 35 for a high-performance sailplane. Continuing with the terminology, we have root chord, which is the chord length at the wing centerline, denoted by CR. Logically, at the other end of the wing is CT, the tip chord. The ratio between these two is known as the taper ratio, CT to CR. The taper ratio affects the lift distribution and the structural weight of the wing. Ratios range from 1 for a rectangular wing to 0 for a delta wing with a pointed tip. For a swept wing, the sweep angle is usually measured as the angle between the line along the wing joining points of 25% chord and a line perpendicular to the root chord or aircraft centerline. Finally, the mean aerodynamic chord, abbreviated to MAC or MAC, is the chord drawn through the geographic center of the plan area. It is located at the reference axis of the aircraft and is a primary reference for longitudinal stability considerations. A rectangular wing of this chord and the same span would have broadly similar pitching moment characteristics. As mentioned in the last lesson, the third dimension in the airflow over a wing, lateral flow, is created by pressure differentials. Air flowing over the top surface of a wing is at a lower pressure than that beneath, which can be at a pressure similar to, slightly higher or slightly lower than ambient, depending on angle of attack and wing section. The pressure differential induces spanwise flow from high to low, towards the roots on the upper surface, and generally towards the tips on the lower surface. The trailing edge and wingtips are where the airflows interact. The crossover of the inward flow on the upper surface and the outward flow on the lower surface at the tips and trailing edge form vortices, particularly at the tips, where air can spill around them to the low pressure area on top. By convention, the wing is viewed from the rear, so the vortex at the left wingtip rotates clockwise, and at the right wingtip anti-clockwise. The arrangement of the forces can be seen with the vector triangle. At higher angles of attack, with a lower IAS, the shape of the triangle will change. As speed decreases, the chordwise vector will shorten, and the spanwise vector will lengthen, with the greater pressure differential that is creating the increased lift. The result is stronger wingtip vortices. In a more pictorial representation, the change of vortex, form, and strength with speed is shown on the screen. The general pattern of the vortices is also shown. Trailing edge vortices create certain vertical velocity components in the airflow near the wing, both behind and in front of it. These vertical velocities cause a downwash over the wing, which, in turn, causes a reduction in the effective angle of attack. As the vortices increase in strength with increased angle of attack at lower speeds, there is further reduction in the effective angle of attack. Because of this local reduction in effective angle of attack, the overall lift generated by a wing will be below that which would be generated if there were no spanwise pressure differential. It is, paradoxically, the production of the lift itself which reduces the magnitude of the lift. To replace the lift lost by the increased downwash, the aircraft must be flown at a higher angle of attack. If the vortices were absent, the lift vector would be at a right angle to the free stream relative airflow. But with the effective airflow created by the vortices, the lift vector is tilted back and creates drag, known as induced drag. The stronger the vortices are, the greater is the induced drag. Wingtip vortices, in particular their influence on upwash and downwash, have significant effect on several important areas of aerodynamics, stability and control. Some of these effects will be examined in the following lessons. Wingtip vortices can extend behind an aircraft for a considerable distance and can prove extremely hazardous to any aircraft unfortunate enough to encounter them. The maximum tangential airspeed in the vortex may be as high as 90 meters or 300 feet per second immediately behind a large aircraft. Wake turbulence is rarely detectable, so it is very important that pilots are aware of the potential distribution and duration of vortex wake turbulence, and of the effect of surface wind speed and direction on the normal behavior of wingtip vortices. For the information of all operators, The UK Civil Aviation Authority publishes an Aeronautical Information Circular, which describes the hazard and states the approach and departure separation in time for departures and distance for approaches required between various categories of aircraft based on their weight. The AIC is updated from time to time, the most recent at the time of writing being AIC Pink 72 of 2010. Wake vortex generation begins when the nose wheel lifts off the runway at rotation on takeoff and continues until the nose wheel touches down again on landing. Wake vortices exist behind every aircraft, including helicopters when in flight, but are most severe when generated by heavy aircraft. They present the greatest danger during the final approach and landing phases of flight. And on takeoff and initial climb. In other words, at low level, and where there is likely to be a lot of air traffic. A wake turbulence encounter can lead to loss of control, and possibly to structural damage. And, if the encounter takes place near the ground, may leave insufficient time or height to recover. The characteristics of the vortices are determined by the following aspects of the generating aircraft. First, the gross weight. The higher the weight, the stronger the vortices. A shorter wingspan will cause interference between the two vortices, which weakens them. As speed is reduced and the lift coefficient is correspondingly increased, the vortices will strengthen. At any given speed or weight, the lowering of gear and flaps will decrease vortex strength. Changes in pitch attitude, which are often associated with changes in speed, will also affect vortex strength, which increases with the angle of attack. Generally, the larger the aircraft creating the vortices is, compared to the aircraft encountering them, the greater will be the wake turbulence hazard. Typically, the two wingtip vortices remain separated by about 3/4 of the aircraft's wingspan, and in still air will sink slowly and level off, about 500 to 1,000 feet below the aircraft's flight path. There is evidence that a helicopter will produce stronger vortices than a fixed-wing aircraft at the same weight and speed. Behind a large aircraft, the vortex wake can extend as much as 9 nautical miles. If an aircraft is within 1,000 feet of the ground, the vortices will sink to within about twice the aircraft's wingspan on the ground, and in still air move outward at about 5 knots from the track of the generating aircraft. Please note that the rate of movement shown here is exaggerated, and that there is, of course, only one vortex per wing. In a crosswind, if the wind is light and steady, the vortex structure will drift with wind. If the crosswind is in the region of 5 knots, the downwind vortex will drift away, but the upwind vortex will more or less stay in the same place. There are 2 possible hazards in this situation. First, for aircraft departing from the runway used by the preceding aircraft illustrated, where the vortex stays in or close to the climb-out. And secondly, for aircraft using a parallel runway downwind of the situation shown, with the vortex drifting across the runway and climb-out. Similar hazards would exist for an aircraft following another on the approach. Vortices will, of course, decay with time, but the biggest influence on their dispersal is atmospheric turbulence. The stronger the wind, the more quickly the vortex will break down. The time separation minima, published in the AIC mentioned before, are applied by air traffic control, but these do not guarantee that an aircraft will avoid wake turbulence. The separation only reduces the likelihood of vortex encounter, and may decrease the severity of any effects if an encounter does occur. It is worth remembering that the most serious risks occur when following heavy large aircraft at low speed in light winds, and particularly when close to the ground. If the positions of the vortex wake of a preceding or crossing aircraft can be visualized, and this assumes the pilot knows the relative position of the other aircraft, then there is a reasonable chance of avoidance. Staying above or upwind of it will usually keep you clear. However, this may not be possible or advisable during a published procedure when in cloud. So adherence to the published separation minima is the safest option. The subject of wake turbulence is covered in further detail in the Air Law and Operational Procedures and Hazards section of the syllabus. When an aircraft is flying at any height significantly more than its own wingspan, the development of wingtip vortices is unaffected, and the vortices will have their normal effect of upwash in front of the wing and downwash behind it. However, during takeoff and landing, proximity to the ground, at heights less than the aircraft's wingspan, will prevent full development of the vortices, which reduces the upwash and downwash. This, in turn, causes the effective angle of attack of the wing to increase. This, with the associated aerodynamic changes which occur, is known as ground effect. This lesson examines what happens when an aircraft is in ground effect. Generally, lift will be increased and induced drag will be reduced. In addition, the reduced downwash will affect both longitudinal stability and tailplane pitching moment. The influence of ground effect depends on the distance of the wing above the ground. A large reduction in the induced drag coefficient, CDI, will only occur when the wing is very close to the ground, that is, within about half a wingspan. If we take a few examples from the graph on the screen, which plots reduction in CDI against the ratio of height to wingspan, or h over b, we can see that for an aircraft with a wingspan of 40 meters, or 131 feet, the reduction in CDI is only about 1.5% at a height of 40 meters, that is, with a height-span ratio of 1. As the height comes down to 10 meters, a ratio 0.25, the CDI has dropped by 23.5%. But at 4 meters, a ratio of 0.1, the induced drag coefficient has fallen by a substantial 45%. The height of the wing above the ground when the aircraft is in the landing attitude is determined by its mounting position on the fuselage. From the graph just used, it was seen that the last few meters of descent make a big difference to the reduction of drag coefficient, so it can be said that low-wing aircraft will experience a greater degree of ground effect than high-wing aircraft. Whilst ground effect may possibly change the aerodynamic characteristics of the tailplane in its own right, a low-mounted tailplane will have its effective angle of attack modified by the change in downwash. As the aircraft comes into ground effect, the tailplane loses downforce, causing a nose-down pitching moment. A high-mounted tailplane may be above the influence of the change in downwash angle, and therefore not suffer the same disadvantage. Assuming a tailplane is affected by changes in downwash, it is interesting to consider how the camber of the tailplane will affect the result on its pitching moment. Looking first at a positively cambered tailplane, ground effect creates an increased upforce. In other words, a nose-down moment. If the camber is negative, the change in downwash produces a decrease in the downforce, and again the result is a nose-down pitching moment. With a symmetrical tailplane, the effect is similar to the negative camber, so it can be said that a decrease in downwash will always result in a nose-down pitching moment. The opposite is true of increased downwash. Ground effect is not the only cause of changes in downwash. Flap movement and the formation of shock waves at transonic speeds will also alter the airflow, so appreciation of these phenomena is an important factor in a full understanding of the principles of flight. Increasing downwash, G to D, gives a decrease in tailplane effective angle of attack, and decreasing downwash, D to G, gives an increase. It is important to understand the effect of changes in downwash on the tailplane's angle of attack, but vital to understand their influence on pitching moments. Let's consider an aircraft entering ground effect, assuming that CL and IAS remain constant. As the aircraft descends into ground effect, the following changes take place. The decreased downwash will give an increase in the effective angle of attack, which requires a smaller wing angle of attack to produce the same lift coefficient. If a constant pitch attitude is held when entering ground effect, the increase in lift will reduce the rate of descent or cause the aircraft to level off, an effect known as floating, which lengthens the landing distance. Additionally, the decrease of induced drag will cause a reduction in deceleration, and any excess speed above the correct threshold speed could lead to a considerable float distance. The reduction in power required might also give the aircraft a tendency to rise above the intended descent path to the runway, known as ballooning, unless power is reduced. If the airspeed is allowed to decay late in the final approach, and the pilot attempts to arrest the ensuing increased sink rate by raising the nose, increasing the angle of attack, the wing may stall on entering ground effect, resulting in a heavy landing. The pilot may need to move the control column aft in order to restore sufficient downforce to achieve the desired landing attitude. The loss of downforce is due to the decreased downwash over the tailplane and the associated change in the effective angle of attack. Changes in the airflow around the aircraft may cause differences in pressure error in the pitot static system. Local pressure at the static port is likely to increase, which will make the airspeed indicator and altimeter under-read. The effects of climbing out of ground effect are generally the opposite to those of entering. If we again consider an aircraft climbing away with a constant CL and IAS, the following changes will occur. The lift coefficient will reduce, requiring an increase in angle of attack to compensate. The drag, and thus power required, will increase. The increase in downwash will generally produce a nose-up pitching moment, so the pilot will have to move the control column forward to compensate. The pressure error change, which would occur on entering ground effect, is reversed, with a small local static pressure decrease and a slight increase in ASI and altimeter indications. It is possible to become airborne in ground effect at an airspeed and angle of attack such that, after leaving ground effect, the aircraft could sink and even settle back onto the runway. It is therefore vital that the correct speeds and attitudes are used for takeoff. The nose-up pitching moment may induce an inadvertent over-rotation and tail strike. This lesson concludes the section on lift, which is a basic part of the principles of flight which requires a thorough understanding, since a good deal of the remainder of the syllabus is concerned with the application and management of the forces involved. The next section deals with drag, a force closely allied with the generation of lift. By the end of this series of lessons on drag, you should be able to define and understand the elements that make up total drag. They are skin friction drag, form drag, and interference drag, which together are termed parasite drag and induced drag. You will also learn about the effect of lift and configuration on parasite drag, and what is meant by the term streamlining. Drag is the force which resists the forward motion of the aircraft. It acts parallel and in the same direction as the relative airflow, that is, in the opposite direction to the flight path. You need to remember that it makes no difference to the airflow pattern if the aircraft is moving through the air or if the air is moving past the aircraft. It is the relative velocity that matters. Every part of an aircraft that is exposed to the airflow, not just the wing shown here, produces resistance, which can be categorized into various types, which together contribute to total drag. Total drag is subdivided into two main types: induced drag, or lift-dependent drag, which is the result of lift generation, and parasite drag, or zero-lift drag, which is independent of lift generation. Parasite drag can be further subdivided into skin friction, form drag, and interference drag. Skin friction and form drag together are known as profile drag. To start our examination of drag, we will look at parasite drag. If an aircraft were to be flying, but producing no lift or downforce, the only drag present would be parasite drag, which, as already seen in the drag family tree, is comprised of skin friction, form, and interference drag. An aircraft's skin, regardless of material, will to some degree have imperfections or roughness in its surface, due to paint, rivets, and other protrusions, contamination, etc. Air particles in direct contact with the surface are accelerated to the speed of the aircraft and are carried along with it. Adjacent particles will be accelerated by contact with the lower particles, but their velocity will be less, but only slightly so, because of the low viscosity of the air. As distance from the surface increases, less and less acceleration of the air takes place. Thus, there exists over the entire surface a layer of air whose relative velocity ranges from zero at the surface to a maximum at the boundary of the air that is affected by the passage of the aircraft. This layer, from the surface to the point where there is no detectable viscous effect, is known as the boundary layer. Where the change of speed is smooth and progressive, the flow is referred to as laminar. In flight, the nature of the boundary layer will determine the maximum lift coefficient, the stalling characteristics, the value of form drag, and, to some extent, the high-speed properties of the aircraft. The boundary layer is not always smooth or laminar. In general, the flow over the front of a surface will be laminar, but will become turbulent some distance back, at a point known as the transition point. The increased rate of change of velocity at the surface in turbulent flow will give more skin friction than laminar flow. A turbulent boundary layer also has more kinetic energy than a laminar layer, and is more resistant to separation. A forward movement of the transition point will increase skin friction because of the greater area of turbulent flow. There are two factors that can affect the position of the transition point. First, the surface condition. The thin laminar layer is very sensitive to any irregularities. Roughness on the leading edge skin can cause early transition to turbulent flow, which fans out downstream, causing a marked increase in skin friction drag. Secondly, a laminar layer cannot exist where pressure is rising in the direction of flow. Over a curved surface, like a wing, the transition point is at or near the point of maximum thickness, which is the point of lowest pressure. So the flow is against what is called an adverse pressure gradient. The transition point is thus further forward than if the surface were flat. It is worth noting that for clarity, the depth of the layers has been exaggerated in the diagrams. In reality, the laminar boundary layer is about 2 mm deep and thickens to about 20 mm in the turbulent flow. Form drag results from the pressure at the leading edge of a body being greater than at the trailing edge, hence its alternative name. Overall, skin friction causes a continual reduction of boundary layer kinetic energy as flow continues back along the surface. The adverse pressure gradient after the transition point also causes a further drop in kinetic energy. If there is insufficient kinetic energy to overcome the adverse pressure gradient, the lower levels of the boundary layer stagnate, and the upper levels overrun them, causing separation. The surface flow after the separation point will now be forwards, but because of separation, there will be a lower pressure at the trailing edge than at the leading edge. The aerodynamic force from high to low pressure thus acts against the direction of flight as form or pressure drag. The loss of the kinetic energy required to overcome the adverse pressure gradient and prevent separation of the boundary layer can be caused by various factors. As angle of attack increases, the transition point moves closer to the leading edge, and the adverse pressure gradient becomes stronger. This moves the separation point forward. Eventually, the separation point is so close to the leading edge that there is not enough wing area to generate the lift required. The CL decreases rapidly, and the wing stalls. Another factor concerns transonic flight. When a shock wave forms on the upper surface, the increase of static pressure through the shock wave creates an extreme adverse pressure gradient. If the shock wave is strong enough, separation will occur immediately behind it. This phenomenon will be explained more fully in the part of the syllabus on high-speed flight. Coming back to subsonic flight, a turbulent boundary layer will resist separation better than a laminar flow meeting the same adverse pressure gradient. In some circumstances, this is an advantage. For example, some aircraft have small vanes called vortex generators, fitted on top of the wing ahead of the ailerons, to ensure that the boundary layer remains attached longer than on the rest of the wing, to retain control effectiveness at speeds close to the stall. In normal flight, however, laminar flow is preferable, owing to its lower drag penalty. The term streamlining is often used to refer to the smoothing of a vehicle's or aircraft's design shape, or the addition of fairings or fillets to modify it. But more specifically, it is the shaping of a body to keep separation as close to the trailing edge as possible. Streamlining increases the ratio between the length and depth of a body, reducing the curvature which induces an adverse pressure gradient. The best fineness ratio, as it is known, has been found to be 3:1. The combination of form drag and skin friction is known as profile drag, as it can be considered that it results from the cross-sectional area or profile of the aircraft presented to the relative airflow. The final element of parasite drag is interference drag. When considering a complete aircraft, the parasite drag in total will be greater than the sum of its parts. This additional drag is the result of interaction between the boundary layers of adjacent parts of the aircraft. Probably the best example of this is the junction between fuselage and wing at the wing root. The air is accelerated over the wing and will be faster than the airflow over the fuselage. Where the two flows mix in the angle between the two surfaces, the interference causes turbulence and drag. The solution to this problem is to add fillets to smooth out the transition between the surfaces, making the velocity change more gradual, minimizing the turbulence and thus the drag. There are a few factors which significantly affect parasite drag. First, like lift or any other kind of drag, it will vary directly with the square of the indicated airspeed. If IAS is doubled, parasite drag is quadrupled. And if IAS is halved, parasite drag is reduced to a quarter of its previous value. Changes in configuration will also have an effect on parasite drag, which varies in direct proportion to the frontal area presented to the airflow. This cross-sectional area is known as parasite area. If flaps and landing gear are lowered, speed brakes extended, or roll control spoilers operated, parasite area, and thus parasite drag, will increase. Airframe contamination, that is, accumulations of ice, snow, frost, slush, mud, or even insects, will increase the parasite drag coefficient. In the case of severe airframe icing, the parasite area may be increased also. From this examination of parasite drag, we shall move on in the next lesson to the other main constituent of total drag, induced drag. Induced drag is an undesirable byproduct of lift. Wingtip vortices modify upwash and downwash in the vicinity of the wing, and these changes in the relative airflow produce a rearward component in the lift vector, known as induced drag or lift-dependent drag. At low indicated airspeeds, IASs, the angle of attack will be greater than at high speed, and this will produce stronger vortices. The stronger the vortices are, the greater will be the induced drag. The airflow over the top surface of a wing is at a lower pressure than that below the wing. The two flows are modified by this pressure differential, which creates a spanwise element towards the root on the top surface and towards the tips on the lower surfaces. And these flows interact at the trailing edge and wingtips. In the conventional view of the aircraft from the rear, the vortices produced by this interaction rotate clockwise at the left wingtip and anti-clockwise at the right wingtip. At lower IASs, and therefore higher angles of attack, the decreased chordwise vector and increased spanwise vector, due to the greater pressure differential, will increase the resultant spanwise flow, making the vortices stronger. Wingtip vortices create certain vertical velocity components in the airflow around the wing, both in front of it and behind it. Compared with the relative airflow, the vortices increase upwash and downwash over the outer portions of the span, which reduces the effective angle of attack. If we look at this effect in cross-section, the vertical velocities can be seen to be greatest close to the wing where the vortices are strongest, and immediately ahead of the wing. These vertical velocities, then, are a function of vortex strength. So the stronger the vortices, the greater the reduction in effective angle of attack. Since TAS is also a principal factor in the relative airflow, these two factors combine to determine the change in effective angle of attack. Because of the localized reduction in effective angle of attack, the overall lift generated by a wing is actually less than it would be if there were no spanwise pressure differential. And paradoxically, it is the production of the lift itself that reduces the magnitude of the lift being produced. To replace the lift lost by the increased upwash and downwash, the wing must be flown at a higher angle of attack than would otherwise be necessary. The rearward tilt of the lift vector caused by this extra angle is induced drag. There are three main factors which affect induced drag, two of which will vary during flight, namely lift and speed. Taking lift first, it can be assumed that, since induced drag is a component of the lift force, the greater the lift, the greater will be the induced drag. Lift for level flight will equal weight, so induced drag will depend on the weight of the aircraft, a heavier aircraft generating more induced drag. Some maneuvers, for example turns, require the lift force to exceed the weight. The ratio of lift to weight being known as the load factor, or G, for gravity. As lift is greater than weight in a turn, so will induced drag be greater than in straight and level flight. Thus induced drag also increases as the load factor increases. Induced drag will increase in proportion to the square of the lift force. For a constant lift force, induced drag decreases with increased speed. Because as speed increases, the downwash caused by the wingtip vortices becomes less significant, and the rearward inclination of the lift vector is less. Induced drag varies inversely as the square of the speed. The third factor which will affect induced drag, and which will not change in flight, except perhaps slightly with the extension of large Fowler flaps, increasing the chord of the inboard section of the wing, is aspect ratio. The tip vortices of a high aspect wing affect a smaller proportion of the span, so the overall change of downwash caused by the vortices is smaller, giving less rearward tilt to the lift vector. Thus, for a given lift force, induced drag decreases as aspect ratio increases. The induced drag coefficient is inversely proportional to the aspect ratio. From the factors just discussed, and particularly the last, aspect ratio, it can be seen that a high aspect ratio, that is, a fairly long, narrow wing, is preferable for aircraft designed to operate at around Mach 0.8 for the greatest part of their flights, as are conventional high-speed jet transport aircraft. This is because of the relationship between induced drag, lift coefficient, both low at high speeds, and aspect ratio, expressed in the formula CDI equals CL squared over AR. The higher the aspect ratio, the lower the induced drag. We can examine the effect of aspect ratio by looking at the lift curves for various configurations. The starting point is a wing of a typical section, but of infinite aspect ratio, obviously a purely theoretical situation. But if the wing is given an AR of 18, it can be seen that reduction in AR increases the angle of attack necessary to produce a given lift coefficient. Further reduction in AR, shorter wings, will continue to increase the angle of attack required for CL max. Higher aspect ratio wings are more sensitive to changes in angle of attack, but require a smaller angle of attack for maximum lift. If comparison is made between the coefficients of lift and induced drag, again, starting with a theoretical wing of infinite length, we can see that for a given lift coefficient, a high AR wing will have a lower induced drag coefficient than a low AR wing. At the high lift coefficients associated with low IASs, the induced drag is high and increases rapidly with CL. The lift and drag curves for high AR wings show continued strong increase in CL with angle of attack up to the stall, and large changes in CD only at the point of stall. From a practical point of view, there are restrictions on the aspect ratio of the wing in designing an aircraft. A long high aspect ratio wing will impose weight limits in a structure's strength being rigid enough to resist excessive bending. The longer the wing is, the more susceptible it is to any bending moment. Wing bending moments can, however, be reduced by mounting engines in underslung pods and carrying fuel in the wings. Some aircraft have to keep a certain amount of fuel more in their outboard tanks than that in the inboard tanks, known as wing relieving fuel, to reduce the wing bending moment. The weight of the fuel counters the upward force of lift from the outer wing. A high aspect wing, particularly at low airspeeds, will suffer from a reduced rate of roll compared with a wing of the same chord but shorter span. The reduction is caused, only whilst the aircraft is rolling, by the increased vertical tip speed of the longer wing, adding to the wing's forward TAS to cause a greater effective angle of attack with its attendant induced drag. The greater the effective angle of attack at the tip, the more will be the resistance to roll. This phenomenon is known as aerodynamic damping and will be covered in greater detail later in the syllabus. A long wing will allow less wingtip ground clearance in maneuvers close to the ground during takeoff and landing, which could be a significant factor in a crosswind or gusty conditions. The formula for induced drag, as you will see on the screen, is very similar to the basic lift and drag formulae. On first sight, the equation would seem to imply that induced drag, dI, increases with speed. However, the induced drag coefficient, CDI, is proportional to the square of the lift coefficient, CL squared, and inversely proportional to wing aspect ratio, AR. To maintain a constant lift force, as speed increases, CL must be reduced. Thus, with an increase in speed, CDI actually decreases. We can work through an example which illustrates the change in CDI with speed, which leads to the change in DI. If an aircraft's speed is increased from 80 knots, 41 meters per second, to 160 knots, 82 meters per second, the dynamic pressure will be 4 times greater. ISA sea level density is used here, but any constant density will give the same result. Referring to the lift formula, lift equals Q times CL times wing area S. If dynamic pressure is 4 times greater because speed is doubled, CL must be reduced to 1/4 of its previous value to maintain a constant lift force. If we apply 1/4 of the previous CL to the CDI formula, then the new CDI equals 1/4 CL squared over AR. And as AR is constant, CDI equals 1/4 squared, or 1/16 of the previous CDI. If 1/16 of the previous CDI is applied to the induced drag formula, we get induced drag equal to 1/4 of its previous value. The conclusions are that if speed is doubled in level flight, dynamic pressure will be quadrupled, CL must be decreased to 1/4 of its previous value, and the induced drag coefficient will be 1/16, and the induced drag 1/4 of their previous values. If speed is halved, dynamic pressure will be 1/4 of its previous value, CL will need to be quadrupled, CDI will be 16 times greater, giving 4 times the induced drag. From what you have seen in this lesson so far, you will know that induced drag is low at high speeds, but at low speeds it comprises over half the total drag. It has also been shown that a high aspect ratio wing reduces the strength of the wingtip vortices for a given lift force, but that there are practical restrictions, both structural and aerodynamic, on very high aspect ratio wings. So other methods of reducing vortex strength have been devised. A flat plate mounted vertically on the end of the wing will restrict the flow of air from the high underside pressure to the low upper surface pressure, and has a similar effect to a high aspect ratio wing, but without the associated bending loads. However, the plate itself can cause parasite drag, and at higher speeds there may be no overall drag saving. Fuel tanks mounted at the wingtips will have a similar beneficial effect to end plates in reducing induced drag, with the added benefit of a reduction in wing root bending moment. Probably the most widely seen method of controlling wingtip vortices is the winglet, which is now incorporated into many categories of aircraft, large and small. Small vertical or near vertical extensions of the wingtip are shaped and angled to the induced airflow, generating a small forward force, or negative drag. Winglets also partly block the flow of air from lower to upper surfaces, reducing the tip vortex strength. The small vortex created by the winglet also interacts with and further reduces the strength of the main vortex. Finally, simpler variations of wingtip shape, such as turned up or turned down tips, can be used to reduce induced drag. Vortices are weakened by the blocking of airflow from lower to upper surface round the wingtips. Parasite drag, which is the sum of skin friction, form and interference drags, is so called because it is not directly associated with the generation of lift. However, although the connection is not direct, parasite drag does in reality vary with lift. As the CL increases with higher angles of attack, the parasite area increases with the greater frontal area presented to the relative airflow. Graphically, the increase of drag against lift can be shown as on the screen, with parasite drag in blue and induced or lift-dependent drag in red. However, the part of parasite drag above the minimum value occurring at zero lift is normally included with the induced drag coefficient, as shown in the second graph, where the parasite drag coefficient remains constant at its minimum against the increase in CL. Parasite drag is unaffected by the magnitude of lift, but varies with dynamic pressure and area. If all other factors are held constant, it changes significantly with frontal area. For example, lowering the gear and flaps can increase the parasite area by up to 80%. So at any given IAS, the parasite drag would increase by the same proportion. If altitude is changed, but at a constant IAS, the parasite drag would not change because of the altitude change, but would change in direct proportion to the parasite area during configuration change, as it is dependent on dynamic pressure. The effect of speed alone is the most important effect. If all other factors remain constant, doubling the speed will give 4 times the dynamic pressure, in accordance with the formulae for lift and drag being based on speed squared, and hence 4 times the parasite drag. By the same token, halving the speed will give 1/4 of the drag. This variation of parasite drag shows that it will be of greatest importance at high IASs and of least significance at low speeds. For example, an aircraft at a speed just above the stall could be generating parasite drag which is only 25% of its total drag. At the other end of the scale, literally, at its maximum level flight speed, the parasite drag could comprise almost 100% of the total drag. This predominance of parasite drag at high speed reinforces the need for clean airframe design and good streamlining for the best high-speed performance. This consideration of variations in parasite drag leads to an examination in the next lesson of the combination of parasite and induced drag into total drag and its significant values. An aircraft's total drag can be defined as the sum of its parasite drag and induced drag. This lesson examines the essential aspects and significance of total drag. If the curves for parasite drag and induced drag are plotted together, you can easily see the predominance of induced drag at low speed and of parasite drag at high speed. If the two sets of values are combined, we get a curve for total drag, a shape with which you will become very familiar. Because of the way that the two component types of drag vary with speed, the speed at which total drag is at its minimum occurs where the induced and parasite drags are equal. This minimum drag speed, usually referred to as min drag speed or VMD, is an important reference for many aspects of aircraft performance. range, endurance, glide, maneuver, landing and takeoff performance are all based on some relationship involving the aeroplane total drag curve. Since flying at VMD incurs the least total drag for flight with lift equaling weight, the aircraft will also be at the angle of attack for the maximum lift-drag ratio, LD max, which is around 4 degrees. It is important that you remember that LD max is obtained at a specific angle of attack, and also that the maximum lift-drag ratio is a measure of aerodynamic efficiency. On this subject, it is worth noting that if an aircraft is operated at the LD max angle of attack, drag will be at a minimum while generating the required lift. Any angle lower or higher than that increases the drag for a given lift force. More drag requires more thrust, which is inefficient and costly. You should also note that if IAS is varied, the lift-drag ratio will vary. Lift-drag ratio can be presented in a polar diagram, which plots CL against CD. This shows the CL increasing initially more rapidly than CD, but ultimately CD increases more quickly. LD max can be found from the drag polar by drawing a tangent to the curve from the origin, the slope of the tangent determining the value of the maximum lift-drag ratio. This is a common method of displaying the lift-drag ratio, and you will become quite familiar with it. As fuel is consumed, gross weight reduces, requiring less lift and reducing induced drag. The effect on total drag is that the curve moves down and to the left, as total drag and VMD are reduced. If the aircraft is operated at a higher weight, the curve moves up and to the right, as a result of the greater induced drag, and VMD occurs at a higher IAS. Changes in configuration, as for example on the approach to land, where landing gear, flaps, and air brakes or spoilers will be extended in a sequence appropriate to type, will create significant increases in parasite drag, but differing variations in induced drag. More lift with flaps with the increased CL, less with spoilers. The overall result is an increase in total drag, but a reduction in the min drag speed, with the curve moving up and to the left. Since transport aircraft tend to operate mostly at steady indicated airspeeds, it is relevant to consider variations of drag with IAS. At a constant IAS, dynamic pressure remains constant, so even if altitude is changed, drag will not change, even though TAS will change according to the changes in density with climb or descent. For an aircraft to be in steady flight, it must be in equilibrium. That is, with no out-of-balance forces or moments. When it is trimmed to fly at a steady speed, thrust and drag are equal. Therefore, when an aircraft is in steady flight, it can be said that the terms drag and thrust required are essentially interchangeable, so that when considering a total drag curve, it could also be looked at as a thrust required curve. For an aircraft in steady flight, if there is a change in speed without a change in power or thrust, the thrust available, there will be either an excess or a deficiency of thrust available, depending on the trim speed. We shall consider an aircraft at two speeds, at points A and B. If at speed A the speed is disturbed and rises, drag also rises, and a thrust deficiency exists. The aircraft then decelerates and settles back at its original speed. In this area of the curve, then, the aircraft is speed stable. Similarly, if the aircraft were to lose speed, drag would decrease, and the aircraft would regain the lost speed. Considering the aircraft at speed B, if it gains speed, drag decreases, and with an excess of thrust, the aircraft's speed will continue to drift up to VMD. In this area of the curve, the aircraft is speed unstable. Possibly, the most potentially hazardous situation occurs with a speed decrease in the speed unstable part of the curve, as the aircraft would then tend to decelerate further unless the deceleration is rectified with a prompt and generous application of thrust. Flight in this region of the curve is often referred to as being on the wrong side of the drag curve. Thinking back to earlier in the lesson, you will remember that lowering gear and flap and extending speed brakes lowers VMD, which has the benefit of extending the speed stable region to the left. Indeed, some aircraft fitted with air brakes routinely fly approaches with brakes out for that very reason. Finally, you will notice that the curve either side of VMD is fairly flat. In this region, the neutral IAS area, there is no distinct tendency to either speed stability or instability. However, the general rule to remember is that above VMD, the aircraft will be speed stable, and below it, speed unstable. Following on from your study of total drag, we can examine the relationship between thrust, drag, and power. You have already seen that drag in certain circumstances can also be referred to as thrust required, and you will see that a similar relationship exists with power required. They are both important airframe considerations. Although pilots tend to use the word power when discussing aircraft handling, quite often it is the case that they should be referring to thrust. Thrust is a force, a push or a pull, which opposes drag, but power is a rate of doing work. Power, then, is work over time, and work equals force times distance. So power must be force times distance over time. The force we are concerned with here is drag. Distance over time is speed, and the only true speed is the speed of the aircraft through the air, true airspeed, or TAS. We can thus rewrite the equation to read power required equals drag times TAS. If an aircraft climbs at a constant indicated airspeed, drag will remain constant, but TAS will be increasing, so power required will increase. As stated in the first part of the lesson, power is a rate of doing work, and so we must consider power required, since when the aircraft is climbing, work is being done to raise it to a higher altitude. Logically, the maximum work can be done on the aircraft in the minimum time, when the power available from the engine or engines is greatest, and the power required by the airframe is least. For easy reference, keep in mind the definition that power is a rate of doing work, and associate the words power and rate. For example, the minimum rate of descent is achieved when the aircraft is flown at the minimum power required speed, known as VMP, or min power speed. These considerations and other associated factors are covered in detail in the lessons on aircraft performance and flight mechanics. The diagrams on the screen represent data for one particular aircraft in level flight at one weight, and at sea level where IAS equals TAS. Starting with a curve for drag or thrust required against TAS. The graph for power required is constructed by multiplying each value of drag by the appropriate TAS and converting it to kilowatts. Note that the min power speed, an IAS, is lower than min drag speed. The effect of a change in altitude for an aircraft flying at min drag speed would be that its drag would not change, VMD being an IAS. However, the aircraft's TAS would be increasing. And since the power required would also be increasing in proportion, the ratio of TAS to power required is unaffected, and VMP will remain a lower speed than VMD. The information in this lesson is mainly concerned with performance, especially the relationship between minimum power speed and minimum drag speed, which is of importance when considering rates and angles of descent in a steady glide, which is covered elsewhere in the syllabus, in Chapter 12 of the OAA Principles of Flight book. A summary of the salient points from this series of lessons on drag follows in the next lesson. This final lesson in the series on drag consists of a summary of the main points. As a reminder of the divisions of drag, here is the family tree. Parasite drag is made up of skin friction drag, form or pressure drag, which together are known as profile drag, and interference drag. Parasite drag varies as the square of the IAS. If you double the speed, you get 4 times the parasite drag. If you halve the speed, you get 1/4 of the parasite drag. Designers can minimize parasite drag by streamlining, incorporating fillets and fairings, using laminar flow wing sections, and minimizing frontal area. Flight crews must ensure that the airframe, and particularly the wing, is not contaminated by ice, snow, frost, slush, insects or mud. On induced drag, you will need to remember the following key points. Spanwise airflow generates wingtip vortices. The higher the CL, or the lower the IAS, the stronger the wingtip vortices. Wingtip vortices strengthen downwash. Strengthened downwash inclines wing lift rearwards. The greater the rearward inclination of the wing lift, the greater will be the induced drag. Induced drag varies inversely as the square of the indicated airspeed. If speed is halved, the CDI will increase by 16 times, and the induced drag by 4. If speed is doubled, the induced drag coefficient will reduce to 1/16 of its previous value, and the induced drag to 1/4 of its previous value. Designers can minimize induced drag by using a high aspect ratio planform, using a tapered wing planform with wing twist or washout, and/or spanwise camber variation, and by incorporating end plates, tip tanks, winglets, or tip shaping. On induced drag, you will need to remember the following key points. Spanwise airflow generates wingtip vortices. The higher the CL, or the lower the IAS, the stronger the wingtip vortices. Wingtip vortices strengthen downwash. Strengthened downwash inclines wing lift rearwards. The greater the rearward inclination of the wing lift, the greater will be the induced drag. Induced drag varies inversely as the square of the indicated airspeed. If speed is halved, the CDI will increase by 16 times, and the induced drag by 4. If speed is doubled, the induced drag coefficient will reduce to 1/16 of its previous value, and the induced drag to 1/4 of its previous value. Designers can minimize induced drag by using a high aspect ratio planform, using a tapered wing planform with wing twist or washout, and/or spanwise camber variation, and by incorporating end plates, tip tanks, winglets, or tip shaping. Total drag is the sum of parasite and induced drag. Total drag is a minimum when parasite and induced drag are equal. At low IAS, induced drag is dominant. At high IAS, parasite drag is dominant. The IAS at which the two component drags are equal is called minimum drag speed, VMD. As gross weight decreases in flight, induced drag, total drag, and VMD all decrease. At a constant IAS, altitude has no effect on total drag, but TAS will increase as density reduces with higher altitude. Configuration changes, which increase the parasite area, such as landing gear, flaps and speed brakes, increase parasite and total drag, but reduce VMD. An aircraft flying at a steady IAS higher than VMD with a fixed power setting will have speed stability. An aircraft flying at a steady IAS at VMD or slower with a fixed power setting will usually not have speed stability. If an aircraft at a steady IAS at a fixed power setting within the non-stable IAS region encounters a disturbance which slows the aircraft, it will tend to slow further. IAS will tend to continue to decrease and the total drag to increase. The IAS for minimum power required, VMP, is slower than the minimum drag speed, VMD. Maximum TAS to power ratio, which is 1.32 VMP, occurs at VMD.
This series of lessons will teach you about the many aspects of the stall, an aerodynamic phenomenon which can result in loss of height and ultimately loss of control if not correctly recognised and handled. Such a situation would obviously be potentially very hazardous at low level on the approach or after takeoff. It is vital, therefore, that a pilot should be able to identify the signs and symptoms of stalls in any configuration or stage of flight, in order to prevent or recover from a stall with minimum height loss. You will be taught how to do this during your flying training, but these lessons will give you the theoretical knowledge you will need to understand how and why stalls happen. Different types of aircraft exhibit different stalling characteristics, some less desirable than others, but all should give the pilot some indication of an incipient stall. Airworthiness authorities specify the minimum stall qualities that an aircraft must possess. Reference will be made in the course of the lessons to such regulations for training purposes, but you should note that these requirements are occasionally subject to change. The coefficient of lift, or CL, of an aerofoil increases with angle of attack up to a maximum CL max. Any further increase above this critical angle of attack or stalling angle will make it impossible for the airflow to follow the upper contour of the wing smoothly. The flow will separate from the surface, causing CL to decrease and drag to increase rapidly. Since the CL max of an aerofoil corresponds to the minimum steady level flight speed, the 1G stall speed, it is an important point of reference. The stall, then, is caused by airflow separation, which occurs either when the boundary layer has insufficient energy or the adverse pressure gradient becomes too great. If we look at a sequence of an approach to the stall, we can see that at low angles of attack, virtually no flow separation occurs before the trailing edge, the flow being attached over the rear part of the wing in the form of a turbulent boundary layer. As angle of attack, or alpha, is increased, the adverse pressure gradient increases, reducing the kinetic energy, and the boundary layer will begin to separate from the surface at the trailing edge. Further increase of alpha makes the separation point move further forward, and the area of the wing that is generating a pressure differential, and thus lift, becomes progressively smaller. At alphas greater than the critical angle, which will depend on the wing planform, the extremely steep adverse pressure gradient will have caused so much separation that the wing can no longer generate enough lift to support the aircraft's weight, and the wing is stalled. It is important to remember that the angle of attack is the angle between the chord line and the relative airflow. Therefore, if the angle of attack is increased up to or beyond the critical angle, an aeroplane can be stalled at any airspeed or flight attitude. If we study the lift curve shown in this sequence, it can be seen that the increase in CL is linear over a large proportion of the range of alpha up to the stall. But as the effects of separation begin to be felt, the curve begins to flatten. Eventually, CL reaches a peak and then drops at an angle steeper than the rate of increase. The alpha at which it reaches its peak is called the critical or stalling angle of attack, and the corresponding value of lift coefficient is CL max. Most aeroplanes will stall at around 14 to 16 degrees alpha. Stall characteristics vary with different kinds of aircraft, but there are common factors which may occur with all aeroplanes. For modern aircraft, during most manoeuvres, the onset of the stall is gradual. The first indications may be provided by any or all of the following. Flight controls less effective than usual. Speed low and decreasing. Nose attitude higher than normal. Light aerodynamic buffet. Or the operation of a stall warning or stall prevention device. If the stall is allowed to progress beyond the incipient stage, any one of the following is symptomatic of a fully developed stall. Wing drop, nose drop, heavy aerodynamic buffet, or a loss of height. These symptoms form part of the formal stall recognition conditions described shortly. The behaviour of various types of aircraft at the stall is covered in more detail later, and recovery from the stall is described in the next part of the lesson. If a stall occurs, either incipient or fully developed, the principal action that must be taken is to reduce the angle of attack below the critical angle to decrease the adverse pressure gradient. This action may consist simply of releasing back pressure on the control column or moving it smoothly forward until the wings are unstalled. Excessive forward movement of the controls would lead to an unnecessary height loss during recovery. The use of full or maximum permitted power is usual during stall recovery to minimize height loss. As the angle of attack reduces, the airspeed will increase, and at a safe margin above the stall speed, any lost height can be regained by moving the control column back. Pilots should be careful not to pitch up too quickly, as this may restall the wing, even at a higher speed, which is known as a secondary stall and is covered in detail later in this series of lessons. The rudder should be used with great caution at any time when stalled or close to the stall, because of the possibility of causing a spin, on which more later. It is safer to use the rudder only after the wings are unstalled, and then only to prevent further yaw if a wing has dropped because it has stalled slightly before the other. It is generally safer only to use the ailerons to level the wings, also once the wings are unstalled. On swept-wing aeroplanes, the ailerons can be used to correct a wing drop, coordinated with a small amount of rudder, because design requirements for stall characteristics demand features promoting early wing root stall. However, the rudder on modern jet transports is very powerful, and excessive use can result in over-controlling, or even, in extreme cases, structural failure. At the low speeds normally associated with stalling, dynamic pressure is at a low value, and greater deflection will be required to achieve the same response as that found at a higher speed. The controls will also feel less responsive, as mentioned earlier in the lesson. If an accidental stall should occur, it is important that the recovery is effected before the process develops too far, with a large wing drop giving a high rate of descent or possibly leading to a spin. Moving a control surface alters the chord line and hence the angle of attack. An aircraft may have one wing which is less efficient than the other and stall slightly before it, causing a wing drop. Trying to lift a dropping wing with aileron will increase its angle of attack further, taking it deeper into the stall. At the same time, the upgoing aileron on the opposite wing will decrease its angle of attack, possibly unstalling that wing, which produces more lift and exacerbates the roll already made worse by the changes in effective angle of attack. The moral of this is that ailerons should be used with great caution when close to the stall. Swept-wing aircraft basic stalling requirements, however, are designed to enable safe use of the ailerons as far as stall recognition, with small amounts of rudder, if smoothly applied, to coordinate with the ailerons. Various means of achieving this capability are discussed later. The use of rudder has already been mentioned in the earlier section on stall recovery, with its attendant risks. A coarse application of rudder before the wings are unstalled to pick up a dropped wing, but inadvertently in the wrong sense, in the direction of roll, could put the aircraft into a spin. Even if the rudder were applied to oppose a wing drop, it would require a large rudder deflection, which could well cause a spin in the opposite direction. Taken with the aforementioned restrictions on the use of the ailerons, these factors would suggest that the ailerons and rudder should be kept neutral until the wings are unstalled, and only used when the aircraft has reached a safe speed margin above the stall. A formal standard of stall recognition is established to determine when the behaviour of the aeroplane gives the pilot a clear and distinctive indication of an acceptable nature that the aeroplane is stalled. These acceptable indications of a stall, occurring either individually or in combination, are 1. A nose-down pitch that cannot be readily arrested. 2. Buffeting of a magnitude and severity that is a strong and effective deterrent to further speed reduction. And 3. The control column reaches the aft stop, that is, full up elevator, and no further increase in pitch attitude occurs when the control is held fully aft for a short time before recovery is initiated. The following section of the series of lessons deals with stall speeds and warning and prevention devices.
This section of the lesson will tell you how the stall speeds quoted in aircraft flight manuals are determined and the parameters on which they are based. Aircraft need to fly at low speeds with high angles of attack during takeoff and landing in order to keep the required runway lengths to a reasonable minimum. But there must be an adequate safety margin allowed between the minimum speed for normal operations and the stalling speed. During the flight testing that takes place before type certification, prototype aircraft are stalled, and the stalling speeds established for inclusion in the flight manual. The stalling speed for small aircraft, those in the EASA category CS23, for normal, utility, aerobatic and commuter aircraft, is based on the stall speed in the landing configuration, VS0, and the speed for a given configuration, VS1. For large aircraft, in EASA category CS25, a reference stall speed, known as VSR, is used. VSR is a calibrated airspeed defined by the manufacturer, and may not be less than a 1G stall speed. It is expressed in formula form as being equal or greater than VCL max over the square root of NZW, where VCL max is the calibrated airspeed obtained when the load factor-corrected lift coefficient first reaches its maximum during the laid-down test manoeuvre. In addition, if the aircraft is fitted with a stick pusher, a stall prevention device described in the next section of the lesson, VCL max may not be less than the speed at which the device operates. NZW is the load factor normal to the flight path when the aircraft is at VCL max. For an aircraft without a stick pusher, the speed at which it reaches its CL max at 1G, in other words its 1G stalling speed, can be considered to be its VSR. For the purpose of the test, to determine VCL max, the aircraft is flown with the following conditions: 0 thrust at the stall speed, propeller pitch, RPM controls, if applicable, at the takeoff setting, landing gear and flaps set as appropriate to the performance standard being tested, the weight to be that applicable when VSR is being used as a factor to determine compliance with the required performance standard, the centre of gravity to be in the position that results in the highest value of VSR, and the aeroplane must be trimmed for straight flight at a speed determined by the manufacturer, between 1.13 VSR and 1.3 VSR. During the test, the aeroplane must be decelerated from the trim speed at no more than 1 knot per second. An additional condition, which applies when the aircraft is fitted with a stick pusher, is that the reference stall speed may not be less than 2 knots or 2%, whichever is the greater, above the speed at which the device operates. VSR will vary with each of the conditions specified. Factors which affect VSR are thrust in excess of 0, wing contamination, and load factor. One thing that does not affect indicated stall speeds, however, is density altitude. The EASA regulations and their equivalents outside Europe specify that there must be clear and distinctive warning of a stall, sufficiently in advance of the stall for it to be avoided, both in straight and turning flight, and with the landing gear and flaps in any normal position. The warning can be provided either through the inherent aerodynamic characteristics of the aircraft itself, such as buffet, or by means of a device that will give clearly distinguishable indications under expected flight conditions. However, a visual warning that requires the attention of the flight deck crew will not suffice on its own. There must be a tactile or audible warning as well. A warning device must provide a warning in each normal configuration. Regarding the speed at which a device operates to give adequate stall warning, known as VSW, it should begin no less than 5 knots, or 5% of CAS if greater, above the speed at which stall recognition would occur, and should continue to operate until the angle of attack is reduced to about the angle at which it began. Under the same conditions, but also in straight flight, at idling power, and with the C of G which gives the maximum VSR, there should be a minimum of 3 knots or 3% of CAS above VSR. The regulations also stipulate that the warning margin must be sufficient to allow the pilot to prevent a stall if recovery is initiated 1 second or more after the warning in a 1.5 G turn, decelerating at 2 knots per second, with gear and flaps in any normal position, and with power and trim set for straight flight at 1.3 VSR. Finally, stall warning must also be provided in each abnormal flap or slack configuration likely to be used in flight following system failures, including all configurations covered by flight manual procedures. It is possible that adequate stall warning will be provided by the airflow separating fairly early and causing buffet over the wing and tail plane, but this is often insufficient, and so a device which simulates or substitutes for aerodynamic buffet is usually fitted. Artificial stall warning on small aircraft is usually given by a buzzer or horn, but on modern large aircraft, a stick shaker is used in conjunction with lights and a noisemaker. The stick shaker is intended to represent the aircraft's natural buffet by replacing it with a tactile warning. The noisemaker is added in parallel to ensure that the warning is noticed if the pilot's hands are not on the controls. For example, if the autopilot is engaged. The device consists of a pair of electric motors, one on each control column, and rotating an eccentric weight to generate vibration. Artificial stall warning devices can receive their signals from a variety of detectors, all of which are activated by changes in angle of attack. The leading edge stall warning vane, or flapper switch, usually used on small and medium-sized aircraft, is positioned so that at normal angles of attack, the airflow holds it down. But as angle of attack increases, the stagnation point moves down and back around the leading edge, and the change in pressure raises the switch, making the contact. The alpha vane is mounted on the side of the fuselage and trails in the relative airflow. The fuselage effectively rotates around it, and the vane thus senses the angle of attack. The stick shaker is activated at the appropriate alpha value, Another fuselage-mounted device is the angle of attack probe, consisting of a lateral tube with slots or holes sensitive to changes in the relative airflow, which generates the necessary signals as alpha increases. All of these devices sense angle of attack, and therefore automatically take care of changes in aircraft mass. The alpha vane and probe can also compute the rate of change of alpha and give earlier warning in the case of faster rates of approach to the stall. The detectors are usually datum compensated for configuration changes and are always heated or equipped with an anti-icing facility. There are normally sensors on both sides of the fuselage to allow for any asymmetric airflow due to side slip. This section of the lessons on stalling deals with the characteristics of various wing forms and how they affect an aircraft's behavior at the stall. We shall start with a summary of the requirements for stall characteristics, laid down by the European Aviation Safety Agency, EASA, and the American Federal Aviation Regulations, or FAR. The rules specify, first, that it must be possible to produce and to correct roll and yaw by unreversed use of aileron and rudder controls up to the time the aeroplane is stalled, and that no abnormal nose-up pitching may occur. The longitudinal control force from the elevators must be positive up to and throughout the stall. In addition, it must be possible to promptly prevent stalling and to recover from a stall by normal use of the controls. For stalls with wings level, the roll occurring between the stall and the completion of the recovery may not exceed approximately 20 degrees. The rules for a stall in the turn are a bit more complex, as a wing drop or roll at the stall is potentially more likely. The action of the aeroplane after the stall may not be so violent or extreme as to make it difficult, with normal piloting skill, to effect a prompt recovery and regain control of the aeroplane. The maximum bank angle that occurs during recovery may not exceed approximately 60 degrees in the original direction of the turn, or 30 degrees in the opposite direction, for deceleration rates up to 1 knot per second. If the deceleration is more than 1 knot per second, these bank angles are increased to 90 and 60, respectively. You have learned that stalling is due to airflow separation, resulting in a loss of lift and an increase in drag that will cause the aircraft to lose height. This is generally true, but there are some aspects of aircraft behavior and handling at or near the stall which depend significantly on the wing's aerofoil section and plan form. The shape of an aerofoil section will influence the manner in which it stalls. Some sections will stall very suddenly, with a marked drop in lift, whilst others have a more gradual approach to the stall, with a less dramatic loss of lift. In general, an aeroplane should not stall too suddenly, and the pilot should have adequate warning of the approach of the stall by means of natural warnings, such as airframe buffet or decreasing control effectiveness. If, however, a particular wing design is likely to stall too abruptly, it will be necessary to provide some sort of artificial pre-stall warning, or even a stall prevention device. There are several features of an aerofoil section design that affect behavior near the stall. First, the radius of the leading edge. A large radius will give a much more gradual stall than a sharper, small radius leading edge. Likewise, a thick section, greater camber, particularly near the leading edge, and a forward point of maximum thickness and camber are all more conducive to a gradual, more gentle stall than the opposite characteristics. These features are more typical of a wing designed for efficient high-speed operation. With a sharper leading edge, a low thickness chord ratio, and an aft maximum thickness and camber. A comparison of the shapes of the two lift curves shows the difference between the profile's stalling characteristics. As well as the wing's aerofoil section, its shape or planform will also have an effect on how it stalls. On basic, conventional wing planforms, the separation that causes the stall will not occur simultaneously at all points across the wing. On a rectangular wing, separation tends to start at the wing root trailing edge and spread forward and out towards the tip. Since the reduction in lift occurs initially inboard near the C of G, even if it happens on one wing slightly before the other, there is little tendency for the aircraft to roll. The aircraft loses height, but remains more or less wings level. As the aircraft stalls, the centre of pressure moves aft, causing the nose to drop, thus reducing the angle of attack. This gives the aircraft a natural tendency towards a recovery from the stall. The separated airflow from the wing root passes over the fuselage and tail unit, and the aerodynamic buffet caused by it can provide a warning of the approaching stall. The ailerons, being located outside the separated flow, will tend to remain effective as the stalling sequence starts. All these factors give the most desirable kind of response to a stall, namely aileron effectiveness, nose drop, aerodynamic buffet, and absence of violent wing drop. Despite these advantages, for large jet transport aircraft, a rectangular wing planform would impose unacceptable bending moments and would be less efficient at higher speeds. Compared to a rectangular wing, a tapered wing creates lower bending moments for a given span and is more efficient. The airflow separation on a tapered wing happens first in the area of the wingtips, reducing lift on the outboard part of the wing. This is because the weak wingtip vortices allow separation earlier than the inboard part of the wing, where the stronger vortices from the wider chord reduce the effective angle of attack. If an actual basic tapered wing were allowed to stall in this way, the stall would create aileron buffet and perhaps a violent wing drop, which greatly increases the likelihood of entering a spin. In addition, there would be no buffet at the tailplane, no strong nose-down pitching moment, and very little, if any, aileron effectiveness. To counter these undesirable characteristics, a tapered wing must be modified using one or more of the aerodynamic features described next. The wing can be designed with a twist, which reduces the angle of incidence, the angle between the mean chord line and the fuselage datum line, towards the tip. This is known as washout, and decreases the angle of attack at the tip relative to the root, and the root will tend to stall first. Another method is to vary the aerofoil section across the span, so that the sections near the tip have greater thickness, greater camber, or both. The higher CL max of such sections delays the stall at the tips. Leading edge slots at the wingtips re-energize the boundary layer by increasing its kinetic energy. The result is an increased CL max, delaying separation at the tips and retaining aileron effectiveness. The function of slats and slots is fully described in the lesson on high lift devices. The stall pattern can be influenced by forcing it to start from the root. This could be managed by designing the wing with a smaller leading edge radius at the root, but this is less efficient overall. The desired result can be achieved by fitting small wedge-shaped strips, stall strips, to the leading edge, which promote separation at high angles of attack, but will not affect the efficiency of the wing at cruising speed. Vortex generators, another device that can re-energize the boundary layer, consist of rows of small thin blades about 2.5 centimeters high, set at a small angle, and projecting vertically into the airstream to produce vortices over the upper wing surface. They each generate a small vortex, which causes the free stream flow of high-energy air to mix with and add kinetic energy to the boundary layer, delaying separation. A swept wing will allow higher maximum speed, but has a greater tendency than a straight wing to stall first near the tips. This loss of lift at the tips moves the centre of pressure forward and inward, giving a destabilizing nose-up pitching moment. The lift is now concentrated inboard, and the maximum downwash impinges on the tailplane, adding to the nose-up moment. As soon as a swept wing begins to stall, both the forward CP movement and the increased downwash at the tailplane causes the nose to rise rapidly, further increasing the angle of attack. This is obviously undesirable and unacceptable behaviour at the stall, and can result in a complete loss of control in pitch from which it may be very difficult, if not impossible, to recover. This phenomenon is known as pitch up, and is a very dangerous characteristic of some high-speed swept-wing aircraft. The tendency of a swept back wing to tip stall is due to the induced spanwise flow of the boundary layer from root to tip, and there are several design features that can be incorporated to redress this effect, to give more acceptable stall properties. Wing fences are thin, upright metal strips, which generally extend from leading to trailing edge, and restrict the outward drift of the boundary layer. Vortilons are similar to wing fences, but are shorter and mounted under the wing leading edge. The support pylons of pod-mounted engines act in the same way, which is to create a small but intense vortex over the wing's upper surface at high angles of attack to form an aerodynamic wing fence. Finally, there is a feature rarely used on modern high-speed jet transports, but which did appear on earlier generation jets, such as the Comet airliner and the Hunter. The sawtooth leading edge, like the vortilon and pylon, also produces a vortex at high angles of attack to act as a wing fence. As you have learned in the previous part of this series of lessons on stalling, an unmodified swept wing will stall first near the tips. And since the tips are well aft of the centre of gravity, the loss of lift causes the nose to rise rapidly and further increase the angle of attack. This phenomenon of pitch up stalls more of the wing. Drag will increase rapidly, lift will reduce, and the aircraft will start to sink at a constant nose-high pitch attitude. This results in a rapid additional increase in angle of attack. Separated airflow from the stalled wing will immerse a high-set tailplane, or T-tail, in low-energy turbulent air, and elevator authority is greatly reduced, making it impossible for the pilot to reduce the angle of attack. The aircraft will become stabilized in what is known as the superstall, or deep stall. The two principal factors involved in the superstall are a swept-back wing and a high-mounted tailplane. But of the two, by far the more significant is the swept wing, with its tendency to stall at the tips, causing the pitch-up phenomenon. Aircraft such as the MD-80, Boeing 727, Fokker 28, and the BAC-111, the aircraft on which the phenomenon was discovered during its flight testing in 1963, all have swept wings and T-tails. They also have rear fuselage-mounted engines, which are the reason for the T-tail. But apart from the possibility of the engines causing some turbulence and blanking of the airflow once the aircraft is already stalled, they do not in themselves contribute to the stall. Several devices and design features that can delay the tip stall by various means were described in the last lesson. Methods of reducing the span-wise movement of the boundary layer include wing fences, vortilons, engine pylons, and sawtooth leading edges. Vortex generators are a frequently used design feature that not only delay tip stall, but also improve stalling characteristics by maintaining aileron effectiveness down to lower speeds. The wing root can be made to stall before the tips by changing the aerofoil section at the root, by fitting stall strips, or by fitting Kruger flaps on the inboard sections of the wing, alongside the more efficient variable camber leading edge flaps. Both of these types of flap are described in the lessons on high lift devices. An aircraft which exhibits, or is likely to exhibit, superstall characteristics must be fitted with a device that will prevent it from ever stalling. The device is the stick pusher, developed after the loss of the 111 previously mentioned. Once a superstall commences, its progression is too fast for human response, and the aircraft cannot be unstalled. The stick pusher is incorporated in the elevator control system, and, as its name implies, physically pushes the control column forward at a certain angle of attack before the critical angle, and reduces the angle before a stall can occur. The push force is typically about 80 pounds, which is regarded as being high enough to be effective, but not too high to hold in the event of a runaway. A cutout is included to dump the system in the event of a malfunction. But, once dumped, the system can't normally be reset in flight. In normal operation, once the stick pusher has operated, it will disengage automatically as the angle of attack reduces below a preset value. In an earlier lesson, you learned about the reference stall speed, VSR, the calibrated airspeed at which a large aircraft in the EASA category CS-25 stalls. You also learned that stalling is caused by exceeding the critical angle of attack. Stalling has nothing to do with the speed of the aircraft. The critical angle of attack can be exceeded at any speed. It is worth noting here that to do so in the upper end of an aircraft speed range is likely to exceed its structural limitation, or G limit. However, it has been shown that if an aircraft is flown straight and level, and the speed reduced at a rate of not more than 1 knot per second, then it is possible to identify the CAS at which it stalls, which will be a 1G stalling speed. This reference stall speed is the speed on which are based the recommended takeoff, maneuver, approach and landing speeds, which will give an adequate safety margin above the stall during normal operations. These are calculated as proportions of VSR: 1.05, 1.1, 1.2, 1.3 VSR, etc. There are several factors that can affect the value of VSR. They are weight, maneuvering the aircraft, increasing the load factor, configuration changes, affecting maximum lift coefficient and pitching moment, engine thrust or propeller slipstream, Mach number, wing contamination, and heavy rain. We shall now examine how these changes work. In straight and level flight, the weight of the aircraft is balanced by the lift. So the load factor, which is lift over weight, is 1. Whilst N in brackets is the correct symbol for load factor, the relationship between lift and weight has for years been popularly known as G. 1G corresponds to the force normally acting on us, that is, gravity. If more lift is generated than weight, the load factor will be greater than 1. The force acting on the aircraft and everything in it, including of course the pilot, will be more than normal gravity. If lift equals weight, the load factor will be 1, as you have seen. And from the lift formula, lift equals half rho v squared times CL times S, it can be seen that lift will change whenever any of the other factors in the formula change. Taking density, rho, and wing area, S, to be constant for this example, consider what would happen if thrust is reduced. The speed, v, would reduce because of drag. And from the formula, you can see that lift would decrease. So, to keep lift constant and maintain 1g flight at a reduced speed, CL must be increased by flying at a higher angle of attack. Any further reduction in speed would need a further rise in angle of attack, with each succeeding lower CAS corresponding to a greater angle of attack. Eventually, at a certain CAS, the wing reaches its critical angle and CL max, beyond which any further rise in angle of attack will precipitate a stall. We can transpose and adapt the lift formula to give us a formula for a 1g stalling speed, which equals the square root of lift over half rho times CL max times S. Note that density altitude does not affect indicated stall speed. At CL max for 1g flight, a change in weight requires a change in lift, and it can be seen from the 1g stall speed formula that, for instance, an increase in weight, and therefore lift, will increase Vs 1g. The relationship between basic stalling speeds at two different weights can be obtained from the following formula. The new speed equals the old speed multiplied by the square root of the new weight as a proportion of the old weight, or the square root of new over old. The angle of attack at which the stall occurs will not be affected by the weight. This is provided that the appropriate value of CL max is not affected by speed, which will only happen at speeds above Mach 0.4. To maintain a given angle of attack, say critical angle or alpha CL max, in level flight, if the weight and therefore the lift required is changed, it is necessary to change the dynamic pressure. In other words, the CAS. For example, if an aircraft stalls at 150 knots at a weight of 588,600 newtons, what is the 1g stalling speed at 470,880 newtons? Using the formula, the new to old weight proportion is 470,880 over 588,600, which is 0.8. The square root of this is 0.894, which multiplied by 150 is 134. So the new stalling speed is 134 knots. A useful rule of thumb that can be derived from such calculations is that halving the percentage change in weight, either up or down, will give the approximate percentage change in stalling speed. In the example, a 20% weight reduction gives about a 10% speed reduction. This rule of thumb can be very useful, not least as a gross error check during exams. As you know, in straight and level flight, lift balances weight. But in a level turn, for example at 45 degrees, as shown here, the weight will still be acting vertically downwards, and the wings need to produce a vertical lift vector to balance it. However, as you can see from the diagram, the lift vector is tilted at 45 degrees, and if it is resolved into vertical and horizontal vectors, it is insufficient to balance the weight. The lift must therefore be increased, so that its vertical component balances the weight, and the relationship between the vertical force and the lift required can be found using trigonometry, using the symbol phi as the bank angle and taking the vertical force required as 1, the adjacent, lift being the hypotenuse. Cosine equals adjacent over hypotenuse, and if we transpose this formula, we arrive at L equals 1 over cos phi. Cos phi in this case, at 45 degrees, is 0.707. 1 divided by 0.707 is 1.41. So, for a level 45-degree bank turn, the lift must be 1.41 times that of straight flight, or, to put it another way, increased by 41%. You learned in the previous part of this lesson on stalling that to bank an aircraft and maintain level flight, lift must be greater than weight. The additional lift required is gained by increasing the angle of attack. The measure of the relationship between lift and weight is known as the load factor. Increasing lift in a turn increases the load factor. So as bank angle increases, load factor increases. In straight and level flight at CL max, it would be impossible to turn and maintain altitude, as trying to increase lift would stall the aircraft. If a turn were to be started at a speed above the stalling speed, then at a certain angle of bank, CL would reach its maximum, and the aircraft would stall at a speed higher than the 1g stalling speed. The increase of lift in a level turn is a function of the bank angle. Using the following formula, it is possible to calculate stalling speed as a function of bank angle or load factor. The turning stall speed will equal the 1g stall speed multiplied by the square root of 1 over the cosine of the bank angle. As an example, if the 1g stalling speed is 150 knots, what would be the stalling speed at 45 degrees of bank? The working on the screen shows the result to be 178 knots CAS. Using the same sequence for 60 degrees of bank, a 2g turn in level flight gives a stalling speed of 212 knots CAS, which is 41% greater than the 1g stalling speed. The 45-degree stalling speed is 19% higher, and, since these figures are ratios, they will hold good for any aircraft. As bank angle is increased, the stalling speed will rise exponentially. Whilst operating at high CLs, particularly during takeoff and landing, only moderate angles of bank should be used when manoeuvring the aircraft. For modern high-speed jet transports, the maximum bank that should be used is 30 degrees, except in an emergency. The normal maximum under instrument flight rules, IFR, is 25 degrees, or the angle of bank for a rate 1 turn, 3 degrees per second, if this is less. At higher altitudes, the normal maximum would be about 10 to 15 degrees. In brief, load factor does not affect the stalling angle of attack, but the stalling speed increases in proportion with the square root of the load factor, in the same way as it does with a weight increase, since g is an effective increase in weight. Modern high-speed jet transport aircraft have swept wings with relatively low thickness chord ratios. For example, the Airbus A310 has a ratio of 12%. The overall value of CLmax for these wings is fairly low, and the clean stalling speed therefore correspondingly high. To reduce the takeoff and landing speeds and distances, various high-lift devices are used, increasing the value of CLmax. In addition to lowering the stalling speed, these devices, which principally comprise leading edge flaps and slats and trailing edge flaps, will usually alter the stall characteristics. From the 1G stall formula, it can be seen that an increase in CLmax will reduce the stalling speed. It is possible, with modern high-lift devices, to increase the CLmax by up to 100%. High-lift devices, which are fully described in the next set of lessons, decrease stall speeds and so minimum flight speed, enabling shorter takeoff and landing runs. This is their primary, and for airliners, their sole purpose. The EASA regulation 25.103b states that VCLmax is to be determined with the CG position that results in the highest value of reference stall speed. If the CG is in front of the centre of pressure, the CP, giving a nose-down pitching moment, as is usual, the tail plane must provide a download to maintain equilibrium, but the wing must produce more lift to balance the increased force of weight plus tail downforce. If the CG is further forward, it will produce a greater pitching moment, which must be balanced by a greater downforce from the tail plane. This in turn requires more lift to counter the downforce. From the 1G stall formula, you can see that greater lift gives a higher stalling speed, with the conclusion that forward movement of the CG increases the stalling speed. With landing gear up, the thrust-drag couple is not great, but when the gear is lowered, the profile drag below the CG is increased, which gives a nose-down pitching moment. This must be balanced by increasing the downforce of the tail plane, which in turn needs more lift to balance it. Any change of CG caused by a change in longitudinal position of the gear as it extends will have very little effect. The change in profile drag is far more significant, and the conclusion is that lowering the landing gear increases stall speed. Regarding engine thrust, the EASA regulation 25.103b states that VCLmax is to be determined with zero thrust at stall speed, and it is assumed that the aircraft is supported entirely by lift. If thrust is applied close to the stall, the nose-high attitude will produce a vertical component of thrust, which helps to support the weight, and less lift is required. Propellers will create an extra effect because of the slipstream. The most important factors in this situation are engine type, propeller or jet, thrust-to-weight ratio, and the inclination of the thrust vector at CLmax. With propeller-driven aircraft, the slipstream velocity behind the propellers is greater than the free stream flow, depending on the thrust. Thus, at low IAS and high power, the dynamic pressure within the slipstream is higher than that outside it, and generates more lift than at zero thrust. The lift at any given IAS or angle of attack will be significantly affected. For instance, if the aircraft is in the landing flare and power is reduced suddenly, the resulting loss of lift could cause a heavy landing. On the other hand, a potentially heavy landing can be prevented with a judicious burst of power. A typical jet aircraft does not experience the induced flow velocities of prop-driven aircraft, the only significant factor being the vertical component of thrust. This means that, since less lift is required to support the aircraft, there is lift in hand to decelerate to a lower speed. The effect on stall speed at high thrust can be large, but since there is no induced flow, the angle of attack at the stall will be very similar to that of a power-off stall. The conclusion for both categories of aircraft is that power-on stall speed is less than power-off. As an aircraft flies faster, the streamline pattern around the wings begins to change. Above about Mach 0.4, 4/10 of the speed of sound, the phenomenon of compressibility becomes significant. Mach 0.4 equates to around 300 miles per hour. Pressure waves generated by the wing's passage through the air propagate ahead of it at the speed of sound, and cause the air ahead of the wing to curve upward, or upwash, towards the low-pressure upper surface. At low speeds, the streamline pattern is affected well ahead of the wing, and the air has a fair distance in which to upwash. As speed increases, the wing gets closer to its leading pressure wave, and the air has less space in which to upwash, and so approaches the wing more steeply. The change in streamline pattern accentuates the adverse pressure gradient near the leading edge, and flow separation occurs at a lower angle of attack. Above Mach 0.4, CLmax decreases, as shown in the diagram on screen. According to the 1G stall formula, a drop in CLmax will increase the stalling speed. At a constant EAS, TAS will increase. Also, outside air temperature, or OAT, drops with increasing altitude, causing the local speed of sound to decrease. Mach number is proportional to TAS and inversely proportional to the local speed of sound, or A. As an equation, M equals TAS over A. At a constant EAS, Mach number will increase with altitude. The graph, now on the screen, shows the variation of stalling speed with altitude at a constant load factor. This type of curve is called the stalling boundary for the given load factor, in which altitude is plotted against EAS. At the load factor shown, 1G, the aircraft cannot fly to the left of this boundary. You can see that at lower altitudes, stall speed does not vary. This is because the Mach number at the stall is less than 0.4, too low for compressibility to have any effect. By about 30,000 feet, the Mach number has risen to the extent the compressibility is significant, and the rise in stalling speed is apparent. The conclusion here, then, is that stall speed will initially stay constant with altitude, but will increase with compressibility above about Mach 0.4. The various factors affecting stalling speed considered so far have been pretty much known quantities, explored during flight testing and promulgated in aircraft manuals. But contamination on the wing, particularly ice, frost or snow, can drastically affect the wing profile and affect the nature of the boundary layer, giving unknown and untested stalling speeds and characteristics. Let's consider the effects of these three main types of contamination, starting with ice. Ice formation on the wing will produce large changes in wing contour, particularly on the leading edge, leading to severe local adverse pressure gradients. High surface friction will considerably reduce boundary layer kinetic energy. These hazards cause a large drop in CLmax, and can increase the stall speed by up to 30%, without any change in angle of attack. The extra weight of the ice will also increase the stalling speed, but the reduction of CL max is by far the greater effect. The effect of frost is more subtle. An accumulation of a hard layer of frost on the wing upper surface gives a texture of considerable roughness. Tests have shown that leading edge and upper surface contamination, with a thickness and roughness comparable to coarse sandpaper, can reduce lift by as much as 30%, increase stalling speed by 10 to 15%, and increase drag by 40%. Whilst the basic shape and aerodynamic contour of the wing are unchanged, the increase in skin friction reduces the kinetic energy of the boundary layer, and separation will occur at a smaller angle of attack and at lower CLs than a clean wing. The effect of snow can be similar to frost in that it will increase surface roughness. In addition, any deposit more than a light dusting can add significant weight and alter the aerodynamic profile. If there is any snow on the aircraft, it must be removed before flight. The idea that snow will blow off the wings during taxi or takeoff is a complete misconception, as has been tragically proved on occasions. Notably, the crash of a Boeing 737 into the Potomac River, Washington, in January 1982, which killed 78 people, and in which snow on the wings and tailplane was one of several contributory factors. The pilot in command is legally required to ensure that his aeroplane is aerodynamically clean at takeoff. It is vitally important that the time limitations, the holdover time, on any de-icing or anti-icing process are adhered to. If this time is exceeded before takeoff, the aircraft must be de-iced again. Guidance is available to pilots in the CAA's Aeronautical Information Circular number 106 of 2004, Pink 74, issued 11th of November 2004, entitled Frost, Snow and Ice on Aircraft. AICs are reissued from time to time, so you should check for updates. To summarize the effects of contamination, we can say that while the reduction in CL max with frost is not usually as much as with ice formation, its effect is probably more than may be expected from the comparatively smaller change in profile. The effect on the boundary layer's kinetic energy is a major factor influencing the separation of the airflow. The increase in stalling speed due to ice formation is difficult to quantify, as accretion rates and patterns and ice types vary greatly. Frost is a significant hazard, but will not form on upper surfaces in flight, although it does form under fuel tanks in a descent from a sub-zero high level into warmer, moist air, but this is usually of short duration. Snow, particularly wet snow, at temperatures not far below zero, presents a very serious hazard. All will affect stalling speed. The moral is that any contamination is too much, and none must be allowed to remain on any surface before flight. De-icing is essential. As mentioned earlier, there have been cases involving loss of control in icing conditions due to unexpected stalling at speeds considerably higher than the normal stalling speeds, possibly accompanied by sudden rolling. Control can be lost as a result of a contamination-induced stall, the onset of which can be so insidious as to be difficult to detect until it is too late. The following advice may help you to recognize and avoid these gradual stalls, or recover from one if it does occur. First, a loss of performance in icing conditions may indicate a serious ice buildup, possibly unseen, which is causing a gradual loss of lift and increase in drag. Such a build-up can cause the aircraft to stall at about 30% above normal stall speeds. The longitudinal characteristics of an icing-induced stall may be so unobtrusive that the pilot is unaware that it has occurred. A stall warning system, normally triggered by angle of attack, may not be activated by a low alpha stall, but buffet may assist in stall recognition. The first clue may be a roll control problem, manifested either as a divergent roll oscillation or a wing drop. A combination of roll oscillation and onset of high drag can cause the aeroplane to enter a high rate of descent unless prompt recovery action is taken. If a roll control problem develops in icing conditions, the pilot should suspect an icing-induced stall and take immediate recovery action. The anti-icing system, if fitted, should have been on prior to entering icing conditions, in accordance with operating procedures. If not, it must be activated immediately, and consideration given to leaving icing conditions by track or level adjustment. The tailplane is an aerofoil, and because it is thinner than the wing, will tend to accumulate ice sooner and more quickly than the wing, but with similar effects. However, the tailplane, often an inverted aerofoil, usually produces a downforce. So if it stalls, the loss of downforce will cause a pitch down, with at least a temporary loss of control. Stalling of an ice-contaminated tailplane could be precipitated by the lowering of the flaps, which increases the downwash over the tailplane and consequently alters its effective angle of attack and takes it beyond the critical angle in a negative sense. It should be borne in mind that the tailplane will usually be producing downforce, which is lost if the tailplane stalls. In the event of a sudden pitch down when lowering flaps, the initial recovery action is to retract the flaps, reducing the downwash. Heavy rain, whilst not as hazardous as its freezing cousins, ice, frost and snow, can also have a detrimental effect on stalling speeds and drag. The rain will form a film on the aircraft's surface, increasing the weight, and therefore the stalling speed slightly. As the film of water runs back over the wing, it will distort the profile, roughen the surface, and distort the airflow over the whole aircraft. CL max will decrease, increasing the stalling speed. The surface film will increase interference, profile, and form drag. The approximate overall increments are: for light rain, 5%, moderate rain, 20%, and for heavy rain, up to 30%. This extra drag increases the thrust required. A further consideration, which does not in itself affect stalling speed, is the impact of heavy rain. Lost momentum will require more thrust to maintain speed, and the rainfall will tend to push the aircraft downwards, in much the same way as microburst wind shear, with which it may well be associated. With the conventional layout of the rear-mounted tailplane, the wing stalls first, and longitudinal stability and control are maintained. On the tail-first canard layout, if the wing, the main plane, stalls before the foreplane, then stability will be lost. But if the foreplane stalls first, then control will be lost, and the maximum value of CL is reduced, since both foreplane and main plane are lifting surfaces. In the next lesson in this series on stalling, we return to conventional aircraft and the topic of spinning. When an aircraft is stalled, either inadvertently or deliberately, the motion of the aircraft may, in certain circumstances, develop into a spin. The important general characteristics of a spin are as follows. The aircraft is descending in a steep helical path about a vertical spin axis. The angle of attack of both wings is well above the critical angle. The aircraft has a high rate of rotation around the spin axis. It will also have a high rate of descent. The speed will be low, but possibly slightly above the basic stalling speed, and may be oscillatory. If the speed is relatively high, and possibly also increasing, the aircraft is not in a spin, but a spiral descent or spiral dive. Viewed from above, the aircraft executes a circular path about the spin axis, and the radius of the helix is usually less than half a wingspan. The aircraft may be spinning either erect or inverted, although inadvertent inverted spins are rare, as a fair amount of negative G is involved. The aircraft will be rolling, yawing, and pitching simultaneously. The spin is one of the most complex of all flight maneuvers. It can be defined as an aggravated stall resulting in auto-rotation, meaning that the rotation, which can start without the use of the appropriate controls, for example, a roll or wing drop without aileron movement, is self-sustaining aerodynamically, and will continue until action is taken to correct it. During the spin, the wings are unequally stalled. A spin cannot occur unless the wings are stalled, but is most likely to happen when one wing stalls before the other. That wing will drop, and the aircraft will yaw in the direction of the lower wing. The change in effective relative airflow from the roll deepens the stall on the downgoing wing and lessens it on the upgoing wing. The cause of an inadvertent spin is exceeding the critical angle of attack with an inappropriate use of rudder. In other words, flying out of balance. If prompt recovery action is not taken, an incipient spin may well develop into a full spin. Coordinated use of the flying controls is always important, but especially so during flight at low speed and high angles of attack. Although most pilots are able to maintain coordinated flight during routine maneuvers, this ability is often degraded when attention is divided by distraction from the primary task of flying the aeroplane. Distraction could be caused by even a minor technical problem within the aircraft, concentration on external events or features, obstacle clearance, or the proximity of another aircraft. A spin may also develop if forces on the aircraft are unbalanced in other ways. For example, yaw forces following engine failure in a multi-engine aircraft, or a lateral imbalance due to uneven fuel usage. There are 3 phases or stages of a spin. The first is the incipient spin. Incipient from the Latin for start or begin, and exists from the time the aeroplane stalls and auto-rotation starts until the spin is fully developed. This phase can be regarded as up to the end of the first full turn. A full or fully developed spin exists from the time the angular rotation rates, airspeed and rate of descent are stabilized from one turn to the next. The third phase, the spin recovery, starts when the anti-spin forces overcome the pro-spin forces. As already mentioned, if at the critical angle more lift is lost from one wing than from the other, it will drop. The relative airflow will now be inclined upwards, increasing its effective angle of attack. As the aircraft rolls, the upgoing wing has a reduced angle of attack and remains less stalled than the other wing. The asymmetry of lift increases as the aircraft yaws towards the low wing, accelerating the outside wing and decelerating the inside one. The aircraft is now said to be in the self-sustaining state of autorotation. As with any stall, the nose will drop, and as inertial forces take effect, the spin usually stabilizes at a steady rate of rotation and descent. It is vitally important that recovery from an unintentional spin is initiated as soon as the spin is recognized, since many aeroplanes will not easily recover from a full spin, taking several turns before recovery action takes effect. Recovery from an incipient spin is simpler, quicker, and will incur a much smaller height loss than a full spin recovery. It usually involves centering all controls promptly, then regaining straight and level flight when rotation stops. Every aeroplane type has its own spin characteristics, and any individual aeroplane spin behavior will depend on loading, power, configuration, and other factors. Both the total mass of an aeroplane and the distribution of that mass will influence spin characteristics. Greater mass generally means slower initial spin rates, but these may increase if the spin is allowed to progress. The higher angular momentum will extend the time and height necessary for recovery in a heavy or heavily loaded aeroplane. Within the loading of the aircraft, the center of gravity is more significant than the mass itself, as it affects the aircraft's resistance to spinning, as well as its behavior in the spin. A CG near the forward limit makes the aircraft more stable, with higher control forces, which make it less likely for the pilot to make large, abrupt control movements. The aircraft will be easier to trim, but its stalling speed will be higher than with a neutral or aft CG. A CG towards the aft limit decreases longitudinal static stability and reduces pitch control forces, which tends to make the aircraft easier to stall. If a spin is entered with an aft CG, the spin attitude will be flatter than with a neutral or forward CG. If the CG is at or outside the aft limit, if power is left on, or even if, in some aircraft types, the recovery actions are incorrect or incomplete, the spin may become flat. A flat spin is characterized by a near-level pitch and roll attitude, with the spin axis close to the CG. Although the height lost in each turn of the spin may thus be less than in a normal spin, the very high yaw rate, often more than 1 turn per second, results in a high rate of descent. The relative airflow in a flat spin is nearly straight up, keeping the wings at very high angles of attack. But, more importantly, the upward flow over the tail unit may render the elevator and rudder ineffective, making recovery impossible. Recovery from a stall is achieved by reducing the angle of attack to restore smooth airflow over the wings. A spin recovery has the extra element of needing to stop the rotation. The very complex aerodynamics of a spin may dictate significantly different recovery procedures for different aircraft types. So there can be no universal spin recovery procedure for all aeroplanes, but there will be elements common to most. The recommended recovery for some types involves simply reducing power to idle and centralizing all flying controls or relaxing any pressure applied to them. At the other extreme, some designs dictate that a precise set or sequence of control movements is carried out, timed to coincide with certain points in the rotation and for several turns. That said, there is a general recovery procedure which would be effective for most conventional aircraft in an erect spin, although the manufacturer's procedures, published in a specific type's flight manual, should always be followed. First, move the throttle or throttles to idle. This minimizes height loss and reduces the likelihood of a flat spin developing. It also eliminates asymmetric thrust in multi-engine aircraft and reduces engine torque and propeller gyroscopic effects, which could aggravate the spin. Secondly, although this action can be done simultaneously with the first, set the ailerons to neutral. Aileron deflection can contribute to abnormal spin characteristics. Apply full rudder to oppose the spin to stop the yaw. The direction of spin is best determined from the turn needle or coordinator. The slip ball should not be used, as it is not a reliable indicator of yaw direction, possibly being affected by its position in the cockpit. Once full rudder has been applied and held, the control column should be steadily moved forward until rotation ceases. The forward movement should not be commenced simultaneously with the rudder, in order to allow the anti-yaw force of the rudder to take effect with minimum blanking from the elevator's downward movement. As soon as rotation stops, centralize all controls, particularly the rudder, as if full rudder to oppose the spin is held, the aircraft may enter a spin in the other direction. With some aircraft, the spin may speed up slightly before stopping. Recover from the ensuing dive with back pressure that increases progressively with speed, remembering that too slow a pull-out could result in excess height loss or exceeding aircraft speed limitations, or both, and too abrupt a recovery could result in a further stall at a higher speed. Reset the power as necessary to resume normal flight, taking care to stay in limits. There are some circumstances under which stalls can occur without the normal warning signs and with possibly unexpected or different symptoms from a straightforward simple stall. A crossed control stall can occur when flying at high angles of attack with rudder applied in the opposite sense to the ailerons, over-applied, or even just applied when not required. In other words, in any out-of-balance state. This state will be confirmed by the displacement of the ball in the slip indicator. Crossed control stalls can occur with little or no warning. One wing will stall well before the other, and a quite sudden wing drop can occur. The instinctive reaction to correct the wing drop with aileron must be resisted, as it could make the asymmetry of lift worse. At all times, and especially at low airspeeds in combination with high angles of attack, the rudder should be used to keep the ball in the middle to maintain balanced, coordinated flight. An accelerated stall is caused by an abrupt or excessive pitching up demand on the flying controls. It can occur during a sudden change in flight path during maneuvers demanding high pitch rates, such as steep turns or recovery from a dive. It is called an accelerated stall, or G-stall, because it occurs at a load factor greater than 1G. An accelerated stall is usually more sudden than a 1G stall, the first sign usually being heavy airframe buffet, and may be unexpected because of the relatively high airspeed. For example, in a 2G turn, stalling speed will be 1.41 times the 1G speed, and in a 4G dive pull-out, double the 1G speed, the increase being, as you have learned, proportional to the square root of the load factor. The so-called secondary stall is actually no different aerodynamically from an accelerated or G stall, being a stall at a load factor greater than 1. It is known as a secondary stall when it is triggered while attempting to recover from a stall, usually by trying to hasten the recovery. This can happen either from an insufficient decrease of the angle of attack, or by not allowing the aircraft to accelerate to flying speed before pulling up to regain lost height. To avoid or correct this situation, the solution is simply to maintain full or maximum power and relax any back pressure, or move the control column forward slightly, and allow the aircraft to regain a safe flying speed before regaining lost height. During airline type conversion training on large aircraft, full stalls are not practiced except in flight simulators. To familiarize pilots with the characteristics of their aircraft, only the approach to the stall, down to stick shaker activation, is carried out. For jet aircraft with swept wings, there are no special considerations during the approach to the stall. At the stick shaker, either power on or power off, the aircraft can be recovered by moving the control column smoothly forward until the shaker stops, simultaneously increasing power to the maximum recommended to minimize height loss, and preventing or correcting any wing drop with roll control and rudder to balance, then raising gear and flaps at appropriate speeds if down. For multiprop aircraft, the recovery sequence is almost identical, except that the wings should be levelled with coordinated use of rudder and aileron. The reason for this difference is that the propeller-driven aircraft will experience rapid changes in slipstream and propeller torque during the power increase, and it is essential that the pilot coordinates his control movement during the power change to keep the aircraft in balance. That is, with the ball in the middle. Prevention of yaw is particularly important during stall and recovery. For single-engine propeller aircraft, an incipient stall recovery at the stall warning involves moving the control column smoothly forward to unstall the wings, which is judged by the absence of the stall warner or any signs of an incipient stall, and, at the same time, increasing the power to maximum. Yaw should be prevented with rudder, and the wings levelled with aileron once unstalled, then height regained. A power-on stall and recovery pose extra complications. At the nose-high attitude associated with a power-on stall, there will be appreciable turning effects from the propeller. These will be discussed in the lessons on propellers. Pilots of single-engine aircraft, when flying at low speeds, must be prepared to compensate for the effects of the propeller and of power changes in all three axes, and of gyroscopic forces from the propeller if the nose drops during a stall. It is worth reiterating that any tendency to yaw must be stopped to avoid a spin. This would be particularly true in a high-power, low-speed situation, such as after takeoff or during a go-around, where the pilot's attention could be diverted from the speed and balance. If a stall does occur in this situation, correct and immediate recovery action should be taken at the first sign. Forward movement of the control column, ailerons neutral, and rudder to prevent yaw. A stall that develops into a spin at low level could be irrecoverable. When an aircraft is in a level coordinated turn at a constant angle of bank, the inside wing is moving through the air at a slightly lower speed than the outside wing, and consequently generates less lift. If the ailerons are exactly neutral, the aircraft would have a tendency to roll in the direction of bank, or over bank. If the pilot holds the required attitude and bank angle, he will actually be holding a small aileron deflection to oppose the roll, sometimes known as holding off bank. The deflection, although probably undetectable from control column position, is greater for low speeds than for high speeds. The inner or lower wing will have a slightly greater angle of attack than the outer wing because of the difference in aileron position, and may reach the critical angle first. In a climbing turn, the airspeed is likely to be lower, but with full or high power, and in a single propeller aircraft, the rolling and yawing forces from the propeller and its slipstream will add to the control deflections required for balanced flight, and may complicate the aircraft's reactions in a stall. In a descending turn, the power is likely to be at a low or idle setting. In the event of a stall, the pilot would need to counteract the forces arising around all three axes, as the power is increased through most or all of its range during a stall recovery. As with any situation, it is important for the controls to be coordinated, and particularly so where the aircraft is at or close to the stall, to prevent an inadvertent spin. Regardless of configuration, attitude, speed or power setting, the correct action to be taken by the pilot in the event of a stall warning is to carry out the stall recovery technique applicable to the type of aircraft. Invariably, this will include decreasing the angle of attack below the critical angle to unstall the wings, simultaneously applying maximum permissible power to accelerate and minimize height loss and prevent yaw from developing. At any stage of flight, it is important to fly in balance, but when close to the stall, it is essential to keep control movements coordinated to avoid an inadvertent spin. Remember, keep the ball in the middle. When explaining the basic principles of flight, we consider air to be incompressible at speeds less than 4/10 of the speed of sound, or Mach 0.4. Or, in other words, that pressure is considered to have no effect on air density. At speeds above Mach 0.4, which is about 300 miles per hour, it is no longer practical to make that assumption, because density changes in the airflow around the aircraft begin to affect the behavior of the aircraft. At high altitude, a large high-speed jet transport will be cruising at a speed marginally above its critical Mach number, and will have a small shock wave on the wing. If the aircraft speed is increased, the shock wave will rapidly grow larger, causing the static pressure to increase sharply in the vicinity of the shock wave. The locally increased adverse pressure gradient will cause the boundary layer to separate immediately behind the shock wave. This is called a shock stall. The separated airflow will engulf the tailplane in a very turbulent wake, which will cause severe airframe buffeting, obviously an undesirable phenomenon. This high-speed buffet, or shock stall, can seriously damage the aircraft structure. So an artificial warning device is installed to alert the flight deck crew if the aircraft exceeds its operational speed limit by even a small amount. The limits are VMO, the maximum operating indicated airspeed, and the equivalent Mach number, MMO. The high-speed warning is oral, either a clacker, horn, or siren, and is designed to be easily distinguishable from the low-speed stick shaker triggered by high angle of attack. The warning will not be cancelled until the speed is reduced below the speed at which it is triggered. You have learned that approaching the critical angle of attack can cause airframe buffeting, low-speed buffet. And we have now shown that flying too fast can also cause buffet, high-speed buffet. Any airframe buffet is undesirable, and, if allowed to become prolonged, can lead to structural damage, as well as upsetting the passengers. At high cruising levels, around 36 to 42,000 feet, the margin between the normal stall warning stick shaker and the high-speed warning may be as little as 15 knots. High speeds are operationally necessary, and designers are constantly trying to find ways of increasing maximum speeds without incurring any undesirable flight characteristics. The limits mentioned just now, VMO and MMO, are investigated and established during certification flight testing of new types. These maxima give a speed margin into which an aircraft can momentarily overspeed and be recovered by the pilot before any undesirable effects occur. This lesson concludes the series on stalling. The problems incurred by shock stall, such as tuck, loss of control effectiveness and instability, are covered in detail in the lessons on high-speed flight. Aircraft are fitted with flaps to reduce the takeoff and landing run. The reduction in takeoff and landing run is achieved by reducing the minimum operating speed. The minimum operating speed typically provides a 30% margin of safety above stall speed. Here you can see the transpose lift formula you were introduced to in previous lessons. Please note the typical stall speed for a jet transport aircraft of 131 knots, indicated airspeed, and the associated minimum operating speed that is 30% higher. You can see that increasing the maximum lift coefficient, CLmax, gives a decrease in stall speed, and therefore a decrease in minimum operating speed. CLmax is increased by temporarily increasing the camber of the wing with flaps. Only trailing edge flaps are illustrated for the moment. Flaps are a hinged portion of the trailing or leading edge of the wing that can be deflected downwards and so produce an increase in camber. For low-speed aircraft, the flaps will be on the trailing edge only, but on high-speed jet transport aircraft, there will be flaps on the trailing edge and the leading edge. We will consider the common types of trailing edge flap first. The plane flap is usually fitted to light aircraft and is of simple construction. The plane flap gives a good increase in CLmax, but with fairly high drag. Here we show a 10-degree flap selection. 10 degrees of flap will be ideal for takeoff, because CLmax will be increased a moderate amount, but drag will increase only slightly. Prior to landing, flaps should be selected in small increments, and 10 degrees will be the initial selection. It should be noted that any amount of flap will increase drag. The significance of this fact will be explained later. Further flap selection will continue to increase CLmax. Selecting flap angles of 20, 30 or 40 degrees will continue to increase CLmax, but also give a significant increase in drag. So the larger angles are usually used for the approach to landing, when the extra drag is an advantage. The next type of trailing edge flap we'll consider is the split flap. The difference from the plane flap is that the split flap only moves the lower surface of the trailing edge. The next type of trailing edge flap we'll consider is the slotted flap. When the slotted flap is lowered, a slot is opened between the leading edge of the flap and the trailing edge of the wing. The slot directs high-energy airflow from the bottom surface of the wing onto the upper surface of the flap. This increases the kinetic energy in the boundary layer over the flap. Therefore, the slotted flap can be lowered to a larger angle before airflow separation begins. This allows a greater increase in CLmax with much less drag than is possible with either the plane or the split flap. A slotted flap can have more than one slot. Double or triple slotted flaps are usually fitted to larger aircraft, which can offset the higher weight and greater complexity against the increased efficiency. The most efficient type of trailing edge flap is the Fowler flap. Fowler flaps are fitted to both large and small jet transport aircraft. When flaps 1 is selected, the first movement is rearward, which increases the wing area. You can see that increasing the wing area also decreases the stall speed and the minimum operating speed. Flaps 1 is useful for loitering in the terminal area because there is a useful reduction in stall speed but no significant increase in drag. When selections greater than flaps 1 are made, the camber starts to increase. Flaps 5 or flaps 15 are typical selections for takeoff. As before, the larger flap settings are used for the approach to landing. We will now select flaps up. This is a non-practical selection and speed of operation. If you selected flaps all the way up like this when flying, the aircraft would sing like a stone. We are resetting the scene to consider slotted Fowler flaps. For maximum efficiency, Fowler flaps can have as many as 3 slots. This example shows triple slotted Fowler flaps as fitted to large jet transport aircraft, such as the Boeing 747. Again, this animation is not practical. We are merely showing the type of flap. You can see here the effect of the type of flap on CL max. The plain flap and the split flap have nearly the same ability to increase CL max. The slotted flap benefits from the greater angle to which it can be deployed without suffering airflow separation. But the best type of flap for increasing CL max is the Fowler flap. We now need to highlight the difference between the change in lift coefficient and the change in drag coefficient with increasing flap angle. In this example, we have selected flaps 5. You can see that the increase in lift coefficient is much greater than the increase in drag coefficient. With a selection from flaps 5 to flaps 10, you can see the increase in lift coefficient is less, while the increase in drag coefficient is greater. As the flap angle is increased, there will be a progressively smaller increase in lift coefficient and a larger increase in drag coefficient. This is the reason why the larger selections of flap are reserved for the landing approach, when a large amount of drag is a benefit. For takeoff, only the smaller flap angles are used, because drag must be kept to a minimum to optimize aircraft acceleration. This will be discussed in more detail in later lessons. The CL angle of attack graph shows a reduced stall angle with trailing edge flaps selected. This is because the lift curve is plotted using the original chord line, before the flaps are lowered. When the pilot lowers the trailing edge flaps, the wing camber is increased, and if the pilot did not prevent it, lift would increase. As the flaps deploy, the pilot must reduce the angle of attack so that the effective angle of attack remains constant, and that lift still equals weight. Please remember that any amount of flap will increase drag. We have already seen that CL max increases as the flaps are lowered, but unfortunately drag will also increase, so we need to consider LD max. We must generate enough lift to balance the weight, but at the same time drag must be a minimum. Therefore, drag will divide into lift the maximum number of times. We call that LD max. The following illustrations will show the efficiency of flaps. The greater the LD max, the greater the aerodynamic efficiency. If a tangent is drawn from the origin of the graph to the curve of the lift drag polar plot, the angle between the straight line and the horizontal axis is a measure of LD max. We will now compare the aerodynamic efficiency of the previously mentioned types of flap with that of no flap. Here you can see the CL-CD polar of the plane flap. Notice that the angle between the straight line from the origin and the horizontal axis is less than that for no flap. This shows a decrease in LD max, which is a reduction in aerodynamic efficiency. This is the CL-CD polar of the split flap, together with the plain flap. Notice the angle between the split flap straight line from the origin and the horizontal axis is again less than that for no flap, but pretty much the same as the plain flap. Therefore, the plain and the split flap have approximately the same aerodynamic efficiency. Now you can see the slotted flap polar. Less drag is generated, and it is more aerodynamically efficient than either the plain or the split flap. But again, LD max is less than with no flap. Here, we see the most aerodynamically efficient type of trailing edge flap, the Fowler flap. But once again, it has a lower LD max than no flap. Does an understanding of reduced LD max with flaps down have a practical application? Yes, it is a very important takeoff climb consideration. We have learned that the use of about 15 degrees of flap reduces the takeoff run. That's why flaps are fitted. But any amount of flap reduces the ability to climb. We can see that takeoff flap reduces the takeoff run required, but also reduces the ability of the aircraft to climb. When carrying out aircraft performance calculations prior to flight, this conflict must always be considered. Depending on the length of runway available and any obstacles present during the initial climb, it might be better to use no flaps for takeoff. This will be explained in more detail in future lessons. Flap movement, both up and down, may generate an aircraft pitching moment. Any pitching moment generated is due to movement of the centre of pressure, CP, and changes in downwash. Note that the CP is aft of the aircraft, CG. This generates a nose-down pitching moment. The aircraft, however, is in equilibrium because of the matching nose-up pitching moment from the downforce on the tail. First, we will consider movement of the CP. Only the top surface pressure distribution will be shown. As the flaps deploy, there is a general increase of suction on the top surface, but there is also an increased acceleration of the airflow in the vicinity of the flap hinge. This produces a localized reduction in pressure, which moves the CP aft, and an aircraft nose-down pitching moment is generated. Let us now take a look at the effect of downwash. You can see that as the flaps deploy, the downwash increases. This increases the downforce on the tail and generates an aircraft nose-up pitching moment. It is now obvious that flap deployment generates two pitching moments, a nose-down pitching moment from the wing and a nose-up pitching moment from the tail. So, if you are asked the question, what pitching moment does the aircraft experience when trailing edge flaps are deployed? The only answer you can give is, it depends. The net pitching moment the aircraft experiences will depend upon which of the two pitching moments is dominant. On some aircraft, the net pitching moment will be nose down. On some aircraft, the net pitching moment will be nose up, and on other aircraft, there will be no net pitching moment. However, if the aircraft you are flying has Fowler flaps, it will usually generate a net nose-down pitching moment when the flaps are deployed. Because Fowler flaps increase the wing area by moving rearwards when deploying, a larger nose-down pitching moment is generated. This gives an increased tendency to generate a net aircraft nose-down pitching moment when the flaps are lowered. If a T-tail is fitted to an aircraft, it will also influence the net aircraft pitching moment. A T-tail is attached in a higher position, so the change in downwash from flap deployment will have a smaller influence on the tail force, and a reduced nose-up pitching moment is generated. This animation repeats the fact that as flaps are lowered, the pilot must decrease the angle of attack, so that lift remains the same as the weight. Therefore, with flaps down, the aircraft will fly in a more nose-down attitude. On approach to landing, this is an advantage, as it gives a better view of the runway. Because of the high minimum speed of jet transport aircraft, even the fitment of trailing edge flaps does not reduce the takeoff and landing run to acceptable values. For this reason, in addition to the most efficient trailing edge flaps, jet transport aircraft must also be fitted with leading edge flaps. The next lesson will examine leading edge flaps in detail, plus the operational details of high lift devices. The design of jet transport aircraft is biased towards maximum efficiency at high speed. Unfortunately, they will also have a high minimum operating speed, and even the most efficient trailing edge flaps will not reduce the takeoff and landing run to acceptable values. Therefore, jet transport aircraft must also be fitted with leading edge high lift devices, known as flaps or slats. This lesson will examine the three main types of leading edge high lift device in detail, in their order of increasing efficiency. Being the least efficient, we will begin with the Kruger flap. The illustration shows a cross-section through the leading edge of the wing. You can see that the Kruger flap forms part of the leading edge lower surface. When fully out, the Kruger flap gives a smoother path for the airflow over the leading edge of the wing, allowing the airflow to retain maximum kinetic energy. Kruger flaps are either in or out. There are no intermediate angles like trailing edge flaps. Operationally, leading edge devices are usually used together with the trailing edge flaps. But for reasons of clarity, only leading edge devices will be illustrated. There is usually only one flap lever on the flight deck. When the flight crew makes a flap selection, an aircraft system will schedule the leading edge devices to operate in conjunction with the trailing edge flaps at the appropriate time. In this example, a selection of flaps 1 activates the Kruger flaps. They will remain fully out until the flaps are selected from flaps 1 to flaps up during retraction. With the Kruger flaps out, the camber of the wing is increased. And as you can see, CL max is increased. In addition, the forward end of the chord line is lowered, which increases the stall angle. The next type of leading edge device to consider is the variable camber leading edge flap. The variable camber is more efficient than the Kruger flap. The reason for its increased efficiency is that the variable camber leading edge flap has a mechanism that curves the flap surface as it extends. When fully out, the variable camber flap gives an even smoother path for the airflow than the Kruger flap, allowing maximum retention of kinetic energy in the boundary layer. Again, there are no intermediate selections possible. They are either in or out. In practice, their speed of operation is about twice that illustrated. With the variable camber leading edge flaps out, the camber of the wing is increased slightly more than with the Kruger flap. And as you can see, CL max is also increased. The forward end of the chord line is once again lowered, which increases the stall angle. Now we come to the most efficient leading edge high lift device, the slat. To illustrate the effect of slats, a wing is shown at a high angle of attack, with the airflow just starting to separate at the trailing edge. The aircraft is positioned on the lift curve. As the slats are driven open, high-energy air from under the leading edge flows onto the top surface of the wing. This increases the kinetic energy in the boundary layer, which in this example reattaches the airflow. Slats increase CL max by increasing the boundary layer kinetic energy. This merely extends the lift curve. If a constant angle of attack is maintained, the lift coefficient of the aircraft will remain the same, and there will be no operational change. For the aircraft to benefit from slats, the pilot must fly the aircraft at a higher angle of attack, a higher nose attitude. There are two disadvantages with the higher nose attitude. Firstly, when rotating the aircraft for takeoff or flaring to land, there is an increased tendency to tail strike. Secondly, there is reduced visibility from the flight deck when approaching to land. Here we can see a sketch of the low pressure area on the top of the wing, with the aircraft at a high angle of attack. Suction is reduced towards the trailing edge because of minor airflow separation. When slats are driven open, we know that the increased boundary layer kinetic energy reattaches the airflow. The low pressure area becomes more evenly distributed, but the total area changes very little. Please note that the suction peak does not move forward, so the effect of slats on aircraft pitching moment is insignificant. Some jet transport aircraft have an automatic system that will fully extend the slats for stall protection. If the aircraft approaches the stall angle too closely, the automatic slat system will extend the slats to the fully open position. This illustration shows the order of increasing stall angle for flaps. The configuration that gives the lowest stall angle is trailing edge flaps. The next higher stall angle is no flaps, and the highest stall angle is leading edge flaps. This is not an operational consideration, but the examiners might ask you. If a flap selection is made, and, due to a fault of some kind, only the flaps on one side move, the rolling moment generated can be greater than the pilot can oppose with roll control. Flap asymmetry must be prevented. To avoid the possibility of flap asymmetry, transport aircraft are usually fitted with a flap asymmetry protection system. Devices monitor flap extension angles on each half of the wing, and if an asymmetry of greater than 1 or 2 degrees is detected, the mechanism that drives the flaps is switched off, and a warning on the flight deck will alert the pilots. Transport aircraft can be fitted with a flap load relief system, which prevents the flaps deploying if the indicated airspeed is too high. The pilot can move the flap selector, but the flaps will not extend until the indicated airspeed is reduced to the value appropriate for that flap setting. These flap angle limiting indicated airspeeds are known as VFE. Excessive dynamic pressure can damage the flaps themselves, their hinges and operating systems, or the wing. In this example, flaps 25 has been selected at too high an indicated airspeed. In other words, above VFE for flaps 25. The flap load relief system prevents the flaps from moving. The aircraft is now slowed to VFE for flaps 25, and the flaps move down to 25 degrees. The indicated airspeed is now reduced to VFE for flaps 30. When flaps 30 is selected, the flaps move down to 30 degrees. But if the indicated airspeed is allowed to increase, the flap load relief system will drive the flaps back to flaps 25. If now the indicated airspeed is reduced to VFE for flaps 30, the flaps will move down to 30 degrees of flap again. Here we will only consider the effect of flaps on the takeoff and landing run. Other variables will be covered in future lessons. We will consider takeoff flaps first. The length of the takeoff run is affected by the minimum indicated airspeed at which the aircraft can safely fly. But the length of the takeoff run is also affected by the rate of acceleration. The minimum safe takeoff speed will be possible at the highest CL max, and this will be achieved at the largest flap setting. But large flap angles also generate the most drag, which will decrease aircraft acceleration and make the takeoff run longer. A smaller flap angle will give less CL max, which will result in a higher takeoff speed, but the reduction in drag will give better acceleration. Taking both CL max and drag into consideration, there will be an optimum flap angle that will give the shortest possible takeoff run. For jet transport aircraft, the optimum flap angle for takeoff is approximately 15 degrees. We can see that increasing flap angles result in a decreasing takeoff run. But beyond the optimum takeoff flap angle, the distance increases. What is the point in not using all of the runway length that is available? The operational advantage of using the optimum flap angle for takeoff is to carry more weight from a given runway length. After takeoff, a minimum climb gradient is required. The ability of an aircraft to climb is reduced by flaps because of the extra drag they generate. So, if the required minimum climb gradient will limit the maximum takeoff weight, a smaller flap angle will be used for takeoff, even though it will result in a longer takeoff run. If runway length is not limiting, you can see that the maximum takeoff climb limited weight will be achieved with no flaps. To reduce the landing distance, maximum flap angle should normally be used. This results in a lower minimum speed because of the high CL max, and a steeper approach path and increased deceleration because of the high drag. This aircraft has just taken off, and it is now time to retract the flaps. Note the indicated airspeed of 150 knots and the aircraft position on the flaps down lift curve. As the flaps retract, the lift coefficient decreases. Lift is now less than the weight, and the aircraft will sink. Increasing the angle of attack to keep lift the same is not an option, because as you can see from the lift curve, the aircraft will stall. Obviously, this is not the way to retract the flaps. We must trade indicated airspeed and angle of attack to keep lift the same as the weight. Let's reset the original conditions to consider the correct way to retract the flaps after takeoff. Before retracting the flaps, the indicated airspeed must be increased to VZF, the minimum indicated airspeed for zero flap. As the indicated airspeed increases, the angle of attack must be decreased to keep lift constant. Now when the flaps are retracted, the pilot can increase the angle of attack to keep the lift constant. When considering flap extension prior to landing, we can use the same principle of trading indicated airspeed and angle of attack to keep lift the same as the weight. As the flaps extend, the pilot must decrease the angle of attack. Just in case the examiners ask you, please note that to maintain level flight at a constant indicated airspeed as the flaps extend, the lift coefficient must remain constant. With the aircraft now on the flaps down lift curve, the pilot can decrease the indicated airspeed while increasing the angle of attack to keep lift the same as the weight. If an external force disturbs an aircraft from a steady state of flight, it is stability, built into the aircraft by the designers, that gives it the tendency to return to a steady state of flight without any help from the pilot. In this regard, all aircraft must have several qualities. Firstly, the aircraft must have enough stability to maintain a steady flight condition. In other words, the pilot can't be made to feel that the aircraft is balanced on the head of a pin, ready to head off into some strange attitude. The aircraft must also have the ability to recover from various disturbing influences by itself. An example of a disturbing influence is a gust of wind. The aircraft must also have proper response to the controls throughout the entire flight envelope. The study of stability is broken down into two categories: static stability and dynamic stability. Static stability is the initial reaction of the aircraft following removal of the disturbing force. Dynamic stability is what happens after the initial reaction. We will start with static stability and consider dynamic stability later. There are three types of stability: positive, neutral, and negative. To demonstrate positive static stability, we will consider a ball in a bowl. The ball is stationary in the bottom of the bowl. The ball is in equilibrium. As a reminder, equilibrium exists when the sum of the forces is zero and the sum of the moments is zero. The ball has been displaced from equilibrium by a disturbing force. When the disturbing force is removed, the initial reaction of the ball is to start back towards its previous state of equilibrium, a demonstration of positive static stability. You are probably thinking a ball would not just stop like that. No, it wouldn't. Although dynamic stability will be discussed later, it will help to have an insight now. As soon as the disturbing force is removed, the ball will return through its previous state of equilibrium until friction and air resistance damp out the motion. It will eventually stop moving in its previous state of equilibrium. Everything after the initial reaction is dynamic stability. Let's now consider neutral static stability. The ball is in equilibrium on a flat level plate. A disturbing force displaces the ball from a state of equilibrium, and when the disturbing force is removed, the ball remains in a new state of equilibrium, a demonstration of neutral static stability. Whenever a disturbing force moves the ball and then the disturbing force is removed, the ball remains in equilibrium. Now for a look at negative static stability. The bowl is inverted with the ball in equilibrium. The ball is displaced from equilibrium by a disturbing force. When the disturbing force is removed, the initial reaction is for the ball to displace further from equilibrium, a demonstration of negative static stability. We must now consider the aeroplane reference axes. These are used to help visualize the forces and moments on the aircraft. All axes pass through the center of gravity. Illustrated is the longitudinal axis. Here is the lateral axis. And this is the normal axis. The aircraft rolls about the longitudinal axis. In the context of stability, motion about the longitudinal axis is called lateral stability. An easy way to remember which is which is to add the axis about which the aircraft rotates. In this case, lateral stability is about the longitudinal axis. The aircraft yaws about the normal axis. Motion about the normal axis is called directional stability, the easy one to remember. The aircraft pitches about the lateral axis. Motion about the lateral axis is called longitudinal stability. Again, to fix in your mind which is which, add the axis about which the aircraft rotates. In this case, longitudinal stability is about the lateral axis. We will study longitudinal static stability first, because pitching motion does not interfere with either rolling or yawing. We know that the center of pressure moves when the angle of attack changes. During our study of stability, we will be considering changes in angle of attack, together with various center of gravity locations. To aid understanding, a location called the aerodynamic center is used. Don't think of this as a wing. This is merely a concept. To help you understand the concept, think of the aerodynamic center, the AC, as a pivot. Consider angle of attack 1. Angle of attack 1 will generate lift 1, acting through the center of pressure. Lift 1 is acting at distance 1, aft of the aerodynamic center. Lift 1 multiplied by distance 1 generates pitching moment m. Pitching moment m acts nose down, about the aerodynamic centre. An increase in angle of attack moves the centre of pressure forward and increases the lift. Angle of attack 2 generates lift 2, acting at distance 2. Lift 2 is bigger than lift 1, but distance 2 is shorter than distance 1, such that pitching moment m will remain the same. The Greek letter delta, in front of alpha and lift, is used to indicate change. The change in angle of attack has generated a change in lift. But because pitching moment m remains the same with a change in angle of attack, we can consider the change in lift acting at the aerodynamic centre. You can see that the original lift force is greyed out. We are interested only in the change in lift. There are 4 facts about the aerodynamic centre in which the examiners are interested. First, the location of the aerodynamic centre is stationary at 25% aft, but only in subsonic flow. During your studies of high-speed flight, we will discuss the location of the aerodynamic centre in supersonic flow. Second, the direction of pitching moment m is nose down about the aerodynamic centre. Third, pitching moment m stays the same with a change in angle of attack. Fourth, we consider the change in lift from a change in angle of attack to act at the aerodynamic centre. The aerodynamic centre will also be used in future lessons when we discuss aircraft limitations. During our study of stability, and later in aircraft limitations, we make 2 uses of the aerodynamic centre. First, it is stationary at 25% aft. Second, it is the point through which the change in lift acts. Having covered some basic facts about stability, we will now apply them to an aircraft. Illustrated is the wing of an aircraft. For the time being, we will ignore the rest of the aircraft. We are in level flight, in a state of equilibrium. The flight path is shown, as are the aircraft CG, the aerodynamic centre, and the greyed out lift force. An upward vertical gust has increased the angle of attack. This generates an increase in lift, acting at the aerodynamic centre. The change in lift is acting through arm X, forward of the aircraft CG. This generates an aircraft nose-up pitching moment, which pitches the aircraft nose up. This will further increase the angle of attack, and the aircraft will continue to pitch nose up at an increasing rate. The wing, considered in isolation, is therefore statically unstable. This illustration shows that the change in wing lift, multiplied by the wing arm, can be called the wing moment. As we have seen, the wing moment is destabilizing. We will now consider how the designers provide the aircraft with static longitudinal stability. The tail plane is the aerofoil that gives the aircraft static longitudinal stability. For the moment, we will consider that the vertical gust changes the angle of attack on the tail plane by the same amount as the wing. The tail plane will generate an increased up force. I know you are thinking the tail force should be pointing down, but here we are merely considering the change in force on the tail plane. All textbooks illustrate longitudinal static stability in this way. The change in lift on the tail plane acts through an arm to the aircraft centre of gravity. The change in tail plane lift, multiplied by the tail arm, can be called the tail moment. The tail moment is stabilizing. If the stabilizing tail moment is bigger than the destabilizing wing moment, the aircraft will have some measure of longitudinal static stability. A vertical gust has displaced the aircraft from equilibrium. But because the tail moment is larger than the wing moment, the aircraft will immediately start to return to its previous state of equilibrium, without any input from the pilot. The fore and aft position of the centre of gravity will have a significant effect on longitudinal static stability. The illustration shows a centre of gravity position at which the stabilizing tail moment is bigger than the destabilizing wing moment. The aircraft will have some measure of longitudinal static stability. If the centre of gravity moves forward, the length of both arms change. The tail arm becomes longer, which makes the stabilizing moment bigger. And at the same time, the wing arm becomes shorter, which makes the destabilizing moment smaller. Therefore, with the centre of gravity in a more forward position, the aircraft has more longitudinal static stability. If the centre of gravity moves aft, the length of both arms will change again. The tail arm becomes shorter, which makes the stabilizing moment smaller. And at the same time, the wing arm becomes longer, which makes the destabilizing moment bigger. Therefore, with the centre of gravity in a more aft position, the aircraft has less longitudinal static stability. Now let's consider what would happen if the centre of gravity is moved further aft. A CG position would eventually be reached when both the destabilizing moment and the stabilizing moment are the same. If a gust were to change the angle of attack, the aircraft would be displaced from equilibrium, but no net pitching moment would be generated. The aircraft would not displace any further, but would not start to return towards its previous equilibrium either. It would stay displaced. What type of longitudinal static stability would this be? Neutral longitudinal static stability. The CG position that will give the aircraft neutral longitudinal static stability is called the neutral point. Operationally, you would never fly an aircraft with the CG on the neutral point. You might think that neutral longitudinal static stability is not too bad. But remember, the aircraft must always be flown with a margin of safety. If the CG were to move after the neutral point, the aircraft would have negative longitudinal static stability, and when hit by a gust, will continue to displace from equilibrium, which is obviously not acceptable. Having returned the CG to the neutral point, we will now consider the acceptable CG range. If we move the CG slightly forward of the neutral point, the aircraft would have a small amount of longitudinal static stability, but there would still be an insufficient margin of safety. Moving the CG slightly further forward will increase longitudinal static stability a little more, but will still not provide a big enough margin of safety. With further forward movement, eventually a CG position will be reached when the minimum acceptable longitudinal static stability exists. The CG position that guarantees minimum acceptable longitudinal static stability is known as the aft CG limit. Operationally, the CG must never move outside the aft CG limit at any time during the flight. Calculating the CG position during the entire flight will be fully covered in a different subject called mass and balance. If we now move the CG forwards of the aft CG limit, the longitudinal static stability will increase. But we don't want the CG too far forward, because there is such a thing as too much longitudinal static stability. You might think the more longitudinal static stability, the better. But no. In addition to our example gust, the pilot can also momentarily change the angle of attack when a pitch input is made. Longitudinal static stability will oppose the pilot's pitch input in the same way it opposes a gust. The greater the stability, the more the resistance to pitch input. So, in addition to the effect of CG position on longitudinal static stability, we must also consider the effect of CG position on the ability of the pilot to maneuver the aircraft in pitch, and the stick forces required. Consequently, to ensure minimum ability for the pilot to maneuver the aircraft in pitch, plus ensure the stick forces are not too high, a forward CG limit is required. The forward CG limit will give maximum longitudinal static stability and guarantees minimum acceptable maneuverability and maximum acceptable stick forces. The aft CG limit will give minimum acceptable longitudinal static stability and gives maximum maneuverability and minimum acceptable stick forces. We will now take what we have learned about longitudinal static stability and, using simple sketch graphs, consider some of the variables. Here are the two axes. The vertical axis represents pitching moment, with increasing nose-up pitching moment above the horizontal axis and increasing nose-down pitching moment below. The horizontal axis represents lift coefficient, increasing to the right. Your previous knowledge will tell you that the horizontal axis could instead be labelled angle of attack or decreasing indicated airspeed. As you will see, all three values need to be considered to give a full understanding of these graphs. For the time being, we will use lift coefficient for the horizontal axis, but you need to keep the two alternative values in mind. An aeroplane in equilibrium is shown on the horizontal axis. How do we know it's in equilibrium? Because it is not generating a nose-up pitching moment or a nose-down pitching moment. An upward acting gust has increased the lift coefficient. And because the aircraft has some longitudinal static stability, it will generate a nose-down pitching moment. The nose-down pitching moment will start the aircraft back towards equilibrium. Remember, longitudinal static stability is just the initial reaction to a change in angle of attack. The graph is reset with the aircraft in equilibrium. A downward acting gust now decreases the lift coefficient. Because of its longitudinal static stability, the aircraft will once again generate a pitching moment, but this time it's a nose-up pitching moment. The nose-up pitching moment will start the aircraft back towards equilibrium. The graph is again reset with the aircraft in equilibrium. If we join together the point on the graph that represents the aircraft in equilibrium, the point that represents the pitching moment generated by an increase in angle of attack, and the point that represents the pitching moment generated by a decrease in angle of attack, the plot will represent a longitudinally statically stable aircraft. The curve on the right-hand end of the plot shows the aircraft nose-down pitching moment at the stall. Now let's use the graph to consider variations in longitudinal static stability. Movement of the red dot shows an increase in angle of attack, which generates a nose-down pitching moment. Reset the graph to equilibrium. A decrease in angle of attack generates a nose-up pitching moment. Now we'll look at a decreased level of longitudinal static stability. The same increase in angle of attack has generated a smaller nose-down pitching moment. Reset the graph to equilibrium. The same decrease in angle of attack has also generated a smaller pitching moment, but this time nose up. Now we'll look at an increased level of longitudinal static stability. The same increase in angle of attack has generated a much bigger nose-down pitching moment. reset the graph to equilibrium. The same decrease in angle of attack has also generated a much bigger pitching moment, but this time nose up. The green plot shows longitudinal static stability. The blue plot shows less longitudinal static stability. The magenta plot shows more longitudinal static stability. The direction of all three plots is downward, from left to right. This indicates positive longitudinal static stability. The angles of the plots shows the amount of longitudinal static stability. The steeper the plot, the greater the stability. What does this plot represent? An increase in angle of attack generates no pitching moment, nor does a decrease in angle of attack. This plot represents neutral longitudinal static stability. What do you make of this plot? An increase in angle of attack generates a nose-up pitching moment. This is not good. Reset the graph. A decrease in angle of attack generates a nose-down pitching moment. Again, this is not good. When the slope of the plot is upwards from left to right, it represents negative longitudinal static stability. As with positive longitudinal static stability, the steeper the slope, the greater the instability. Here are the three types of plot we'll be using from now on: stable, neutral, and unstable. So what does this plot represent? Here's a big clue. The plot represents an aircraft with a swept wing. Stable at high speed, because the plot slopes downward to the right. The plot continues to slope downward to the right as speed is reduced. But the slope is becoming less steep, which represents a slight decrease in longitudinal static stability. With further reduction in indicated airspeed, the stability becomes neutral. From your previous studies of swept wing stall at higher angles of attack, tip stall will begin. And like all swept wing aircraft, this will generate a nose-up pitching moment. In the next segment, we will be using graphs like these to illustrate other variables. The net pitching moment about the lateral axis is due to the contribution of each of the component surfaces. A fact the examiners might be interested in is that the wing camber has no effect on longitudinal static stability. This is because the pitching moment about the aerodynamic center is always nose down, regardless of angle of attack. The contribution of the wing has already been explained in previous lessons. But to remind you, the wing is destabilizing because the aerodynamic center is forward of the aircraft CG. At the small angle of attack used in the cruise, the fuselage acts as a symmetrical aerofoil. The reduction in pressure on the top is the same as the reduction in pressure on the bottom, with an area of stagnation pressure at the nose. Under these conditions, the fuselage generates no pitching moment. Any change in angle of attack generates an aircraft pitching moment, which is destabilizing. The pitching moment is generated by the change in pressure distribution on the fuselage and nacelles. As we have already established, the tailplane is the aerofoil that provides the stabilizing influence to the aircraft. This is due to the stabilizing pitching moment it generates when the aircraft is subjected to a change in angle of attack. For simplicity, the first explanation of longitudinal static stability assumed a gust would give the same change in angle of attack to the tailplane and the wing. In practice, the airflow at the tailplane will be affected by the airflow from the wing trailing edge, as illustrated, and the tailplane will experience a smaller change in angle of attack than the wing. The designers ensure the tailplane can always generate the appropriate stabilizing moment by attaching the tailplane at a smaller angle of incidence than the wing. This is called longitudinal dihedral. The illustration shows a wing incidence of 4 degrees and a tailplane incidence of 2 degrees. If a gust of wind increases the angle of attack by 4 degrees, the change in wing lift will be 100%, whereas the change in tailplane lift will be 200%. The graph shows a typical build-up of components and their effect on longitudinal static stability. The wing is destabilizing. The wing and the fuselage together are even more destabilizing. The tailplane contribution is very stabilizing. And when we consider everything together, the aeroplane has the required degree of longitudinal static stability. Notice the location of the CG in the illustration is listed as 20% MAC. The mean aerodynamic chord is used as a reference point from which the location of the CG is measured as a percentage. The higher the percentage, the further aft the CG. We can use the graph to show the effect of CG position on longitudinal static stability. With the CG at 10% MAC, the aircraft is stable. The aircraft is less stable with the CG at 20%, and even less stable with the CG at 30%. 40% MAC is the neutral point, and with the CG at 50% MAC, the aircraft will be unstable. The neutral point and 50% MAC are shown with a dash line, because operationally the CG must never be positioned outside the aft CG limit. The effect of thrust on longitudinal static stability will be greatest at low indicated airspeed and high thrust, such as during takeoff and the approach to landing. The vertical location of the thrust line defines one of the contributions. The illustration shows an aircraft with pod-mounted engines beneath the wing. Because the thrust line is below the aircraft CG, an increase in thrust will produce a nose-up pitching moment, which is destabilizing. A propeller located forward of the CG will also contribute a destabilizing effect. The change in momentum of the prop wash will generate a force normal to the plane of the propeller. It has already been stated that a stable aeroplane will resist displacement from equilibrium. The control surface displacement and the control forces should reflect the stability of the aeroplane and provide suitable reference to the pilot for precise control of the aeroplane. The effect of elevator deflection on pitching moment is illustrated. The elevator is neutral to the tailplane, and the aircraft is flying level at a given lift coefficient. A momentary increase in angle of attack generates a stabilizing nose-down pitching moment. Reset the graph. A momentary decrease in angle of attack generates a stabilizing nose-up pitching moment. Reset the graph. The illustration shows a certain amount of static longitudinal stability, with the elevator at neutral. The aircraft is maintaining level flight by increasing the angle of attack as the indicated airspeed is decreased, until once again it is in equilibrium at a lower airspeed. To hold this angle of attack at a lower airspeed, the elevator must remain displaced at a position 10 degrees up from neutral. A momentary increase in angle of attack generates the same stabilizing nose-down pitching moment. Reset the graph. A momentary decrease in angle of attack generates the same stabilizing nose-up pitching moment. Reset the graph. The illustration has shown the same amount of static longitudinal stability with the elevator at 10 degrees up as it did with the elevator neutral. This is easily seen at a glance from the fact that the two plots are parallel. Now the aircraft is continuing to maintain level flight by decreasing the angle of attack as the indicated airspeed is increased, until once again it is in equilibrium at a higher airspeed. To hold this angle of attack at a higher airspeed, the elevator must remain displaced at a position 10 degrees down from neutral. A momentary increase in angle of attack generates the same stabilizing nose-down pitching moment. Reset the graph. A momentary decrease in angle of attack generates the same stabilizing nose-up pitching moment. Reset the graph. The illustration has shown that the same amount of static longitudinal stability will be obtained with the elevator at 10 degrees down, neutral, and 10 degrees up. Elevator position does not affect longitudinal static stability because only the change in lift is considered. We can now consider the effect of CG position on elevator deflection. Please note that the vertical axis of the graph now represents elevator deflection. With the CG at 10% MAC, the aircraft will have a lot of longitudinal static stability, and a large up elevator deflection is required to maintain a given lift coefficient. With the CG further aft at 20% MAC, there is less longitudinal static stability, and less up elevator is required to hold the same lift coefficient. With the CG even further aft at 30% MAC, there is less longitudinal static stability, and less up elevator is required to hold the same lift coefficient. This animation illustrates the increase in aircraft controllability with an aft CG. Please note that the horizontal axis of the graph now represents indicated airspeed. All aircraft must have something called stick position stability. This means that the aeroplane must require the stick to be moved aft to increase the angle of attack, and trim at a lower indicated airspeed, and to be moved forward to decrease the angle of attack and trim at a higher indicated airspeed. While maintaining level flight, as the indicated airspeed is reduced, the elevator must be moved up. This requires the pitch control in the cockpit to be moved aft. Reset the graph. While maintaining level flight, as the indicated airspeed is increased, the elevator must be moved down. This requires the pitch control in the cockpit to be moved forward. Please note that the vertical axis now represents stick force. In addition to stick position stability, all aircraft must have stick force stability. This means that a push force must be required when indicated airspeed is increased, and a pull force must be required when indicated airspeed is decreased. The plot shows the stick force gradient with the aircraft in trim at low indicated airspeed. To maintain a reduced indicated airspeed of, let's say, 10 knots at low speed, a certain pull force is required. The plot now includes a stick force gradient with the aircraft in trim at a higher speed. To maintain the same 10 knot speed reduction from trim speed at a higher speed, a pull force is still required, but the required pull force is smaller. We can now consider the effect of CG position on stick force. From our previous studies, we know that moving the CG forward increases longitudinal static stability. With the CG at 30% MAC, a speed reduction requires a small pull force. With the CG at 20% MAC, the same speed reduction requires a larger pull force. With the CG at 10% MAC, the same speed reduction requires an even larger pull force. Moving the CG aft decreases the stick forces required to displace the aircraft from trim speed. Aerodynamic damping was first discussed when you were studying drag. We will now see how it can affect static stability. While the pilot is pitching the aircraft, the change in tailplane angle of attack is greater than the change in angle of attack of the wing because the tailplane is moving down. As soon as the pitch angle stops changing, the tailplane and the wing have effectively the same angle of attack. For the study of maneuver stability, we need to consider the period during the change in angle of attack. Study the vector diagram. It shows the tailplane with the true airspeed vector and the speed of tailplane down travel vector. The effective airflow direction is the resultant of the aircraft true airspeed and the speed of tailplane down travel while pitching. You can now see the increase in angle of attack while pitching, which generates an upforce that we know is aerodynamic damping. Aerodynamic damping gives a change in tail force, in this case upwards, while the pilot is pitching the aircraft nose up. At higher altitude, at the same indicated airspeed, the true airspeed is faster, which reduces the change in tail force for the same rate of aircraft pitch change. Let's consider the diagram we used earlier to define the neutral point. The neutral point is the position at which the CG would need to be for the destabilizing wing moment and the stabilizing tailplane moment to be the same. If we now add the change in tail lift to the change in tailplane lift due to a gust, the CG would have to be further aft for the wing moment and the tailplane moment to balance. This CG position is called the maneuver point. The maneuver point will always be aft of the neutral point. If we now look again at the aft CG limit and a sample aircraft CG position, you can see that the aircraft will always have more maneuver stability than static stability. This is because the distance from the maneuver point to the aircraft CG is greater than the distance from the neutral point to the CG. We can now take what we have learned about maneuver stability and apply it to a study of stick force versus load factor. An aircraft with positive maneuver stability should give a steady increase in stick force with increase in load factor, or G. The stick force per G must be positive, but neither too high nor too low. If the stick force per G is too high, the aircraft will be difficult and tiring to fly. If the stick force per G is too low, the aircraft may be accidentally overstressed because of the light control forces. You may be asked to calculate stick force per G, so you need to remember that in level flight the aircraft is at 1 G, and a maneuver that gives a load factor of 2.5 is only a 1.5 G increase. The graph shows a typical stick force gradient. A load factor of 1.6 G requires a 10-pound pull force, and a load factor of 2 G requires a stick force of 18 pounds. These stick force values don't represent any particular aeroplane and are just sample values. Let's now consider the effect of various CG positions on the stick force gradient, starting with the CG at 30% MAC. With the CG further aft at 40% MAC, the stick force gradient is reduced, in that, for the same load factor, the stick force is reduced. With the CG forward at 10% MAC, the stick force gradient is increased. For the same load factor, the stick force is higher. We can now consider the effect of altitude on stick force per g. At higher altitude, the stick force gradient is reduced. This is due to reduced aerodynamic damping. In conclusion, the possibility exists that the forward CG limit could be set to prevent an excessive stick force gradient, and thereby an inability for the pilot to maneuver the aircraft adequately. As the CG moves aft, the stick force gradient decreases, and the lower limit of stick force gradient may be reached, and the pilot could be in danger of too readily being able to accidentally overstress the aircraft. Designers can modify the stick forces, if required, to give adequate maneuverability throughout the entire flight envelope. The first device that can be used to tailor the control forces is the downspring. The downspring is used to increase the airspeed stick force stability. The downspring consists of a preloaded spring attached to the control system that tends to rotate the elevator down. The effect is to contribute an increment of pull force independent of control deflection or airspeed. The second device used to tailor the control forces is the bob weight. The bob weight consists of an eccentric mass attached to the pitch control system. The bob weight mass is subjected to the same change in load factor as the aeroplane. Thus, the bob weight will provide an increment of stick force in direct proportion to the load factor applied. This will prevent the pilot applying too much G during maneuvers. The more the pilot pulls back, the more resistance the bob weight adds to the control system. An aeroplane must have adequate controllability as well as adequate stability. As previously mentioned, an aeroplane with high longitudinal static stability will have great resistance to displacement from equilibrium. There are three conditions of flight that provide the critical requirements of longitudinal control power: maneuvering, takeoff, and landing. Any one or a combination of these conditions can determine the position of the forward CG limit. We will look first at the maneuvering control requirements. The aeroplane should have sufficient pitch control power to achieve the maximum usable lift coefficient during maneuvers. The illustration shows that with the CG forward at 10% MAC, the maximum elevator deflection is not capable of trimming the aeroplane at CL max. But with the CG slightly further aft at 18% MAC, maximum elevator deflection is now capable of trimming the aeroplane at CL max. Now for a look at the takeoff control requirements. At takeoff, the aeroplane must have enough elevator control power to be rotated to the takeoff attitude. Anything that increases the nose-down pitching moment will increase the amount of elevator deflection required for the same pitch attitude. For example, if the CG is further forward, or the rolling resistance is increased by, for instance, runway contamination. Now we can look at landing control requirements. When flaring to land, enough elevator control power must be available to rotate the aircraft to the required nose-up attitude. Anything that increases the nose-down pitching moment will increase the amount of elevator deflection required for the same pitch attitude, such as idle thrust, full flap, forward CG, and the aircraft in ground effect. Each of the longitudinal control power requirements are critical for high longitudinal static stability. If the forward CG limit were accidentally exceeded, the aeroplane may encounter insufficient controllability in any of these conditions. To conclude our study of longitudinal static stability, it must be remembered that the forward CG limit is set by the minimum permissible controllability, and the aft CG limit is set by the minimum permissible stability. You must keep your aircraft CG within the forward and aft limits at all times during the flight. It is now time to look at dynamic stability. We can then apply what we learn to a study of longitudinal dynamic stability. We will first consider a type of dynamic stability called subsidence. This is not operationally possible for an aeroplane. The vertical axis is displacement from equilibrium, and the horizontal axis is time. The red dot represents an aeroplane in equilibrium. The red dot is displaced from equilibrium, and when the disturbing force is removed, the initial reaction is to start to move back towards equilibrium. This illustrates positive static stability. And over a period of time, the dot returns to equilibrium. This illustrates positive dynamic stability. Let's reset the graph and reintroduce the ball in the bowl. Displacement takes place. The disturbing force is removed, and an initial return towards equilibrium begins. Over a period of time, a return to equilibrium takes place. We have an illustration of positive static and positive dynamic stability. How is it possible for the ball to gently return to equilibrium with no oscillations? Damping. If the bowl is full of a viscous substance, such as syrup, the ball might act as illustrated. Now we will consider another type of dynamic stability, called divergence. The red dot is displaced from equilibrium, and when the disturbing force is removed, the initial reaction is to start to move further away from equilibrium. This illustrates negative static stability. And over a period of time, the dot continues to move away from equilibrium. This illustrates negative dynamic stability. We have a negative static and negative dynamic stability. Let's reset the graph and include the ball in the bowl. Displacement takes place. The disturbing force is removed, and the initial movement away from equilibrium begins. Over a period of time, a further movement from equilibrium takes place. An illustration of negative static and negative dynamic stability. Let's have a look at neutral dynamic stability. The red dot is displaced from equilibrium, and when the disturbing force is removed, the initial reaction is to stay displaced from equilibrium. This illustrates neutral static stability. And over a period of time, the dot continues to stay equally displaced from equilibrium. This illustrates neutral dynamic stability. We have neutral static and neutral dynamic stability. Another type of dynamic stability is called damped oscillation. The red dot is displaced from equilibrium, and when the disturbing force is removed, the initial reaction is to start back towards equilibrium. This illustrates positive static stability. And over a period of time, the dot continues to move back to equilibrium with several oscillations. This illustrates positive dynamic stability. We have positive static and positive dynamic stability. Let's reset the graph and include the ball in the bowl. Displacement takes place. The disturbing force is removed, and the initial movement back towards equilibrium begins. Over a period of time, with several reducing oscillations through equilibrium, a return to equilibrium takes place. An illustration of positive static and positive dynamic stability. This is the ideal type of stability for an aeroplane, but in reality it is not quite so good as illustrated. This next type of dynamic stability is called undamped oscillation. The red dot is displaced from equilibrium, and when the disturbing force is removed, the initial reaction is to start back towards equilibrium. This illustrates positive static stability. And over a period of time, the dot continues to oscillate through equilibrium with no reduction. This illustrates neutral dynamic stability. We have positive static and neutral dynamic stability. Let's reset the graph and include the ball in the bowl. Displacement takes place. The disturbing force is removed, and the initial movement back towards equilibrium begins. Over a period of time, there is continuous oscillation through equilibrium with no damping of motion. An illustration of positive static and neutral dynamic stability. Clearly, energy is being added for this to occur. The final type of dynamic stability is called divergent oscillation. The red dot is displaced from equilibrium, and when the disturbing force is removed, the initial reaction is to start back towards equilibrium. This illustrates positive static stability. But over a period of time, the dot continues to oscillate through equilibrium with an increase in displacement. This illustrates negative dynamic stability. We have positive static and negative dynamic stability. Let's reset the graph and include the ball in the bowl. Displacement takes place. The disturbing force is removed, and the initial movement back towards equilibrium begins. But now, over a period of time, there is increasing oscillation through equilibrium. The only way this can occur is for energy to be added. The energy usually comes from the pilot trying to damp out the motion, but out of phase with it, making it worse instead of better. This is called pilot-induced oscillation. All aircraft must demonstrate the required amount of static and dynamic stability. If the aircraft were allowed to have static instability with a rapid rate of divergence, it would be very difficult, if not impossible, to fly. Longitudinal dynamic stability concerns the variation of displacement with time following a disturbance. Longitudinal dynamic stability consists of two basic types of oscillation: long-period oscillation, the phugoid, and short-period oscillation. We will consider the long-period oscillation, the phugoid, first. The phugoid is a gradual interchange of potential and kinetic energy about some equilibrium airspeed and altitude. The period of oscillation is between 1 and 2 minutes, so is easily controlled by the pilot. There are changes in altitude, attitude and airspeed, but there is no significant change in angle of attack. Damping in the phugoid is weak. Short-period motion consists of rapid pitch oscillations, during which the aeroplane is constantly restored towards equilibrium by its static stability and the displacement being decreased by pitch damping. So flying at high altitude will tend to reduce dynamic stability due to the reduction in aerodynamic damping. Short-period oscillation involves rapid and significant changes in angle of attack, load factor, so can generate damaging flight loads to the aircraft structure. There is no significant change in altitude, attitude, or airspeed. The period of motion of 1 to 2 seconds is close to the normal pilot response lag time. There is the possibility that an attempt by the pilot to forcibly dampen oscillation may make it worse and produce instability. This concludes our study of longitudinal stability. We will consider directional stability and lateral stability next. Directional stability involves moments about the normal axis and their relationship with yaw or side slip angle. A disturbing force has yawed the aircraft to the left. The angle between the relative airflow and the longitudinal axis is called the side slip angle. This is a positive side slip angle. If the aircraft is yawed to the right, it would be a negative side slip angle. A question in the written exam might describe this aircraft as being nose to the left. However, a pilot would describe this aircraft as being in a right side slip. If the aircraft illustrated has directional stability, when displaced from equilibrium, it would generate a stabilizing yawing moment to the right. The contribution of the fuselage is destabilizing because its aerodynamic center is forward of the aircraft CG. The side surface of the aircraft is referred to as the keel surface. There is an area of keel surface forward of the CG and an area of keel surface aft of the CG. For adequate directional stability, the keel surface after the CG must be increased with the addition of a fin, or as it's sometimes called, a vertical stabilizer. The fin generates a stabilizing moment that is larger than the destabilizing moment from the fuselage. You must appreciate that when taxiing, during the takeoff run and during the landing run, in fact, whenever the aircraft is moving with the wheels on the ground, the directional stability of the aircraft will always generate a yawing moment into the wind. This is known as weathercocking. The pilot must actively prevent weathercocking by use of the rudder. A swept wing also gives a small stabilizing moment. Whenever the aircraft side slips, in this case to the right wing has a reduced sweep angle and the left wing has an increased sweep angle. This gives more lift on the right wing and less lift on the left wing. Consequently, the right wing has more induced drag and the left wing has less induced drag, which results in a small stabilizing contribution. We have seen that the fin gives an aircraft directional static stability, but sometimes a basic aircraft design undergoes modification to increase its fuselage capacity, which reduces its static directional stability. It is not possible to just fit a larger fin, so a device called a dorsal fin and/or a ventral fin can be added. These are both lightweight and simple to attach. The dorsal fin is more common, and not only increases the keel surface aft of the CG, but also decreases the aspect ratio of the fin. A high aspect ratio aerofoil has a certain stall angle, but a low aspect ratio has a larger stall angle. A swept-back aerofoil also has an increased stall angle. The majority of aircraft have a swept-back fin for this reason. Bear in mind that the side slip angle of the aircraft is effectively an angle of attack, and if the fin were to stall, the aircraft would become directionally unstable. To review the makeup of directional static stability, we can see that the fuselage is destabilizing. The fin alone is very stabilizing, but has a limited maximum side slip angle because of the possibility of fin stall. The complete aeroplane has directional static stability, which can be restricted by the stall angle of the fin. The addition of a dorsal fin can retain acceptable directional stability, and it reduces the likelihood of fin stall during normal operations. The final thing to consider is the purpose of the ventral fin. The illustration shows an aircraft flying at a small angle of attack, with a typical yawing moment to side-slip angle ratio. The plot shows an acceptable value of directional static stability. As the aircraft slows down, its angle of attack must be increased. The wake from the wing is now contacting the fin and reduces its effectiveness. You can see the plot now represents the reduced level of directional static stability. The addition of a ventral fin will increase the directional static stability at high angles of attack. During this lesson, you may have noticed how directional static stability might interact with lateral static stability. Lateral static stability will be discussed next, and we can then investigate how directional and lateral stability interact with each other. Lateral stability involves the study of moments about the longitudinal axis. If the aircraft is displaced away from wings level, the inclination of the lift vector will generate a side force, and the aircraft will start to move sideways through the air. This is known as side slip. From our study of directional stability, it is obvious that a side slip will generate a yawing moment. If we freeze the animation during the side slip, we can see that a side slip angle exists, and the resultant fin force will generate a yawing moment towards the direction from which the airflow is coming, and the aircraft will weathercock into the wind. We are seeing a sample of the interaction between lateral stability and directional stability, which will be fully explained at the end of this lesson. For the study of lateral stability, we will concentrate on the rolling moments generated by a side slip. The type of lateral stability is determined by the direction of the rolling moment generated by the side slip. If the side slip generates an unfavourable rolling moment, the aircraft will roll further away from wings level. This is unstable due to side slip. If the side slip generates no rolling moments, the aircraft will neither roll further away from nor back towards wings level. This is neutral. If the side slip generates a favourable rolling moment, the aircraft will roll back towards wings level. This is stable due to side slip. The degree of lateral stability an aircraft has is the net result of the contribution of its component parts. First, we will look at the contribution of the wing. As the aircraft side slips, the relative airflow is no longer parallel to the longitudinal axis, and the forward speed vector and the side slip vector give a resultant relative airflow from the side. It will be easier to see what is happening if a two-dimensional view is used. As the aircraft side slips, the relative airflow is from the side, which we can replace with a view of an airflow stream. We can see that the airflow path is partly over the top and partly beneath the fuselage. This airflow is around the fuselage where the wing is attached. First, we'll look at a wing mounted on the bottom of the fuselage. The wing into wind has a decreased effective angle of attack and less lift, whereas the wing out of the wind has an increased angle of attack and more lift. The difference in lift on each half of the wing will generate a rolling moment that rolls the aircraft further away from wings level. The aircraft has negative lateral static stability. The designers can reduce the unstable contribution of a low-mounted wing by fitting the wing on the fuselage at an angle. This is called dihedral. the upward inclination of the wing from the horizontal. Let's see how dihedral reduces the unstable contribution of a low-mounted wing. It is clear that dihedral removes the wing from the influence of the airflow around the bottom of the wing fuselage junction. And the airflow over the top gives more lift on the wing into wind and less lift on the wing out of the wind, which generates a rolling moment back towards wings level. Dihedral gives an aircraft with a low-mounted wing positive lateral static stability. We will now take a look at the high-mounted wing. The airflow over the top of the fuselage wing junction gives more lift on the wing into wind and less lift on the wing out of wind, which generates a rolling moment back towards wings level. An aircraft with a high-mounted wing has positive lateral static stability merely because of the wing position on the fuselage. Because a high-mounted wing gives the same positive contribution to lateral stability as does dihedral, a high-mounted wing is known as a dihedral effect. A designer may decide on a high wing configuration because a low fuselage position with the aircraft on the ground is desirable for ease of loading. Potentially, the dihedral effect of the high wing may give too much lateral stability. If so, the designer can reduce the stable contribution of a high wing by fitting the wing at a downwards angle. This is called anhedral, the downward inclination of the wing from the horizontal. Most jet transport aircraft have a swept wing to increase the efficiency of high-speed flight. In a right side slip, the wing into the wind has less effective sweep angle, and the wing out of the wind has more effective sweep angle. This gives more lift on the right wing and less lift on the left wing, which generates a stabilizing left rolling moment. The swept wing provides a stable contribution to lateral stability, so is also classified as a dihedral effect. If an aircraft has a high-mounted wing that is also swept, it will have two dihedral effects and may have too much lateral stability. If this is the case, the wing will require anhedral to ensure the proper amount of lateral stability. The fin has already been identified as the aerofoil that provides directional stability. But in a side slip, the aerodynamic force on the fin acts above the CG, which generates a small stabilizing moment. The fin, therefore, is also a dihedral effect, but a small one. The contribution of a ventral fin is very small indeed. As you can see, the aerodynamic force is in the same direction, but is acting below the CG and is destabilizing. For all practical purposes, any contribution of the ventral fin to lateral stability is insignificant. The illustration shows the low pressure area on the top of the wing. Each half of the wing generates a share of the lift, and each component of lift will act at a certain distance from the CG. Any change in lift in a side slip will act through a given arm length to generate a rolling moment. When the flaps are down, the inboard portion of the wing generates a larger percentage of the lift, and each component of lift will be located further inboard. With the flaps down, any change in lift in a side slip will act through a shorter arm and generate a smaller rolling moment. Hence, with flaps down, lateral stability is reduced. As has become increasingly obvious, in a side slip, the lateral and directional response of an aircraft will be coupled. Side slip will simultaneously produce a rolling and a yawing moment. The type of lateral dynamic stability an aircraft will exhibit is determined by which type of static stability is dominant, directional or lateral. If directional static stability is dominant, the aircraft will suffer from spiral instability. If lateral static stability is dominant, the aircraft will suffer from Dutch roll, a combination of rolling and yawing. Because jet transport aircraft have a swept wing, they have a tendency to Dutch roll, and are fitted with a device called a yaw damper to prevent it.
This lesson will cover the basic flying controls, their location on the aircraft, their operation and primary effects, and the various methods available to designers for making control of the aircraft easier and safer for the pilots, and ultimately, of course, safer and more comfortable for the passengers. Variations on the basic configurations will be covered in a subsequent lesson. The basic method of changing the attitude of an aircraft, that is, its position relative to the horizon, is by temporarily changing the camber of the airfoil of the wing, tailplane or fin, which will alter the lift it produces. The diagram shows the change in lift with changes in control surface position. The overall effect of a control movement will also depend on speed. An aircraft needs to be controllable about each of its three axes, which pass through the centre of gravity, or CG, which is conventionally portrayed by a circle with alternate black and white quarters. Basic controls will consist of flap-type sections incorporated into the trailing edges of the main flying surfaces, and positioned at the extremities furthest from the CG to give the greatest control movement. One axis runs vertically through the centre of gravity. This is the normal axis, movement about which is controlled by the rudder, the vertical control surface attached to the fin. The movement around the normal axis is called yaw and can be termed directional control. It is worth noting, however, that the rudder is not used to change direction by yawing the aircraft, but rather for preventing yaw, both in normal and asymmetric flight. This will be covered in more detail in a later lesson. The lateral axis passes through the CG running parallel to a line passing through the wingtips. And movement around this axis is called pitch. The control surfaces are the elevators, which move up and down together to give longitudinal control, and are mounted on the trailing edge of the tailplane. The third axis is the longitudinal axis, which runs from nose to tail through the CG. Movement around this axis is called roll, and is provided by the ailerons, which are mounted at or near the wingtips. They move in opposition. The downgoing aileron increases the lift on that wing, and the upgoing one decreases lift on the other, giving lateral control. These are the conventional three-axis basic control surfaces. In the following lesson, we shall look at variations on the basic types of control surfaces. You have been shown that large and/or fast aircraft have high stick forces because of the large hinge moments generated. Stick forces that are too high make an aircraft difficult for the pilot to control. If aerodynamic balance cannot provide the required assistance to the pilot, powered flying controls must be used. Powered flying controls are hydraulically operated, either using a tapping from the aircraft main hydraulic system, or alternatively using completely self-contained power packs. Powered flying controls can be divided into two categories: power-assisted and fully powered. We will start by looking at power-assisted flying controls. In a power-assisted flying control system, the Power Flying Control Unit, referred to as a PFCU, provides most of the force necessary to reduce the hinge moments. The pilot normally provides only the remaining force. These first few animations merely show the sequence of the operating principle. When the pilot moves the control column, you can see that both the control surface and the servo valve are moved. Movement of the servo valve provides a path for hydraulic fluid under pressure to one side of the PFCU piston and opens the other side to return. However, the piston cannot move because it is connected to the aircraft structure. But the PFCU body is free to move the control surface. The reason for this design arrangement is to make sure that the control surface is moved to the angle and at the rate required by the pilot. This is called follow-up. The force from the hydraulic system moves the body of the PFCU and the control surface until the input from the servo valve is cancelled by the motion of the PFCU body. A hydraulic lock now exists. In reality, as soon as the pilot starts to move the cockpit control, the PFCU immediately moves the control surface to the angle and at the rate of motion commanded. It can be seen that a small proportion of the aerodynamic force generated by moving and holding the control surface into the airflow is still felt by the pilot as stick force, so the natural feel of the controls is retained. The stick force will change in proportion with the square of the IAS, as it would in a purely manual control system. If hydraulic pressure is lost from a power-assisted flying control, the pilot would still be able to control the aircraft, but with significantly higher stick forces. Power-assisted flying controls, therefore, do not require a separate manual reversion system. If the speed or size of an aircraft dictates, a fully powered system will be fitted. As before, these first few animations merely show the sequence of the operating principle. When the control column is moved, the servo valve directs the hydraulic fluid under pressure to one side of the piston and opens the other side to return. The body of the PFCU will move the control surface until the body reaches the position of the servo valve, and then it will stop. The fluid in the PFCU is now trapped, giving a hydraulic lock that prevents any movement of the control surface by the airflow. In reality, as soon as the pilot starts to move the cockpit control, the PFCU immediately moves the control surface to the angle and at the rate of motion commanded. In the fully powered system, there is no mechanical connection between the control surface and the cockpit control. Therefore, the pilot has no stick force or feel at all and could accidentally overstress the aircraft. Previously described devices merely reduced the stick force or feel to manageable levels. There was always an aerodynamic force present at the cockpit control to give a sense to the pilot of the input made. In other words, the pilot could feel the input they had made on the cockpit controls. This feel is essential. A device must be incorporated in a fully powered flying control system to duplicate the required stick force or feel artificially. The artificial feel unit responds to changing dynamic pressure in the same way as an airspeed indicator. And because the symbol for dynamic pressure is Q, the device is also referred to as Q feel. As before, these illustrations are schematic to show the operating principle. If hydraulic pressure to fully powered flying controls were lost, the aircraft would become uncontrollable. so some alternative means of control must be provided to guarantee safe flight. This can be done either by manual reversion or designing redundancy into the power flying control system. Manual reversion can be achieved by either servo tabs or spring tabs. In the event of hydraulic failure to the PFCU, a valve automatically opens to provide a path for the fluid across the piston. This cancels the hydraulic lock and allows movement of the control surface by either a servo tab or spring tab. Redundancy involves the use of multiple, completely independent hydraulic systems to power the flight controls. Each control surface can also be split with each segment powered by a separate hydraulic system. For modern jet transport with only 3 and more commonly 2 gas turbine engines, a ram air turbine or RAT is fitted to maintain adequate redundancy. In the event of an engine and/or a pump failure, the RAT can be deployed to provide a hydraulic flow to the primary flying controls only. To summarise, power flying controls must be used on large and/or fast transport aircraft that have control forces too high for the average pilot. Power-assisted controls retain some of the control's natural feel, but most of the force required is provided hydraulically. Fully powered controls use hydraulics to provide all the force needed to move the control surfaces into the airflow, but there is no direct link between the pilot's controls and control surfaces, and therefore an artificial feel system is required to give the pilot the stick force necessary to fly the aircraft safely. Control surface flutter can affect the ailerons, the elevator and the rudder. Of the 3, we will consider aileron flutter, being perhaps the easiest to visualize. The movements shown are deliberately exaggerated for clarity. When an aileron is deflected downwards into the airflow, an aerodynamic force will be generated, acting upward at the hinge line. This aerodynamic force will twist the wing about its torsional axis and start to wind up the wing like a spring. Because the CG of the control surface is aft of the hinge line, and because there is always a small amount of backlash in the control system, when the wing twists, the aileron displacement will be increased slightly. The increased deflection of the aileron will give an increased twisting force to the wing. This set of actions will repeat. Eventually, the rate of wing twist will decrease and the aileron will start to catch up with the twisting wing, and then the whole process will reverse and become divergent. The result of aileron flutter is here illustrated. Clearly, this is unacceptable and must be prevented. Don't forget, this can occur with the rudder and elevator too. The pilot cannot prevent flutter. Even if you hold the cockpit controls rigid, backlash in the control run will still allow the control surfaces to flutter. Even power flying controls have some backlash. You might think that to reduce control surface flutter, the wing could be made stiffer to stop it twisting. Theoretically, yes, but no structure is absolutely rigid, and increased stiffness increases structural weight, something to be avoided. Remember, reducing flutter is not acceptable. Flutter must be prevented. The control surfaces themselves must have their mass redistributed to prevent them lagging when an input is made. This is called mass balance. To prevent flutter, the CG of the control surface is moved forward onto the hinge. You can see that the force on the hinge line still twists the aerofoil, but there is no increased control surface deflection. A weight is added in front of the hinge to move the CG of the control surface forward onto the hinge line. To minimize the size of the mass balance weight, the weight is sometimes mounted on an arm, as illustrated. When possible, the mass balance weight is mounted inside the aircraft structure to minimize drag. If possible, the presence and security of mass balance weights should be checked during the pre-flight walk-round. Control in pitch is usually achieved with an elevator or, on a few light aircraft, by an all-moving slab tailplane. This entire sequence is simplified for clarity, and we will ignore the effect of any change in IAS. Consider an aircraft in equilibrium at a steady speed with the elevator neutral. If the elevator is deflected up, the tailplane will develop an increased downforce that will begin to pitch the aircraft nose up. As the aircraft begins to pitch up, static longitudinal stability will start to give an opposing nose-down pitching moment, and when the two pitching moments are equal, the aircraft will stop pitching. To hold that particular pitch angle, the elevator must remain displaced. Hence, the elevator is known as a displacement control. If we consider the CG further forward from our previous studies, static longitudinal stability will be increased, and a greater upward deflection of the elevator is required to hold the same pitch angle. This is not something that would happen in flight, but shows that, with a forward CG, a greater elevator deflection is required for a given pitch angle. For this example, to return to level flight, the elevator is returned to neutral and the static longitudinal stability will pitch the aircraft nose down. Smaller aircraft use ailerons for control in roll, but the majority of modern, high-speed jet transport aircraft use a combination of ailerons and spoilers. You may consider this a strange-looking aeroplane, but the two halves of the wing and the cockpit control have been displayed this way to give as large a view as possible. Also, the aileron displacement shown in the following illustrations is emphasized for clarity and is much bigger than that required in practice. If the control wheel is moved to the left aileron moves up. This decreases the camber of the wing in the vicinity of the aileron and reduces lift. At the same time, the right aileron moves down. This increases the camber of the wing in the vicinity of the aileron and increases lift. The difference in lift on the two halves of the wing generates a rolling moment to the left, and the aircraft will start to roll to the left. If you were to hold the ailerons displaced from neutral like this, the left rolling moment would still exist and the aircraft would continue to roll to the left about the longitudinal axis. In normal flight, not something you would want to happen. Clearly then, ailerons are not a displacement control like the elevator. Ailerons are a rate control. If ailerons are displaced from neutral only slightly, the aircraft will roll slowly. The greater the aileron displacement, the greater the rate of roll. Usually, you roll the aircraft to a given bank angle to change heading, in other words, to turn. To hold a given bank angle, you must reduce the rolling moment to zero by returning the ailerons to neutral. Please bear in mind that we are presenting only the principles of flight. When you start flight training, your instructor will show you what is actually required to hold a constant bank angle, but don't worry, it's not fundamentally different. Just before you reach your desired heading, to allow for the time taken to roll the aircraft back to wings level, you turn the control wheel to the right. The left aileron moves down. This increases the camber of the wing in the vicinity of the aileron and increases lift. At the same time, the right aileron moves up. This decreases the camber of the wing in the vicinity of the aileron and decreases lift. The difference in lift on the two halves of the wing generates a rolling moment to the right, and aircraft will start to roll to the right, in this case back towards wings level. Just before you get to wings level, you neutralize the ailerons, which reduces the rolling moment to zero, and the aircraft will stop rolling. We will now look at the byproducts of rolling the aircraft about the longitudinal axis. The first consideration is our old favourite, aerodynamic damping. We will assume a constant IAS, but you should remember that aerodynamic damping is a function of TAS, not IAS. Please note the true airspeed vector. Only the downgoing wing is illustrated. The opposite will take place on the upgoing wing, but will have the same effect. The aileron has been moved up to generate a downforce. The aircraft will begin to roll. This wing is now moving downwards in addition to moving forwards. The black vector represents the downward speed of the wingtip. The blue vector represents the effective airflow and is the resultant of the TAS and the rate of roll. The angle between the TAS vector and the effective airflow vector is the change in effective angle of attack. This increase in effective angle of attack on the downgoing wing generates an upforce called aerodynamic damping. Aerodynamic damping reduces the rate of roll. When the aircraft stops rolling, there is no longer any aerodynamic damping. At a constant IAS, a higher altitude will require a higher TAS. The same aileron deflection will produce the same aileron force because the IAS is constant. But because the TAS is higher, the increase in effective angle of attack is smaller. This results in reduced aerodynamic damping and consequently a higher rate of roll. To achieve the same rate of roll with an aircraft of greater wingspan, the ailerons must be deflected through a greater angle. Because the wingtip is further from the CG, the wingtip has to move downwards through the air faster, increasing aerodynamic damping. The second byproduct of rolling the aircraft about the longitudinal axis is adverse aileron yaw. The objective when rolling the aeroplane is usually to turn to a different heading, as previously described and here animated. If both ailerons move through the same angle from neutral, the downgoing aileron will generate more drag than the upgoing aileron. Parasite drag is the same on both, but the downgoing aileron would generate an increase in induced drag, and the upgoing aileron would generate a decrease in induced drag. Only the downgoing aileron is illustrated. The adverse aileron yaw illustrated here is greatly exaggerated for clarity. The result of adverse aileron yaw is a yawing moment in the opposite direction to that required. If you roll the aircraft, in this case to the left, a yawing moment to the right is generated. This is both aerodynamically inefficient and physically uncomfortable for all on board. It must be pointed out, it's only during the roll, while the ailerons are displaced from neutral, that adverse aileron yaw occurs. Aircraft designers can reduce adverse aileron yaw in several ways. The first method we will look at is differential ailerons. The downgoing aileron moves through a smaller angle than the upgoing aileron. This reduces the difference in drag. Nearly all aircraft have differential ailerons. The second method of adverse aileron yaw reduction we will look at is the freeze aileron. The leading edge of the upgoing aileron projects below the wing, increasing the parasite drag. The downgoing aileron does not project into the airflow. It can be seen that freeze ailerons also reduce the difference in drag. Freeze ailerons are usually used together with differential ailerons on small and medium-sized aircraft. The third method of adverse aileron yaw reduction we will look at is aileron rudder coupling. Aileron-rudder coupling is usually used on large modern aircraft. There is an interconnection between the ailerons and the rudder, such that, when a roll input is made, the rudder is automatically deflected to cancel the adverse aileron yawing moment. Note, the difference in drag from the ailerons still exists. The fourth and final method of adverse aileron yaw reduction we will look at is roll spoilers. Most modern high-speed jet transport aircraft use roll spoilers to assist the ailerons with roll control. The operation of roll spoilers will be fully explained later. As you can see, the spoiler surface comes up on the side with the upgoing aileron, matching the drag on the two sides, and thus reducing adverse aileron yaw to a negligible amount. You have seen that ailerons are mounted as far outboard as possible to give the longest arm from the CG. This is done to minimize aileron size and the angular displacement required for a given rolling moment. Unfortunately, this wingtip location also maximizes the ability of the ailerons to twist the wing. The downgoing aileron increases the camber of that part of the wing with the objective of generating an up force on the wingtip to roll the aircraft. But the wing twist will decrease the wing incidence and reduce the roll force. If we consider a higher IAS, the wing twist will be greater for the same aileron displacement, further reducing the rolling moment. Eventually, an IAS will be reached when the effect of the aileron is cancelled by the effect of the wing twist and the aircraft will not roll when commanded by the pilot. Higher IAS will give a larger rolling moment from the wing twist than from the ailerons, and the aircraft will roll in the opposite direction to that commanded by the pilot. This phenomenon is called high-speed aileron reversal, and would limit the maximum operating speed of the aircraft. Making the wing stiffer to increase the IAS at which high-speed aileron reversal occurs is not an option because it would increase the structural weight of the aircraft. Instead, another pair of ailerons is fitted further inboard on a stiffer part of the wing. These are called inboard ailerons. At low indicated airspeeds, you can see that both the inboard and outboard ailerons operate through their full angle of displacement when commanded from the flight deck. We can see that the aeroplane is flying slowly because the trailing edge flaps are down. After takeoff, the aircraft is accelerated, and when the IAS reaches the speed at which the aircraft can fly safely with the flaps up, the flaps are retracted. As the flaps retract, a mechanism reduces the input to the outboard ailerons. So, as the trailing edge flaps retract, the outboard ailerons will move through a progressively smaller angle than the inboard ailerons. With the flaps fully retracted, the outboard ailerons no longer move, only the inboard ailerons. To complete your understanding, please note the following. The reduction in outboard aileron movement with decreasing trailing edge flap angle is referred to as locking out the outboard ailerons, as in, flap retraction locks out the outboard ailerons. Outboard ailerons can also be called low-speed ailerons. Inboard ailerons can also be called high-speed ailerons or all-speed ailerons. The outboard low-speed ailerons only work when the trailing edge flaps are down. When the trailing edge flaps are retracted, the outboard low-speed ailerons are locked out. The inboard high-speed, all-speed ailerons always work. Please review this scene several times to ensure you remember the complexities. You have previously been shown that flaps are fitted to the trailing edge of the wing, and you have now been shown that ailerons also occupy part of the wing trailing edge. The resulting reduction in flap area reduces the efficiency of the flaps. On large, modern, high-speed jet transport aircraft, this reduction in flap area is a significant disadvantage, so design changes have been made to make the ailerons also work as flaps. Hence the name flaperons. When the trailing edge flaps move down, the flaperons also go down. Now the whole wing area has its camber increased, thus maximising the effect of the flaps to increase CL max. But what about lateral control? Think of the flaperon position with the flaps down as a new neutral datum. When a roll input is made, the flaperons move up and down from this new neutral datum and still provide a change in lift on both halves of the wing for roll control. Spoilers are usually fitted to large, modern, high-speed jet transport aircraft to help the ailerons with roll control. Spoilers are movable panels on the top of the wing. They are hinged at their forward edge and activated hydraulically. When raised into the airflow, spoilers spoil or disturb the airflow, thus decreasing lift and increasing drag. Roll spoilers are activated by the control wheel and move up on the side with an upgoing aileron, proportional to aileron displacement. You can see that the roll spoilers on the side with the downgoing aileron remain flush. Even with the flaps up, the roll spoilers continue to assist the ailerons with roll control. Roll spoilers have several advantages over ailerons. Roll spoilers eliminate adverse aileron yaw. Roll spoilers do not twist the wing. Roll spoilers do not develop flutter. Roll spoilers do not take up space on the trailing edge, leaving it usable for flaps. Because spoilers work by reducing lift, their use will always result in a net loss of lift on the wing. This is not normally a significant disadvantage. When selected by the pilot, speed brakes increase drag. The use of speed brakes increases deceleration and/or gives an increase in the rate of descent without increasing the IAS. There are two common methods of mounting speed brakes: wing-mounted or rear fuselage-mounted. Ideally, speed brakes should give an increase in drag without affecting lift or causing a change in pitching moment. Fuselage-mounted air brakes are best suited to do this, but are only occasionally used on civilian transport aircraft. Modern high-speed jet transport aircraft usually use the spoiler surfaces on the wing as speed brakes. There is a speed brake lever on the flight deck that, when selected to up by the pilot, extends the speed brake symmetrically, thus increasing the drag. There are no speed restrictions for the operation of speed brakes. However, the design of the hydraulic operating system does give a blowback facility. That is, for the same selection from the flight deck, increasing IAS restricts the speed brake angle of deflection into the airflow. This prevents excessive buffeting at higher IAS. While being used as speed brakes, the spoiler surfaces will continue to assist the ailerons with roll control. To illustrate this, we will pull partial speed brakes. Now, when a roll input is made, the spoiler surfaces will move up or down about the datum of the speed brake selection. In flight, the maximum angle to which the speed brakes can deploy is restricted to prevent excessive loss of lift and excessive buffeting. But as soon as the aircraft touches down, there is a need to remove as much lift from the wing as possible so that the wheel brakes will have maximum effectiveness. In addition, there is a need to increase drag as much as possible. After touchdown, the air-ground logic system senses the aircraft is on the ground and removes the restriction on speed brake angle. When full speed brakes are demanded from the flight deck with the aircraft on the ground, the speed brakes deploy to a much larger angle than in flight. This is called lift dump. To fly an aircraft in a steady state, climb, cruise or descent, the pilot must apply the stick force necessary to hold the aircraft in the required attitude. In other words, the pilot must hold the aircraft in a state of equilibrium, or trim. The stick force the pilot may need to apply to maintain equilibrium can be quite high, and all human beings find it impossible to maintain a constant stick force for more than a few seconds. Therefore, a means of reducing the stick force to zero is incorporated in all aircraft. This is known as trimming the aircraft. There are several devices used to trim an aircraft. The most common is the trim tab, which is the first trimming device we will look at. You can see the cockpit controls for trimming, plus the tailplane, the elevator and the elevator trim tab. The trim tab is the small red aerofoil mounted on the trailing edge of the blue elevator. The majority of smaller aircraft have an exposed trim wheel in the cockpit, which the pilot can use to move the trim tab. The trim wheel works in a logical way. Move it down by its rear edge to trim the aircraft nose up, as you will see shortly. Some small aircraft and all modern jet transport aircraft have trim switches mounted on the control wheel. The trim switches also work in a logical way. Move them down to trim the aircraft nose up, again, as you will see shortly. All control movements in the following animations are exaggerated for clarity. Let's consider an aircraft with a forward CG, a nose-heavy aircraft. To maintain equilibrium, the pilot must move the stick aft to move the elevator up. Holding the elevator up requires a pull force. The aircraft is in equilibrium, in trim. To reduce the stick force to zero, the pilot must move the trim switches down, or move the rear edge of the trim wheel down. Making this trim input moves the trim tab down, away from neutral with the elevator. As the trim tab moves down, an aerodynamic up force is generated on the elevator trim tab. Eventually, the moment from the trim tab becomes equal to the moment from the elevator. The stick force has been reduced to zero and the aircraft has been trimmed. Please note, when using a trim tab to trim an aircraft with a forward CG position, the cockpit control remains displaced aft from neutral. Your flight instructors will teach you to put and then hold the aircraft in the required attitude using the flying controls. Only after you have achieved equilibrium should you use the trimming devices to reduce the stick force to zero. To fly the aircraft using the trim to change the attitude is bad practice. Let us now have a look at one of the disadvantages of the trim tab: reduced aircraft nose-up pitch authority with a forward CG. Maximum elevator travel is limited by the primary stops. In this example, let's assume the elevator can move 30 degrees up from neutral and 30 degrees down from neutral, a total travel of 60 degrees. 60 degrees total elevator travel will always be available. Let's assume, once again, because of a forward CG, there is a requirement for the pilot to trim the aircraft nose up. You can see that there is reduced aircraft nose-up pitch authority from the elevator with an aircraft trimmed with a forward CG. This reduction in aircraft nose-up pitch authority might make it difficult for the pilot to flare the aircraft for landing. Some trim tabs are not adjustable in flight, but can be adjusted on the ground by maintenance personnel to correct a permanent out-of-trim condition. They are usually only fitted on the ailerons and rudder of light aircraft. When the early jet transport aircraft were being designed in the 1950s, it was found that an elevator trim tab did not provide enough pitch trim authority for the increased speed range and CG range required. So an alternative method of pitch trim had to be used: the variable incidence trimming tailplane. The variable incidence trimming tailplane is still in use on today's jet transport aircraft. You can see that the trim input controls in the cockpit are the same, but now pitch trim is accomplished by changing the incidence of the whole tailplane. As before, for pitch control, an elevator mounted on the trailing edge of the tailplane is still used. For pitch trim, the incidence of the tailplane is changed with the screw jack. The screw jack is mounted inside the rear fuselage and is driven by motors mounted on a gearbox at the base of the screw jack. Once again, we will consider an aircraft with a forward CG, a nose-heavy aircraft. As before, to maintain equilibrium, the pilot must move the stick aft to move the elevator up. Holding the elevator up requires a pull force. The aircraft is in equilibrium, in trim. To reduce the stick force to zero, the pilot must move the trim switches down. Making this trim input drives the screw jack, which in this case decreases the incidence of the tailplane. Please note that while the tailplane is trimming, the elevator is being returned to neutral. The decreased incidence of the tailplane has replaced the downforce from the elevator. The aircraft is still in equilibrium, but with zero stick force. The aircraft has been trimmed. When the trim position is reached, the elevator is faired with the trimming tailplane. The cockpit pitch control has also been returned to its neutral position. Let's now have a look at the advantages of the variable incidence trimming tailplane over the trim tab. The first advantage is that compared to a trim tab, it is much more powerful and has the ability to trim for larger CG and speed ranges. However, there is a drawback associated with the increased power of the variable incidence trimming tailplane. If the tailplane were to change its incidence without being commanded, the pilot could not stop the aircraft from pitching out of control because the elevator is much smaller than the tailplane. This is known as stabilizer trim runaway, and safeguards have to be incorporated in the design to prevent it. Firstly, there is a mechanical brake inside the gearbox which engages and immobilizes the screw jack whenever a trim command from the flight deck is absent. This prevents the airflow from moving the stabilizer. Secondly, there are two switches on the control wheel in the cockpit. The switches are mounted side by side and are easily moved together by the pilot's thumb when required. The switches are wired in series so that if the contacts of one switch do not break the circuit when the pilot releases the switches, the other switch will break the circuit to stop the trim from running. There is also a warning light that illuminates to tell the pilots that the trim is running, and on the Boeing 737, which has exposed trim wheels, their clanking noise when rotating will be an unmistakable warning. If the stabilizer trim does run away, all inputs to the screw jack drive can be removed by emergency shut-off switch action on the flight deck. The second advantage of the variable incidence trimming tailplane is that there is less aerodynamic drag when the aircraft is in trim, a big advantage in the cruise. The third advantage is that trimming does not reduce the effective range of pitch control. As before, the total range of the elevator is limited by the primary stops. But because the elevator is faired with the tailplane when trimmed, both full up elevator and full down elevator from neutral is always available to the pilot for pitch control. The only disadvantage of the variable incidence trimming tailplane is that it is heavier than a trim tab and more complex. This disadvantage is far outweighed by its advantages. To maximize aerodynamic efficiency in the cruise, reducing the trim drag to an absolute minimum will significantly increase the distance that can be flown using a given amount of fuel. The illustration shows an aircraft in the cruise with the tailplane trim being used to generate the normal tail down force. As you know, lift must balance the aircraft weight plus any tail down force, so induced drag will be increased. Plus the tail down force is an aerodynamic force, which will further increase induced drag. These together make up the trim drag. We have seen that the variable incidence trimming tailplane gives less trim drag than the trim tab. Now we will consider the benefit from moving the aircraft CG in flight. In this case, we need to move the CG rearwards. This is done by pumping fuel from the wing tanks to a trim tank at the rear of the aeroplane, usually fitted inside the fin or the tailplane. Pumping the fuel to move the CG is an automatic function and in practice is a slow and almost continuous operation. But as usual, we have exaggerated the illustration for clarity. Please note that the trim switches are not being used, but the tailplane is changing instance to maintain equilibrium as the fuel is being transferred from the wing to the tail, another automatic function. With power flying controls, there is no feedback of aerodynamic forces to the cockpit controls. The stick forces are generated by the artificial feel system. Therefore, when the aircraft is being trimmed, the trim system will have an input to the artificial feel system that reduces the stick forces as appropriate. We have now reached the end of our study of flying controls. Please feel free to review the lessons as many times as you like, because they contain a lot of detail in which the examiners are interested. In this series of lessons on flight mechanics, you'll be studying the forces acting on an aircraft in flight, and the response of the aircraft to those forces. For an aircraft to be in steady, unaccelerated flight, the following conditions must exist. Forces acting downwards must exactly balance the forces acting upwards, and the forces acting backwards must exactly balance the forces acting forwards. In addition, the sum of all moments must be zero. When all these conditions are met, the aircraft is in a state of equilibrium. In straight and level flight, there are four forces acting on the aircraft: lift, weight, thrust and drag. Weight acts through the centre of gravity, the CG, vertically downwards towards the centre of the Earth. Alternatively, weight can be said to act parallel to the force of gravity. Lift acts through the centre of pressure, CP, normal or at 90 degrees to the flight path. Drag acts backwards, parallel to the flight path. And thrust, for the purposes of this lesson, although not strictly true, can be said to act forwards, parallel to the flight path. For an aircraft to be in steady level flight, a condition of equilibrium must exist. This unaccelerated state of flight is achieved with the aircraft trimmed, with lift equal to weight, and the throttles set for thrust to equal drag. For steady level flight, then, the opposing forces must be equal. The proportion of the lift force to the drag force, known as the lift-drag ratio, for most modern aircraft is between 10 and 20 to 1. In simple terms, this means that lift is 10 to 20 times greater than drag. The lines of action of thrust and drag usually lie fairly close together, so the moment of this couple is small and will be disregarded for this study. The positions of the CG and CP are variable, but under normal circumstances will not be coincident. The CP will move forward as angle of attack increases, and will usually stay aft of the CG, unless the design allows the tailplane forces to stabilize the moments adequately with a forward CP. The CG will move as fuel is used, usually forward, but will usually, on conventional aircraft, remain in front of the CP. The function of the tailplane and elevator, or the stabilator, depending on the design, but referred to generally as the tailplane for simplicity, is to maintain equilibrium in pitch by supplying the force necessary to counter any moments resulting from CP and CG movement. With the CP providing a pitch down moment being behind the CG, the tail surfaces must provide a downforce. If the tailplane is producing a balancing force, this will add to or subtract from the lift required to balance the weight. For a downforce, the usual situation, lift must equal the weight plus the tailplane downforce, and for an upforce, lift must equal weight minus the tailplane up force. For steady level flight at a constant weight, the lift force required will be constant, and at a steady speed, the wing will produce this lift at a given angle of attack. However, if the speed is changed, the angle of attack must change to maintain the same lift. As the lift changes with the square of the speed, but in direct proportion to the angle of attack, the angle required for constant lift will vary as shown on the graph on the screen. The minimum possible level flight speed, Vs, for any given lift force is achieved at the critical or stall angle of attack. For steady level flight at a constant speed, the thrust must equal the drag. Drag increases with speed above minimum drag speed, Vmd, and so, to maintain a higher speed, the thrust must be increased by applying more power. To fly the speed at point A requires a thrust of T1, and to fly at speed B requires a thrust of T2. If the thrust is increased to T2 when the aircraft is at point A, the thrust will be greater than the drag, and the aircraft will accelerate in proportion to the excess thrust AC until it reaches point B, where the thrust and drag are again equal. If T2 is the maximum thrust available, then the speed at B will be the maximum speed achievable in level flight. In this second lesson on flight mechanics, we examine the relationship of the forces in a straight, steady climb. As in straight and level flight, the forces are lift, normal to the flight path, thrust and drag, parallel to it, and weight, parallel to the force of gravity. With the aircraft in a climb at an angle to the horizontal, the Greek letter gamma denoting the climb angle, the weight vector is inclined backwards relative to the flight path at the same angle as the climb flight path is to the horizontal. Note that the JAA objectives use the Greek theta instead of gamma for the climb angle. Weight, W, can be resolved into two components, one opposing lift with a value of W times cosine gamma, and the other acting in the same direction as drag with the value of W times sine gamma. This backwards component of weight, when added to the drag, creates a requirement for more thrust to re-establish equilibrium for steady flight. In a straight steady climb, lift is less than weight, because lift only has to support a proportion of the weight, with the proportion decreasing as climb angle increases. The remaining proportion of weight is supported by thrust. The ultimate illustration of this would be a vertical climb, where no lift is required, but lots of thrust is. You can see that, for a straight steady climb, the thrust required is greater than the drag, because the backward component of weight is added to the drag force. The ability of an aircraft to climb depends on the excess thrust available after opposing aerodynamic drag. The smaller the drag for a given thrust, the greater the ability to climb. For example, drag is less with flaps up, giving a larger climb angle or climb gradient. The climb angle achievable depends on excess thrust, thrust minus drag, and the weight. As both drag and thrust vary with IAS, the excess thrust will be greatest at one particular speed. This is the speed for the best angle of climb, known as Vx. This graph shows the variation of thrust with speed for a jet aircraft, where thrust is fairly constant with speed. And Vx is close to or coincident with Vmd. With the propeller-driven aircraft, where thrust decreases with speed, the maximum difference will usually occur at a speed below Vmd. The drag produced by an aircraft at a given IAS is not affected by altitude or temperature, but higher weights will increase drag, thus reducing the excess thrust available. Climb angle will therefore decrease with increasing weight. Increases in both altitude and temperature will cause a reduction in the thrust available from the engine or engines, which also reduces excess thrust. Climb angle will therefore reduce with increasing weight, altitude and temperature. In a descent, the disposition of the four forces, lift, weight, thrust and drag, will depend on how much power is used, but in all cases the lift vector is inclined forwards with the aircraft in a nose-down attitude. And the weight vector, as in the climb, can be split into two components. One, W cosine gamma, where gamma is the angle of descent, acts perpendicular to the flight path and is balanced by lift. And the other, W sine gamma, acts forward along the flight path and adds to the thrust, which is reduced for the descent. This added component restores the thrust-drag balance. If the nose of the aircraft is lowered with a constant thrust setting, the increased forward component of weight acting forward along the flight path will cause an increase in IAS. This increased IAS will result in a rise in drag, which will eventually balance the weight element, at which point equilibrium is restored and the speed will stabilise. If the throttles are closed, the thrust force is removed and a larger forward component of weight is required to balance drag and maintain a constant IAS. This is achieved by lowering the nose of the aircraft to increase the descent angle, gamma. To sum up the arrangement of forces in a descent, lift is less than weight because lift only has to balance the component of weight perpendicular to the flight path, W cosine gamma. And thrust is less than drag because weight is giving a forward component in the same direction as thrust, W sine gamma. The total reaction of lift and drag opposes the weight vector. There may be emergency situations, typically a pressurization failure at high altitude, in which it is necessary for the aircraft to descend as quickly as possible. The high rate of descent necessary can be achieved by several means, which are usually used in combination according to the circumstances. The first action would normally be to close the throttles to minimize thrust and simultaneously lower the nose to initiate the descent. Drag can be increased by extending speed brakes or spoilers, and if the speed has to be kept low, say with structural failure or an unlatched door, the landing gear and possibly the flaps can be lowered as well, observing the appropriate limiting speeds. If there are no speed restrictions, the gear would be left up and the nose lowered to increase the speed up to the limiting IAS, VMO, or Mach number, MMO. If the initial limit is MMO, then IAS will be increasing as the aircraft descends, and at some stage the nose will have to be raised to keep the speed from exceeding VMO. The rates of descent achieved in an emergency descent can be quite high and would require a fair amount of anticipation by the pilot to level off at the required altitude. In a glide, that is, a descent without power, there is no thrust to provide the propulsive force and balance the drag. This is done by the component of weight acting along the flight path. In a glide, there are only three forces acting on the aircraft: lift, weight and drag. The forward component of weight, W sine gamma, is a product of the descent angle gamma. The greater the descent angle, the greater will be the forward component of weight. This component must balance drag for the aircraft to be in a steady glide. It follows that, if drag is reduced and lift remains constant, the required balance of forces can be achieved at a smaller descent or glide angle. The angle of descent in the glide is a function only of the lift-drag ratio. The angle will be at its least when the lift-drag ratio is at its greatest, which is at the optimum angle of attack, which in turn corresponds to the minimum drag speed, VMD. It is important to remember that at speeds above or below VMD, the glide angle will be steeper. So, the maximum distance in a glide will be achieved when the aircraft is flown at its maximum lift-drag ratio at VMD. The maximum lift-drag ratio is independent of weight. Provided the aircraft is flown at its optimum angle of attack, the glide angle and the still air glide distance will be unchanged, whatever the weight. However, the speed corresponding to the optimum angle of attack, minimum drag speed, will change with weight. VMD increases as weight increases. A higher weight would give an increased forward component of weight, and the aircraft would accelerate towards the higher VMD, with lift increasing and drag increasing until it balances the higher weight component. Equilibrium is re-established at the same maximum lift-drag ratio, but at a higher IAS. At a higher weight, the aircraft will glide the same distance in still air, but at a higher speed, and consequently the rate of descent will be higher. The glide angle will determine the distance that the aircraft can glide for a given change of height. This distance would only be achieved in still air. If there is a wind, the ground speed will be affected, and so the distance will change. In a headwind, the ground distance will be reduced. And in a tailwind, the ground distance is increased. The maximum lift-drag ratio of an aircraft will only be obtained in the clean configuration. Extension of flaps, spoilers, speed brakes or landing gear will reduce the maximum lift-drag ratio and give a steeper glide angle, thus reducing glide range. The minimum rate of descent in the glide is obtained at the indicated airspeed, IAS, which requires minimum power, VMP. Flying at VMP in a glide will enable the aircraft to stay airborne as long as possible, but will not result in the shallowest glide angle or best glide range. As shown in the graph on the screen, VMP is a lower IAS than VMD. Wind speed and direction have no effect on the rate of descent. One way of portraying the relationship of VMP and VMD is shown in the diagram on the screen, which is known as the whole aeroplane CL/CD polar curve. This lesson concludes the topic of descending. The next lesson continues with the flight mechanics of turning. This lesson on the mechanics of flight deals with the forces and factors involved in flying a level, balanced turn. For an aircraft to change direction, it requires a force that will deflect it effectively towards the centre of the arc around which it will fly. This force is called the centripetal force, that is, centre-seeking. As you can see from the diagram, with the aircraft banked, the lift vector is also tilted, and it is the horizontal component of lift which causes the aircraft to turn by providing the centripetal force. If the aircraft is banked and the angle of attack is maintained at the same value as in straight flight, the vertical component of lift would be insufficient to balance the weight, and the aircraft would descend. As the angle of bank increases, the angle of attack must be increased to achieve a greater total lift, with the vertical component being large enough to balance the weight and maintain level flight, and the horizontal component providing the centripetal force. In a steady level turn, if thrust is ignored, lift provides the force to balance weight and the centripetal force to turn the aircraft. If two different aircraft can fly at the same TAS and angle of bank, their radius of turn will be the same, since radius of turn is independent of weight or aircraft type. However, not all aircraft can reach the same angle of bank at the same TAS. With a heavier aircraft, the vertical component of lift required increases, but the centripetal force necessary to maintain the same radius of turn also increases in the same proportion. The lift required, although greater, has the same inclination to the vertical as before, and the bank angle is the same. Rate 1 is 180 degrees per minute, or 3 degrees per second, and rate 2 is double that, at 360 degrees per minute, or 6 degrees per second. Rate 1 is the standard turn rate for instrument flight rules. A useful rule of thumb for calculating the angle of bank required to achieve a rate 1 turn is true airspeed over 10 plus 7. For example, at 150 knots TAS, the bank required is 22 degrees. There are various factors worth remembering when considering the relationships between rate of turn, radius of turn, TAS and bank angle. At a constant TAS, increasing the bank decreases the turn radius and increases the rate of turn. To maintain a constant rate of turn, more speed requires more bank. At a constant bank angle, increasing speed increases the turn radius and decreases the rate of turn. A steeper bank angle reduces radius and increases rate of turn, but produces a higher load factor. Load factor is directly related to bank angle, so the load factor for a given angle is the same at any speed. Reducing TAS reduces turn radius and increases rate of turn without increasing the load factor. A given TAS will give a specific rate and radius of turn in any aeroplane. If TAS is doubled at constant bank, radius is quadrupled. If TAS is doubled at constant bank, rate of turn is halved. To appreciate the last two statements, remember that radius is proportional to speed squared, and rate is speed over radius, so the change in the rate of turn is v times 2 over radius times 4, which is half. As you have already seen, in a bank turn, the lift must be increased to provide not only centripetal force from the horizontal component, but also a vertical component sufficient to balance the weight. As bank is increased, the total lift required, and thus the load factor as well, must increase to maintain the vertical component's value for a level turn. The load factor, or G in common parlance, is the relationship between total lift and weight, can be expressed in the equation load factor N equals lift over weight, which equals 1 over cosine phi, which equals secant phi. The trigonometry of this is fully explained in the lesson on stalling. The relationship can also be shown graphically, and the chart is valid for any aircraft. It can be seen that the curve is exponential, that is, the G increases at an increasing rate with angle of bank. The point to remember is that in a level turn, load factor is a function only of bank angle. Constant bank, constant G. There are certain limitations which can restrict the performance of an aircraft in the turn. For each aircraft type, there is a design limit load factor. For modern high-speed jet transports, the limit is 2.5 G. From the graph, it can be seen that this occurs at 67 degrees of bank, which will determine a turn radius dependent on the TAS. This will be the minimum radius possible without exceeding the G limit. If speed is kept constant but bank is increased, the angle of attack must be increased to provide the further extra lift required. At the stalling or critical angle, no further increase in bank or decrease in radius is possible. Since stalling speed varies with weight and G, this limit will be a function of those two factors. The extra lift required during a turn will result in greater induced drag, so to maintain the straight flight speed, more thrust is required. As more bank is applied, more thrust is needed, and eventually maximum thrust will be reached. At this point, it is not possible to increase the bank or decrease radius. Whether this thrust limit or the maximum load factor is reached first will depend on the G limit and the thrust available. If the thrust available is adequate, the minimum radius of turn occurs at the intersection of the stall limit and the strength or load limit. The speed at this point is VA, the maximum manoeuvring speed. The heavier the aircraft, the greater will be the minimum radius of turn. There are several factors which can cause uncoordinated flight: adverse aileron yaw, engine torque, gyroscopic precession, and spiral slipstream from the propeller, and asymmetric flight, plus, of course, unbalanced control movements by the pilot. Uncoordinated flight exists when the aircraft is side-slipping, and indication to the pilot of side-slip is given by the inclinometer portion, the ball, of the turn coordinator. The miniature aeroplane indicates rate and direction of turn, but not angle of bank. The level index shows when the aircraft is not turning, but not necessarily when the wings are level. When the miniature aeroplane's wingtip is against either of the rate 1 indices, the aircraft is turning at rate 1 or 3 degrees a second. A reminder of rate 1 is below the ball, 2 min referring to the fact that a full 360-degree turn at rate 1 takes 2 minutes. The inclinometer, as already mentioned, shows the pilot if his turn is balanced. Coordinated or balanced flight is maintained by keeping the ball centered between the reference lines with the rudder. If the ball is out to one side, rudder pressure should be applied in that direction. Stepping on the ball is a useful way to remember which way to push on the rudder pedals. Side-slipping towards the center of the turn moves the ball to the inside of the turn, and vice versa. Changing the angle of bank can also restore balanced flight, but will alter the rate of turn. The second instrument here shows an uncoordinated turn to the right, with the aircraft side-slipping towards the center of the turn, a slipping turn. Right rudder or less bank would balance the turn. The third instrument also shows an uncoordinated turn to the right, with the aircraft side-slipping towards the outside of the turn, a skidding turn. Left rudder or more bank would balance the turn. This concludes the lessons on turning flight mechanics. The flight mechanics series of lessons concludes with the next lesson on asymmetric flight.
When an engine fails on a multi-engine aircraft, there will be a decrease in thrust, and on propeller-driven aircraft, an increase in drag on the side with the failed engine. The results will be that the airspeed will decay, the nose will drop, but most significantly, the aircraft will yaw immediately towards the failed or dead engine. Controlling that yaw is of vital importance. The yawing moment is the product of thrust from the operating engine multiplied by the distance between the thrust line and the center of gravity, the thrust arm, plus any drag from the failed engine multiplied by the distance between the engine centerline and the CG. The strength of the yawing moment will depend on 3 factors. How much thrust the engine is developing, depending on throttle setting and density altitude, the distance between the thrust line and the CG, the thrust arm, and the drag from the failed engine. If rudder is applied to counter the yaw, it will generate a moment which is the product of the rudder force multiplied by the distance between the rudder center of pressure and the CG. At this initial stage, the pilot's ability to counteract the asymmetric yawing moment will depend on the rudder displacement, which affects the rudder force, the IAS, also affecting the rudder force, and the CG position, affecting the rudder arm. Under a certain combination of conditions, control difficulties can arise under asymmetric thrust. Let us assume that the live engine is at a high thrust setting, the rudder is at its full deflection, and the CG is at its rearmost limit, that is, giving the shortest rudder arm. If the IAS, the dynamic pressure, is just sufficient to produce enough rudder moment to counter the yawing moment, there will be no yaw. However, any decrease in the IAS will reduce the rudder force, and the aircraft will yaw uncontrollably towards the dead engine. This uncontrollable yaw, in this case to the left, will cause the aircraft to roll uncontrollably, also to the left, owing to the greater lift on the starboard wing whilst yawing left. the aircraft will enter a spiral dive to the left, which at the low speed would be impossible to stop with flight controls alone. If this were to happen close to the ground, the result would be disastrous. In these extreme circumstances, the only way to regain control would be to minimize thrust on the live engine or engines, to remove the yawing moment and permit a controlled forced landing. Thus, there is a minimum IAS at which directional control can be maintained under a given set of conditions after engine failure in a multi-engine aircraft. This minimum speed, which will vary with temperature and density, is called VMC, minimum control speed. There are different speeds for ground and air engine failures, and for different configurations. These are described fully in due course. One of the factors influencing the yawing moment following engine failure in a multi-engine aircraft is the length of the thrust arm. That is, the distance from the CG to the thrust line of the operating engine. In the case of a prop-driven aircraft, the length of the thrust arm is determined by the asymmetric blade effect of the propeller. At positive angles of attack, the thrust line of a propeller rotating clockwise when viewed from the rear is displaced to the right. This is because the downgoing blade generates more thrust than the upgoing blade. This phenomenon is fully explained in the lesson on propellers. If both propellers rotate clockwise, the right or starboard engine's thrust arm will be longer than that of the port engine. So, if the left engine fails, the thrust of the right engine acts through a longer thrust arm and generates a bigger yawing moment, and a higher IAS would be necessary to maintain directional control than if the right engine failed. Thus, at a given IAS, the given situation would be more critical if the left engine failed. The critical engine, then, is the one that would give rise to the biggest yawing moment if it were to fail. To overcome the disadvantage of having a critical engine on smaller twins, their propellers may be geared to rotate in opposite directions, or counter-rotate, with the downgoing blades inboard, giving both engines the shortest possible thrust arm. Bigger turboprop aircraft, such as the King Air and larger, will have co-rotating propellers, turning in the same direction. In the case of four-engine jets, either outboard will be a critical engine. Although the moments are balanced in the diagram on screen, the forces are not. The unbalanced side force from the rudder can be balanced in two ways, either with the wings level or by banking towards the live engine, which in a marginal situation is the preferred method, as will be explained shortly. In the wings level method, rudder is used to prevent yaw, and the ailerons are used to keep the wings level. Yawing towards the live engine gives a side-slip force on the keel surfaces behind the CG opposite to the rudder. The turn indicator will be neutral, and the ball central. This paradox of asymmetric thrust, where the aircraft is side-slipping but the ball is in the middle, is the exception to the rule of balanced coordinated flight. The advantage of the wings level method of balancing the forces is the strong horizontal visual and instrument reference available to the pilot. The disadvantages are that extra parasite drag from the side slip will reduce climb performance, which would be vital when close to the ground, and that there is a possibility of fin stall if the side slip angle is excessive, which would worsen directional control problems considerably. It is more aerodynamically efficient to balance the rudder side force by banking towards the live engine. so that lift gives a lateral component to oppose the rudder force. The bank angle must be restricted to 5 degrees to prevent significant reduction of the vertical lift component. Banking towards the live engine also reduces the side force on the fin from side slip, which effectively reduces the yawing moment and gives more rudder authority to stop the yaw. The cockpit indications on the turn coordinator will be no turn, but the ball will be out to the right. This is the corollary of the indication in the wings level method, there being no side slip, but the ball is not central. The advantage of this method is its better aerodynamic efficiency, without the side slip drag penalty, making it better for use in marginal situations. But it is more difficult than the wings level method for the pilot to fly consistently. In practice, however, pilots will tend to use the wings level method initially, with its simpler handling references, usually combining the techniques only under marginal conditions, when the better aerodynamic efficiency of bank to the live engine or engines is of greater importance. The rolling and yawing moments, and the power of the flight controls to balance them, will determine the controllability of an aircraft with asymmetric thrust. These rolling and yawing moments are affected by thrust on the live engine. Yawing moment increases with thrust, and the further out the engine is mounted on the wing, the larger the moment. Thrust is greatest at low speed and maximum power. Thrust reduces with increases in altitude and temperature, that is, higher density altitudes. The worst case for an engine failure is thus after takeoff at sea level on a cold day. The drag from the propeller itself will depend on whether it is stationary, windmilling, or feathered, but there will always be some contribution to the yawing moment. If the propeller is stationary, it is generating some drag from the blades, which could be at a relatively large angle to the airflow, but no torque. A windmilling propeller will produce a large amount of drag, being driven by the relative airflow, generating both drag and torque. The propeller will also have the load of turning the dead engine, unless an automatic decoupling device is fitted. A feathered propeller will cause the least possible drag. There is no torque, since it is not rotating, and the parasite drag is at a minimum with the blade's edge onto the airflow. If both engines rotate clockwise, the right engine has a longer thrust arm, and failure of the left engine gives a greater yaw moment. This asymmetric blade effect, or P factor, is absent with counter-rotating and contra-rotating propellers, and of course on jets. The aircraft rotates around its CG, but its fore and aft position has no effect on the yawing moment from a failed engine. The rudder arm is affected, however, with an aft CG giving the worst case with the least rudder effectiveness. When the engine turns the propeller, the equal and opposite reaction tries to turn the engine the other way, the torque effect being to roll the aircraft to the left. If the left engine were to fail, it would result in a bigger rolling moment to the left. As with asymmetric blade effect, this happens only with co-rotating propellers. Note, however, that if the propeller is windmilling, the torque is reversed, but is much less than the torque of the live engine. Any propeller-driven multi-engine aircraft will suffer a loss of lift from the slipstream-induced faster airflow over the wing behind the failed engine. The reduction in total lift will give a tendency to descend, but more importantly, a roll towards the failed engine. The roll is exacerbated if flaps located behind the failed engine and its counterpart on the live side are down, owing to the higher CL. If the aircraft is being flown wings level asymmetric, it will be side-slipping, and the dihedral of the forward wing, in this case the port or left wing, will generate more lift, compensating in part for the loss of lift from the slipstream. Any weight increase will require a higher angle of attack at any given speed. This will have the result of increasing asymmetric blade effect with a bigger yawing moment, and partially masking the fin and rudder, making them less effective. Ultimately, the most important element in the control of the aircraft under asymmetric conditions is dynamic pressure, which is a measure of the calibrated airspeed, CAS, which is, in turn, indicated airspeed, IAS, corrected for position error. IAS, of course, is what the pilot sees on his airspeed indicator. Higher IAS means more control effectiveness, and consequently greater rudder movement, all other parameters being unchanged. We can summarize the factors affecting the roll and yaw moments when on asymmetric thrust as follows: thrust on the live engine, altitude, drag from the dead engine and propeller, asymmetric blade effect, center of gravity position, torque reaction, difference in lift from slipstream, rolling moment due to side slip, weight, and finally the vital element of IAS, which determines the amount of control the pilot has over the aircraft. You have learned that when a multi-engine aircraft suffers an engine failure, there are several variables which affect both the yawing moment and the rudder moment used to oppose it. You have also learned that there is a minimum IAS, VMC, below which it is impossible to maintain directional control under asymmetric thrust. Airworthiness authorities, the one quoted in this lesson being the JAA, have laid down conditions to be satisfied in establishing the minimum airspeeds for inclusion in the flight manual of a new type. In most instances, the conditions are based on a worst case. A safety factor is built into these speeds to allow for aircraft age and the response time of an average pilot. Because there are distinct variations in an aircraft's handling characteristics in certain configurations and stages of flight, minimum control speed, VMC, has three separate specifications, which are VMCA, the minimum control speed in the air, VMCG, the minimum control speed on the ground, and VMCL, the minimum control speed in the landing configuration. For aircraft with 3 or more engines, airborne speeds will also be defined for single and double engine failures, nominated VMCA1 and VMCA2, and so on. The JAA and its successor, EASA, specify the parameters for determining VMCA. Here we have paraphrased the JAA requirements as laid down in Regulation JAR 25.149. VMCA is the calibrated airspeed at which, when the critical engine is suddenly made inoperative, it is possible to maintain control of the aeroplane with that engine still inoperative and maintain straight flight with an angle of bank of not more than 5 degrees. VMCA may not exceed 1.13 times the reference stall speed under these conditions. Maximum available takeoff power or thrust on the engines, the aeroplane trimmed for takeoff, the most unfavorable center of gravity position, maximum sea level takeoff weight, the aeroplane in its most critical takeoff configuration, but with gear up, the aeroplane airborne and the ground effect negligible, and, if applicable, the propeller of the inoperative engine either windmilling or, if an automatic feathering device is fitted, feathered. The rudder control forces required to maintain control at VMCA may not exceed 150 pounds, nor may it be necessary to reduce power or thrust on the operative engines. It should be noted that no performance requirements are specified. The only necessity is directional control. There are several factors that affect VMCA. They are as follows. Banking towards the live engine reduces the rudder deflection required, and so allows a lower VMCA. 5 degrees is stipulated because larger bank angles would significantly diminish the vertical component of lift, requiring a higher angle of attack with its attendant drag penalty. The position of the CG, around which the aircraft rotates, will directly affect the length of the rudder arm, and thus the power of the fin and rudder to give directional control and stability. The worst case is with the shortest arm, the CG being at its aft limit. As well as the rudder, the aileron's effectiveness is reduced at lower airspeeds, requiring greater deflection to keep the wings level or hold the required bank under asymmetric power. If the down aileron deflection is large at low speed, it may be enough to cause a stall of that wing, giving an uncontrollable roll towards the dead engine. VMCA must be high enough to avoid this situation. Flap position affects the lift-drag ratio, nose-down pitching moment and stalling speed. With asymmetric thrust, flap reduces climb rate whilst increasing the margin above the stall, but does not directly affect VMCA. However, if takeoff flap is used, there will be a greater difference of slipstream-associated lift between wings, giving a larger rolling moment, needing more aileron, and indirectly increasing VMCA. The undercarriage increases drag and reduces performance. The extra keel surface in front of the CG slightly reduces directional stability, opposing the fin and rudder, with a small increase in VMCA. Increases in altitude and temperature will reduce the thrust from the live engine or engines unless boosted, and VMCA will be reduced accordingly. The relationship between stalling speed and VMCA can be seen on the graph on screen, in which the VMCA curve intersects with VS, typically around 3,000 feet. Thus, above this altitude, an aircraft would reach the stall before VMCA on deceleration after engine failure. This gives a smaller speed margin above loss of control. JAR Regulation CS 25.149 gives the parameters for ground minimum control speed. It states that VMCG is the calibrated airspeed during the takeoff run at which, when the critical engine is suddenly made inoperative, it is possible to maintain control of the aeroplane with the use of primary aerodynamic controls alone, that is, without the use of nosewheel steering, to enable takeoff to be safely continued using normal piloting skill. The rudder force may not exceed 150 pounds or 68.1 kilos, and until the aircraft becomes airborne, the lateral control may only be used to the extent of keeping the wings level. In the determination of VMCG, assuming that the path of the aeroplane accelerating with all engines operating is along the centre of the runway. Its path, from the point at which the critical engine is made inoperative to the point at which recovery to a direction parallel to the centre line is completed, may not deviate more than 30 feet or 9.144 meters laterally from the centre line at any point. As with VMCA, these conditions must be established with maximum available takeoff power or thrust on the engines, the aeroplane trimmed for takeoff, the most unfavourable CG position, and maximum sea level takeoff weight. There are several factors that affect VMCG. They are as follows. As with VMCA, increases in altitude and temperature will reduce the thrust produced by the live engine or engines if unsupercharged, and VMCG will be reduced accordingly. Nose wheel steering is designed for taxiing, making tight turns at low speed, turning off the runway, parking, and so on. When taking off on wet, icy or slippery runways, the nose wheel can lose adhesion and have little steering effect. VMCG is established during flight testing, usually on a dry runway. If the test pilot were to use the steering, it would give a false low control speed, which could result in loss of control if used in emergencies. The regulations are established according to worst-case parameters to give the maximum safety factor. The rudder arm, when the aircraft is on the ground, is shorter than when airborne, as it rotates around the main undercarriage, which is aft of the CG. On most aircraft, therefore, VMCG will be higher than VMCA. JAR Regulation CS 25.149 gives the parameters for landing minimum control speed, VMCL. VMCL is the calibrated airspeed at which, when the critical engine is suddenly made inoperative, it is possible to maintain control with that engine inoperative and maintain straight flight with no more than 5 degrees of bank. The airspeed must be established with the aeroplane in the most critical configuration for approach and landing, with all engines operating, the most unfavourable CG, the aeroplane trimmed for approach with all engines operating, the most unfavourable weight. For propeller aeroplanes, the propeller of the inoperative engine in the position it achieves without pilot action, and go-around power or thrust setting on the operating engine or engines. In demonstrating VMCL, the rudder force may not exceed 150 pounds. The aeroplane may not exhibit hazardous flight characteristics or require exceptional piloting skill, alertness or strength. And lateral control must be sufficient to roll the aeroplane from an initial condition of steady flight through an angle of 20 degrees in the direction necessary to turn away from the inoperative engine or engines in not more than 5 seconds. At low airspeeds, and therefore low dynamic pressures, the effectiveness of all flying controls for a given displacement is reduced. This effect on the rudder has already been mentioned, but the ailerons are similarly affected, of course. To obtain the required response, greater deflection must be used at low speed. The downgoing aileron will add to the yawing moment from increased induced drag, and may even stall the outer section of the wing at low IASs. Adequate aileron effectiveness is clearly very important, since VMCL requirements include rolling and not just directional control. JAA's document CS 25.149 sets out the criteria for establishing the various minimum control speeds for the certification of a new aircraft type. Once established, the speeds will be included in the aircraft's flight manual. From the extracts that have been detailed in this lesson, we can summarize several significant points. First, regarding VMCG, nose wheel steering may not be used when establishing the speed, since its use would artificially reduce VMCG, and on a slippery runway, nose wheel steering is likely to be ineffective at speeds well above taxiing speed, so would not be able to control the aircraft directionally at or above the stated VMCG. For VMCL, the criteria include a roll requirement, and not just one for directional control, as with the other VMC categories. As a general point, the thrust developed by an engine depends on air density, so thrust will decrease with increasing altitude and temperature. The yawing moment due to asymmetric thrust will thus reduce with altitude and temperature, enabling control to be maintained at a lower IAS. VMC therefore decreases with higher density altitude. You learned in the earlier flight mechanics lesson on climbing that an aircraft's ability to climb depends on the excess thrust available after aerodynamic drag is balanced. If a twin-engine aircraft loses an engine, thrust is reduced by 50%. But excess thrust, that is, thrust minus aerodynamic drag, is reduced by more than 50%, as shown in the graph on the screen. The ability to climb may be reduced by as much as 80%. The angle of climb is determined by the excess thrust available, and will be a maximum when the aircraft is flown at the speed where excess thrust is at a maximum. In other words, at a maximum thrust-drag ratio. Since thrust decreases with forward speed, and total drag increases above and below the minimum drag speed, VIMD, the best angle of climb is achieved at a speed below VIMD, but at a safe margin above the stall speed. The IAS for best angle of climb is Vx for all engines operating, and on twin-engine aircraft, Vxse is best for single-engine climb angle. Rate of climb is determined by the excess power available. Power is the rate of doing work, that is, thrust or drag times true airspeed, thrust and drag being forces, and TAS being the only real speed. Although thrust reduces with speed, total power available increases to a point because of the speed factor. Similarly, power required is a measure of drag times TAS, so excess power available determines the available rate of climb. The airspeed for best rate of climb is Vy for all engines operating, and Vyse for best single-engine rate of climb. Vy and Vyse are higher than Vx and Vxse, and provide a safer margin above both stall and VMCA. Under most circumstances, Vy and Vyse are the best speeds to use. On small twin-engine aircraft, Vyse is marked on the airspeed indicator by a blue radial line, and is referred to as blue line speed. Considering all the foregoing factors, we can conclude that at a given altitude, airspeed and power setting, excess thrust depends on the amount of drag being generated, and this in turn will depend on configuration, weight, and whether turns are required. The control surface deflections required to balance asymmetric thrust will also cause drag. It is essential, therefore, that after an engine failure, particularly during takeoff or go-around, drag is reduced and no turns are made until safely clear of the ground. Drag can be reduced by feathering the propeller of the failed engine, raising the landing gear, raising the flaps at a safe height and speed, closing the cowl flaps on the dead engine if fitted, and applying 5 degrees of bank towards the live engine. Flying at blue line speed, VYSE, with maximum permissible thrust on the live engine, will provide maximum performance and optimum control of the aeroplane. While studying principles of flight, for simplicity, we assume that air is incompressible, but this is only valid for low-speed flight. For high-speed flight, we must consider changes in air density due to the changes in air pressure. This is known as compressible flow. When an aircraft moves through the air, pressure waves are generated. To generate some pressure waves, we're going to hit the nose of a stationary aircraft with a hammer, but in flight it will be particles of air that generate the pressure waves. The vibrations from the blow generate a series of pressure waves that move outwards through the air from where the hammer hit the aircraft, the point source. If we zoom out a bit, we can see what is going on more clearly, and for clarity, we'll show just one pressure wave. The pressure wave propagated from its point source, and then the picture was frozen. In the time between the pressure wave being generated and freezing the picture, the pressure wave moved through the air at a certain speed. The speed of pressure wave propagation is called the local speed of sound, represented by lowercase a. The only thing that will affect the speed of sound is the outside air temperature. The higher the temperature, the higher the speed of sound. In the same time interval, but with a higher temperature, the pressure wave would have propagated further, but not so far at a lower temperature. At a constant outside air temperature, do you think the pressure wave will look the same if the aircraft is moving when the pressure wave is generated? Of course it will. Nothing has changed. The pressure wave was generated in the same place, and the air temperature was the same. So the pressure wave will travel the same distance through the air in the same time. But, in the time it took for the pressure wave to propagate, the aircraft will have moved forward from the point source of the pressure wave. The pressure wave moved through the air at the local speed of sound, and the aircraft moved through the air at its true airspeed. To understand the relationship between the local speed of sound and the aircraft true airspeed, we need to remind ourselves of a fixed reference point, the relative airflow. True airspeed is the speed of the aircraft through the air. But which air? The air just in front of the leading pressure wave. The trailing pressure wave is included for reference purposes only. During the study of high-speed flight, the most important aspect of the relative airflow is that it is close to, but as yet unaffected by, the presence of the aircraft. For general review, the relative airflow is also parallel to, and in the opposite direction to, the aircraft flight path, and the length of the vector represents the true airspeed of the aircraft. As soon as the pressure wave passes over an air particle, it is no longer relative airflow. It becomes effective airflow. More about this in a minute. Throughout our study of high-speed flight, there are two major characteristics in which we are interested. The one we will illustrate now is the proximity of the aircraft to the leading pressure wave. The second characteristic is the formation of shock waves, which we will look at later. There is a ratio between the aircraft true airspeed and the local speed of sound. This ratio is called the Mach number, usually shortened to m. The true airspeed of the aircraft in this illustration is 264 knots, and the local speed of sound is 660 knots at 15 degrees C. The Mach number is therefore 0.4. This is said as Mach 0.4. It is important to remember that both the speed of the aircraft and the speed of the pressure wave use the relative airflow as the reference air through which they are moving. We learned earlier that relative airflow can also be called free stream flow. So the Mach number we are discussing here is called the free stream Mach number. The free stream Mach number is basically what is presented on the aircraft Mach meter. The scale shows the aircraft at 4/10 the distance from the point source to the leading pressure wave. But this fact doesn't help us understand how high-speed flight affects the aircraft. It is this that will have an effect on the aircraft: how close the aircraft is to the leading pressure wave. We can now examine how the pressure wave changes the airflow approaching the aircraft. As soon as the pressure wave passes over an air particle, it is no longer relative airflow. It becomes effective airflow. The leading pressure wave effectively acts as a messenger. It tells the air, "Here comes an aeroplane, you'd better get out of the way." You can see that as soon as the pressure wave passes over the air, it starts to upwash. The higher the Mach number, the closer the aircraft is to the leading pressure wave, and consequently, the air has to upwash through a greater angle. You learned during your study of stalling that this will cause CLmax to decrease. Hence, stall speed will increase. The effect of this change will be discussed in detail later. Anything that is moving will have a Mach number. A person walking will be travelling at Mach 0.005, firmly in the low-speed flight region, where we don't need to worry about how close we are to the leading pressure wave. A training plane cruises at about Mach 0.14. A light twin at Mach 0.3, and a turboprop commuter aircraft at Mach 0.4. All these examples operate at speeds less than Mach 0.4, when their proximity to the leading pressure wave has no significance. It is only aircraft that operate above Mach 0.4 that need to know their proximity to the leading pressure wave, and consequently will be fitted with a Mach meter to tell the flight crew the aircraft Mach number. We'll now consider something called the critical Mach number. The critical Mach number is not used operationally, but is an important reference for your understanding of high-speed flight and your ability to answer exam questions. Here is a view of the wing, with the airflow accelerating over the top surface. The airflow will reach maximum velocity relative to the wing surface at the point of minimum cross-sectional area of the airflow. The maximum velocity of air on the wing will always be faster than the true airspeed. Otherwise, there would be no lift generated. The maximum velocity of air on the wing is called local velocity, because we are discussing air relative to the aeroplane's surface. We can now introduce a Mach number called the local Mach number. The local Mach number is the ratio between the speed of the local velocity over the surface and the local speed of sound. Remember, the local Mach number will always be higher than the free stream Mach number. In this example, the free stream Mach number is Mach 0.55, and the local Mach number is higher at Mach 0.8. Let's see what happens as the aircraft accelerates in level flight. Both the free stream Mach number and the local Mach number are increasing. Notice the local Mach number has now reached the same value as the speed of sound, Mach 1. Bear in mind that the free stream Mach number is effectively the aircraft Mach number you'll be seeing on your Mach meter. The aircraft Mach number, at which the local velocity first reaches Mach 1, is called the critical Mach number. The critical Mach number is usually shortened to m crit. The reason that m crit is such an important reference is that as soon as m crit is exceeded by even the smallest margin, a shock wave will start to form at the point of maximum local velocity. In the next lesson, we will examine why shock waves form, and later we'll look at their effect on the operation of aircraft during high-speed flight. We'll now look at what makes a shock wave form. The illustration shows the local Mach number just a touch faster than Mach 1, and a shock wave present on the wing. We need to take a closer look and reintroduce the free stream Mach number display. When the Mach number is reduced to the critical Mach number, the local Mach number is Mach 1, and the shock wave is no longer there. At m crit, there is no shock wave. Whenever a particle of air hits the aeroplane, a pressure wave is generated. Lots of pressure waves. So, for clarity, we'll consider a series of pressure waves originating from the same place on the wing. The pressure waves slow down as they move forward. And then stop at the point of maximum velocity. Why do they slow down and then stop on the wing surface? Because the air is accelerating towards maximum velocity over the leading edge and decelerating from maximum velocity towards the trailing edge. The pressure waves move through the air at the speed of sound, so as they move forwards, they meet air travelling backwards at a higher and higher speed. When they reach the point of maximum velocity, the air is moving backwards over the wing at the same speed as they are moving forward through the air, so they become stationary relative to the wing. At m crit, the pressure waves have no influence on the airflow over the wing. But at speeds above m crit, the pressure waves start to build up. This build-up of pressure waves at flight speeds above m crit is known as a shock wave, so called because of its sudden influence on the properties of the airflow through it. We need to zoom in even closer. We know the air is accelerating over the leading edge of the wing, but the local Mach number is still less than 1. We call this subsonic flow. Behind the shock wave, the local Mach number is also less than 1. Again, subsonic flow. Somewhere within the shock wave itself, the local Mach number will be equal to 1. We call this sonic flow. There will be an area in front of the shock wave where the local Mach number will be greater than 1, and we call this supersonic flow. Please note that the shock wave is located at the rear of the area of supersonic flow. To recap, when the speed of the airflow on the aircraft is less than Mach 1, the flow is subsonic, When the speed of the airflow on the aircraft is equal to Mach 1, the flow is sonic. When the speed of the airflow on the aircraft is greater than Mach 1, the flow is supersonic. And the shock wave is located at the rear of the area of supersonic flow. Aircraft are classified in accordance with their maximum operating speed, which will be either subsonic, transonic, or supersonic. We will now define the associated speed ranges. The illustration shows a table with aircraft Mach number increasing to the right. We know the average training plane is fairly slow. A light twin is a little faster, and a turboprop commuter plane faster still. As we've seen, all these types of aircraft operate at speeds below about Mach 0.4, where incompressible flow is assumed, low-speed flight, whereas jet transport aircraft operate at the considerably higher speed of approximately Mach 0.82, inside the speed range where compressible flow must be considered, high-speed flight. The first real division we have to consider is MCRIT. Aircraft that operate up to approximately Mach 0.75 are classified as subsonic. An aircraft is classified as being a subsonic aircraft because all local velocities are less than Mach 1. The other division we have to consider here is approximately Mach 1.2. Aircraft that operate between approximately Mach 0.75 and Mach 1.2 are classified as transonic. An aircraft is classified as being a transonic aircraft because some local velocities are less than Mach 1 and some local velocities are greater than Mach 1. It is within the transonic speed region that changes take place on the aircraft because of the existence of shock waves. Aircraft that operate at speeds above Mach 1.2 are classified as supersonic. An aircraft is classified as being a supersonic aircraft because all local velocities are greater than Mach 1. So there we have it. Subsonic when all the local velocities are less than Mach 1. Transonic when some local velocities are less than Mach 1 and some greater than Mach 1. And supersonic when all the local velocities are greater than Mach 1. Having considered some of the preliminary definitions and explanation of high-speed flight, we can now consider the changes that take place because of flight in the transonic speed region with shock waves on the wing. Now we're going to look at the changes that happen to the airflow as it passes through a shock wave. We can see a close-up view of the airflow flowing through a small shock wave on the top surface of a wing. The airflow is accelerating, and the grey shading shows the area of supersonic flow. Note once again that the shock wave is located at the rear of the area of supersonic flow. The velocity of the airflow downstream of the shock wave is subsonic, less than Mach 1. The air has been decelerated by the shock wave. And, in accordance with Bernoulli's theorem, if the velocity of the air decreases, its pressure will increase. The temperature of the airflow will increase as it flows through the shock wave. And the density of the air will also increase. All these changes take place within the shock wave. The airflow enters the front of the shock wave with one set of properties and exits the shock wave with a different set of properties. A further effect is that the airflow will begin to separate from immediately behind the shock wave. At speeds just above MCRIT, this is not a problem, but as Mach number increases, it will start to become a limiting factor to further acceleration. We examine the effect of these changes in a future lesson. There are two slightly different types of shock wave, the normal and oblique. The following data may be required to answer written exam questions. but is of no operational importance. We will examine the normal shock wave first. It is called a normal shock wave because it is 90 degrees to the upstream flow. As previously pointed out, the boundary layer enters the shock wave with one set of properties and emerges with a different set of properties. The velocity and Mach number decrease to subsonic speed. The airflow energy is greatly decreased. The static pressure and density are greatly increased. The temperature of the boundary layer is increased. The local speed of sound is increased because of the temperature rise. The temperature rise of the boundary layer through a shock wave is one of the major causes of the increase in drag during high-speed flight. To summarize, velocity and energy decrease, and everything else increases through a normal shock wave. We will now consider the other type of shock wave, the oblique shock wave, so called because it is more than 90 degrees to the upstream flow. The boundary layer changes direction as it passes through an oblique shock wave, a noticeable difference from the normal shock wave. Downstream of the oblique shock wave, the velocity and Mach number decrease but remain supersonic. The airflow energy decreases. The static pressure, temperature, and the local speed of sound all increase. To summarize, as with the normal shock wave, the velocity and energy decrease, and everything else increases through an oblique shock wave. But please note the differences. The boundary layer energy, static pressure, and density change more through a normal shock wave than through an oblique shock wave. The velocity and Mach number decrease through both types of shock wave. Through the normal, it decreases to subsonic, whereas through the oblique, it remains supersonic. The other difference is that through an oblique shock wave, the airflow changes direction. We've just seen the changes to the properties of the airflow as it passes through a shock wave. We'll now examine how these changes affect the aeroplane. The diagram shows an aerofoil section with the vertical axis depicting decreasing pressure. The blue line is the reduction in pressure on the top surface. The red line is the pressure on the bottom surface. The difference between the two pressures generates lift. The center of the area of the top and bottom surface pressure distribution is what determines the position of the center of pressure, and it is the distribution of pressure that will be changing. There will always be a small amount of separated air at the trailing edge, called the wake. In the top right-hand corner is a sketch graph showing lift coefficient against Mach number. The red dot is a sample lift coefficient at Mach 0.75, our assumed m-crit. In the bottom right-hand corner is a sketch graph showing drag coefficient against Mach number. The red dot is a sample drag coefficient at our assumed m-crit. If m-crit is exceeded by even the smallest margin, a shock wave will form on the top surface, with an insignificant amount of airflow separation immediately behind it. We will now see what happens to the distribution of pressure with increasing Mach number. More of the airflow will be accelerated to supersonic speed, and the area of supersonic flow on the top surface will be bigger. Because the shock wave is always at the rear of the area of supersonic flow, the shock wave will start to move rearwards. With the initial acceleration to Mach 0.84, the shock wave doesn't move very far aft, but it will become thicker and start to have a greater effect on the airflow through it. There will be a lot happening during these next few animations, so don't try to watch everything. Please concentrate on the shape of the suction and how it changes. The shock wave makes the top surface pressure change shape. There is now a negative pressure differential on the aft portion of the wing, and consequently the centre of pressure has moved rearwards. Rearwards movement of the centre of pressure is a significant development, which will be examined in detail later. There has been no loss of lift. In fact, during the acceleration to Mach 0.84, the lift coefficient has increased slightly. Unfortunately, the drag has also increased, which is one of the limiting factors to operating an aircraft at speeds higher than about Mach 0.84. Please also note the increased airflow separation from immediately behind the shock wave. At higher Mach numbers, this will become another limiting factor. We have introduced the changes that take place when operating an aircraft up to a typical maximum operating Mach number. We can now examine higher Mach numbers, and while we don't want to operate our aircraft at those speeds. The reasons why it is not wise or efficient to exceed approximately Mach 0.84 will now be examined. If the Mach number is allowed to exceed approximately Mach 0.84, a typical maximum operating Mach number, the increased airflow separation from behind the shock wave, will start to cause a phenomenon known as high-speed buffet. Observe the airflow separation increasing and forward movement of the centre of pressure. The separated airflow from the shock wave will extend beyond the tailplane. A shock wave has now started to form on the bottom surface and will cause the bottom surface pressure to change shape. Further acceleration to Mach 0.9 shows both shock waves moving further rearwards, and the changes in pressure distribution on the wing has caused the centre of pressure to move forwards again. The lift coefficient has decreased radically, and the drag coefficient has continued to increase, both of which reduces operating efficiency. Airflow separation has also increased. Further acceleration sees both shock waves moving all the way back to the trailing edge. There is now supersonic flow over the entire top and bottom wing surfaces. The pressure distribution has evened out, and the centre of pressure has moved aft. The lift coefficient has consequently started to recover, and the drag coefficient has reached its highest value. At a speed just exceeding Mach 1, another shock wave starts to form, called the bow wave. You will now see the centre of pressure moving aft to the 50% chord position. With the centre of pressure at the 50% chord position, static longitudinal stability is increased. The bow wave has moved aft to the leading edge and is said to attach between Mach 1.3 and 1.4. At supersonic speed, the lift coefficient has started to level off, but at a value less than at subsonic speed. The drag coefficient has also started to level off, but at a value higher than at subsonic speed. To summarize, as the Mach number is increased to approximately Mach 0.84, drag increases only slightly, so the advantage of a higher true airspeed is achieved efficiently. The disadvantage of flying faster than mcrit is that the centre of pressure will move rearwards, giving a nose-down pitching moment called Mach tuck. Mach tuck can be prevented by the fitment of a system called Mach trim, which was explained in detail earlier. There are two major reasons why Mach numbers above approximately 0.84 must be avoided. The first is because of excessive airframe buffeting, caused by the separated airflow from the shock wave contacting the tailplane. And secondly, the massive increase in drag would make operation of the aeroplane too expensive. The initial climb to cruise altitude will be flown at a constant indicated airspeed. You will already be familiar with variations of this sketch graph. Usually, the illustration uses calibrated airspeed, but for practical reasons, we will be using CAS to represent indicated airspeed. From the elements of principles of flight you have already studied, you will know that air density decreases with increasing altitude. So, in order to maintain a constant indicated airspeed during the initial climb, you must increase the true airspeed. As altitude is increased, the outside air temperature will be decreasing, and therefore the local speed of sound will be decreasing. So, during the initial climb at a constant indicated airspeed, the true airspeed will be increasing, and the local speed of sound will be decreasing. It is obvious, therefore, that the Mach number will be increasing. During the initial climb, an altitude will eventually be reached when the Mach number can no longer be increased without the aircraft exceeding its maximum operating Mach number, or MMO. This is called the changeover altitude. For reference purposes, the changeover altitude is approximately 29,000 feet. The continued climb to cruise altitude must be flown at a constant Mach number, slightly less than MMO. MMO may not be deliberately exceeded in any regime of flight, climb, cruise or descent, to quote the regulations. The outside air temperature will still be decreasing, so the true airspeed must be decreased to keep the Mach number constant. The air density will still be decreasing, so the indicated airspeed will also decrease. You should now be asking yourself how lift can remain constant if both air density and indicated airspeed are decreasing. When climbing above the changeover altitude at a constant Mach number, the angle of attack must be increased. We have now reached the tropopause, above which the outside air temperature remains constant in the international standard atmosphere. Because outside air temperature remains constant above the tropopause, to maintain a constant Mach number, the true airspeed must remain constant. This fact is not obvious when asked a question about it, but the ability to visualize this diagram will help. Because air density is still decreasing, the indicated airspeed will continue to decrease, but at a lower rate, because during this portion of the climb, the true airspeed is constant. We can now consider the changes that take place in a descent from cruise altitude. Unsurprisingly, the initial descent will be made at a constant Mach number. Initially, the true airspeed will have to remain constant because of the constant outside air temperature. And because of the increasing air density, the indicated airspeed will be increasing. But now, to keep lift the same as the weight, the angle of attack will have to be decreased. As the tropopause is passed, the true airspeed will have to be increased, and the indicated airspeed is increasing at a greater rate because both the true airspeed and the air density is increasing. As the changeover altitude is approached in the constant Mach number descent, the aircraft is now in danger of exceeding the other maximum operating speed, VMO. In case you've forgotten, VMO is an EAS, the only V-speed that is not a calibrated airspeed. As with MMO, the regulations state, VMO may not be deliberately exceeded in any regime of flight, climb, cruise or descent. So the descent below the changeover altitude is carried out at a constant indicated airspeed, with true airspeed and Mach number both decreasing. This diagram contains all the information you need to answer the relevant questions in the written exams, so it's a very good idea to commit it to memory. It was explained earlier that as the shockwaves form at aircraft speeds greater than m-crit, the centre of pressure moves rearwards. If we view the aircraft from the side, we can see the result of this event more clearly. An aircraft nose-down pitching moment is generated, which is called Mach tuck. Mach tuck is the first physical manifestation of shockwave formation on the aircraft. When studying longitudinal stability, we learned that an aircraft must require an increasing push force with increasing speed. Mach tuck must therefore be opposed with an automatic aircraft system called Mach trim. In practice, Mach trim generates an opposing pitching moment as the aircraft accelerates to, as the examiners word it, high Mach numbers. In fact, Mach trim must generate an opposing pitching moment which is greater than Mach tuck. This illustration will show us why. All aircraft must have a stick force gradient that requires an increasing push force with increasing speed. At high Mach numbers, Mach tuck reduces the stick force gradient to a negative value, which means an increasing pull force would be required. At high Mach numbers, Mach trim has to generate a larger pitching moment than Mach tuck to ensure the required stick force gradient is maintained. We can now consider how Mach trim is achieved. There are three methods. Move the elevator up, decrease tailplane incidence, or move the centre of gravity rearwards. However, the preceding three methods of achieving Mach trim will only work while accelerating beyond m-crit. It is more correct to say that Mach trim adjusts the longitudinal trim at high Mach numbers. m-crit has already been defined as the aircraft Mach number at which the local velocity first reaches Mach 1. Let's see what happens as the angle of attack is increased. Because of the reduction in cross-sectional area of the airflow, the boundary layer has accelerated, and instead of a local Mach number of 1 at an aircraft Mach number of 0.75, the local Mach number has increased to 1.05. So, Mach 0.75 is no longer m-crit. The increase in angle of attack has resulted in m-crit decreasing to Mach 0.7. The significance of a decrease in m-crit with increasing angle of attack will greatly influence the safe operation of jet aircraft operating at their cruise altitude. You might like to think about what would require an increase in angle of attack in the cruise. It was mentioned earlier that at speeds above approximately Mach 0.4, the 1g stall speed starts to increase. We will now take a look at why this happens, and the effect it has on the aircraft when cruising at high altitude and high Mach numbers. The illustration shows the effective airflow starting to upwash as soon as the leading pressure wave passes over it. We can also see the average effective airflow angle of attack. As the Mach number increases, the effective airflow has to upwash through a greater angle, and the effective angle of attack will increase. The result will be a decrease in CLmax and a reduction in stall angle. We know that air density does not affect the 1g stall speed, and we know that airflow separation just before the 1g stall can cause airframe buffeting. To avoid any confusion, we should now call this low-speed buffet. Low-speed buffet will begin at a speed called the buffet boundary. We can say that as altitude increases, the 1g stall speed is constant until a very high altitude is reached, above which the stall speed increases. There is an altitude above which flight at the 1g stall speed should not be attempted. This is called the aerodynamic ceiling, at which only one speed is possible. You might think that in the cruise we do not operate jet aircraft anywhere near the 1g stall speed, but we have just seen that increasing Mach number makes the 1g stall speed increase. When operating a jet aircraft at high altitude and high Mach number, it will be necessary to turn occasionally for navigation purposes. We already know that turning requires lift to be increased, and therefore the load factor will increase. We also know that increasing the load factor will increase the stall speed. With increasing load factor, the so-called very high altitude above which the stall speed increases will get lower and lower and lower and lower. The dashed blue line represents the constant Mach number. You can appreciate that when turning at high cruising altitude at high Mach number, the bank angle must not be excessive. We can now superimpose a line representing the EAS at which high-speed buffet will occur. High-speed buffet is caused by the excessive airflow separation from immediately behind a shock wave we saw earlier. High-speed buffet is a Mach number phenomena, but a given Mach number will represent a decreasing EAS with increasing altitude. There will also be a high-speed buffet boundary above which buffeting will begin. So there is low-speed buffet and high-speed buffet, a low-speed buffet boundary, and a high-speed buffet boundary. At low altitude, there is a wide operating speed range between the low-speed buffet boundary and the high-speed buffet boundary. But with increasing altitude, the operating speed range with no buffet decreases. This is the operating speed range envelope at sea level. Stall boundary on the left and high-speed buffet boundary on the right. At a representative cruise altitude for a jet transport aircraft, the operating speed range envelope is much reduced. The standard definition of the aerodynamic ceiling is the altitude at which the low-speed buffet and the high-speed buffet are the same speed. The aerodynamic ceiling can also be referred to as coffin corner. We can now consider how low and high-speed buffet can be avoided while operating a jet transport aircraft in the cruise. We will now see how a jet transport aircraft can be operated in the cruise at high Mach number without the risk of buffeting. This is an example of a buffet onset chart, with emphasis on the word onset. An aircraft must be operated at all times with a margin of safety from the onset of buffeting. All we have learned so far about the factors that affect Mach number and shockwave formation are drawn together in this chart. In particular, we have learned that there is an altitude at which only one speed is possible, the aerodynamic ceiling. It would be extremely foolish to fly at this altitude, because turning to a new heading or the slightest turbulence would stall the aircraft. Regulations, if not common sense, require an aircraft to be operated with a minimum margin to the buffet of 0.3 g. This equates to something called the 1.3 g altitude. We will now examine the buffet onset chart in detail, and then derive some operational data from it. On the left, we have pressure altitude, increasing vertically downwards, labelled as flight level. At bottom left, increasing to the right, is Mach number, with MMO highlighted. At bottom right, above the axis, there is bank angle increasing to the right. The calculation for load factor has been done for you and is listed below the axis. Increasing vertically on the right, we have aircraft weight in tons. The plots on the left represent the onset of both high and low speed buffet at a series of flight levels, with flight level 350 highlighted. So we can manipulate the data on the buffet onset chart. We'll zoom in. Aircraft data will be presented to you. The aircraft is flying at Mach 0.8, at flight level 350, at a weight of 110 tons. You would move upwards from Mach 0.8 to flight level 350 and across to 110 tons, and then down to the load factor bank angle data, where you would find that the aircraft will start to buffet at a bank angle of 53 degrees, or a load factor of 1.65 g, at a higher altitude of flight level 370. Buffet onset would be at a bank angle of 49 degrees, or a load factor of 1.46 g. If we consider a lower weight of 100 tons, a bank angle of 57 degrees or a load factor of 1.81 would be possible at buffet onset. We'll revert to the original data, so we can determine the 1.3 g altitude under these conditions. Move upwards from 1.3 g to 110 tons, and left to Mach 0.8. Now interpolate between flight level 390 and flight level 410 to discover that the 1.3 g altitude is flight level 400. If you are asked if the 1.3 g altitude can be exceeded for any reason, the answer is no. The 1.3 g altitude may not be deliberately exceeded for any reason. The last thing we will determine is the speed of buffet onset in 1G flight, at both high and low speed. This is a common written exam question. Move upwards from 1G to 110 tons, and left towards the flight level 350 plot. We can see that the high-speed end of the flight level 350 plot is above our position on the graph. This tells us that under existing conditions, high-speed buffet is not limiting. The high-speed limitation is MMO. If we continue to the left, we will eventually intersect the low-speed end of the flight level 350 plot. Moving downwards, we will discover that the aircraft would begin to low-speed buffet at Mach 0.57. The conclusion is that under existing conditions, high-speed buffet is not a problem, and the maximum speed of the aircraft is limited by MMO, the maximum operating Mach number, and the aircraft would begin to low-speed buffet at Mach 0.57. The purpose of commercial transport aircraft is to fly as fast, but at the same time as efficiently as possible. We have seen that most of the adverse effects of high-speed flight begin when flying faster than mcrit. So if mcrit can be increased, a higher true airspeed is possible while maintaining the same level of efficiency. The unfavorable characteristics of high-speed flight, such as Mach tuck, high-speed buffet, and wave drag, are grouped under the heading of compressibility effects. There are several methods of increasing mcrit, the first of which is the thin wing section. A thinner wing increases the cross-sectional area of the streamlined flow. This results in a reduction in local velocity. Therefore, mcrit is increased. Unfortunately, a thin wing has some disadvantages. Namely, less lift is produced for a given angle of attack, the structural weight is higher, and there is an obvious reduction in the size of the fuel tanks. With these disadvantages in mind, the designers will provide jet transport aircraft with a wing as thin as is practical. A swept-back wing is the most commonly used method of increasing mcrit. Sweep forward would give the same benefit, but forward sweep is structurally unsound, so generally speaking, has only been used on a few experimental aircraft. Consequently, any references to a swept wing means swept back. The only reason a swept wing is fitted to an aircraft is to increase the critical Mach number. A swept wing also has some associated byproducts, some favourable and some not, which we'll look at later. Observe, the effective airflow passes over a straight unswept wing at 90 degrees to the leading and trailing edges, giving a certain effective chord. On a swept wing, the effective airflow passes over the leading and trailing edges at an angle, which gives an increase in effective chord. This results in a decrease in thickness-chord ratio, which has the effect of increasing the length of the stream tube. Thus, the local velocity is decreased, and therefore mcrit is increased. And vice versa. Anything which causes an increase in local velocity will decrease mcrit. For example, a downgoing aileron. To illustrate some of the advantages and disadvantages of a swept wing compared to a straight wing, we can use the lift curve. A favourable byproduct of a swept wing concerns flight in turbulence. Here we can see an angle of attack that results in a certain lift coefficient. If a gust increases the angle of attack, the lift coefficient will increase. If we now reset the graph, we can consider the lift curve of a swept wing for comparison. At the same angle of attack, the lift coefficient of the swept wing is less than that of a straight wing. But because of the reduced lift curve gradient of the swept wing, the same increase in angle of attack will result in a smaller increase in lift coefficient. Therefore, one of the favourable byproducts of a swept wing is that it is less sensitive to changes in angle of attack due to a gust or turbulence. Let's now consider an unfavourable byproduct of a swept wing. Illustrated is an angle of attack that gives the required lift coefficient from a straight wing. To obtain the same lift coefficient from a swept wing requires a higher angle of attack. The disadvantage to an aircraft with a swept wing is that it must fly with a noticeably higher nose attitude at low indicated airspeeds. This complicates landing gear design, including the possibility of tail strike when taking off and landing, plus reduced visibility from the flight deck. Another unfavourable byproduct of a swept wing is that the maximum lift coefficient is reduced when compared to a straight wing. This results in a higher stall speed, thus increased takeoff and landing distances. The two major disadvantages of the swept wing, pitch up at the stall and Mach tuck, have been covered elsewhere. We have seen that some of the problems of high-speed flight are associated with airflow separation behind the shock wave. As you learned when studying stalling, if the kinetic energy of the boundary layer is increased, separation will be reduced. Boundary layer kinetic energy can be increased if vortex generators are fitted. These are small blades projecting from the surface. Each blade generates a small but intense vortex, which re-energizes the boundary layer and reduces shock-induced airflow separation. A written exam question may use the wording, "Vortex generators induce high-energy air from the free stream flow to mix with the boundary layer." A further disadvantage of a swept wing is the reduced effectiveness of trailing edge control surfaces and high lift devices because their hinge line is swept. Let's summarize the relevant facts about a swept wing. Its purpose is to increase the critical Mach number. Its advantages are: it gives a positive contribution to lateral static stability, a positive contribution to directional static stability, and decreased sensitivity to gusts and turbulence. Its disadvantages are: pitch up from its tendency to tip stall, with the attendant possibility of deep stall or superstall, Mach tuck, a higher stall speed and consequent increased takeoff and landing run, less effective trailing edge control surfaces, particularly the trailing edge flaps, and lastly, a higher nose-up attitude at low indicated airspeed. Just as a matter of interest, the sweep angle for a jet transport aircraft is approximately 30 degrees, measured from the quarter chords line to a line perpendicular to the root chord. Our study of shock waves has concentrated on those on the wing, usually the place where supersonic flow first occurs. But a shock wave will form wherever the local velocity exceeds Mach 1. There will be a local airflow acceleration wherever the cross-sectional area of the streamline flow is reduced. So, at transonic speed, there will be shock waves at various locations on the aircraft, in addition to those on the wing. Wherever there is a sudden change in the cross-sectional area of the aircraft, from nose to tail, shock waves will form and add to the wave drag of the aircraft. To minimize wave drag, there is an ideal rate of change in cross-sectional area of the whole aircraft, from nose to tail, which is called area rule. But this shape is not practical because of the need for a wing, tail surfaces and engines, which will unfortunately give rise to sudden changes in the cross-section. Aircraft must be carefully designed so that items with a large cross-section, like the wing, are positioned at the widest area of the fuselage, and that the cockpit, tailplane, engines and other bumps are spread out along the fuselage. For aerodynamic and other reasons, the ideal area rule is not possible, but by clever design a good compromise can be achieved. Engine position can be optimized. Even the swept wing helps with area rule. Flap tracks and their operating mechanisms have to be streamlined, but the shape and length of the fairings is optimized to take advantage of area rule. But by far the greatest contribution to area rule is the design of the wing root fairings on modern jet transport aircraft. The designers of military aircraft don't have to make so many compromises with area rule as do the designers of transport aircraft. Here, the ideal cross-sectional area distribution is shown. And this is the actual cross-sectional area distribution of an aircraft with no area rule incorporated in the design. When area rule is incorporated in the design, the actual distribution of cross-sectional area is much closer to the ideal, and consequently, wave drag is minimized. You can see that the designers have reduced the cross-sectional area of the fuselage where the wing is attached. This is obviously not possible on a transport aircraft. A wasted fuselage resembles a conventional Coke bottle, and you may see references to Coke bottle shape in questions relating to area rule in the written exam. A common design element used to increase efficiency when operating in the transonic speed region is the supercritical aerofoil. A conventional aerofoil section is shown for comparison purposes. Here is a supercritical section. At first sight, it looks a bit odd, but it is only towards the wing root that the shape is as obvious as this. When compared to the conventional, the supercritical section has a blunt or well-rounded leading edge, greater thickness, a flat upper surface, and a thick trailing edge. Because the airflow doesn't accelerate as much over the flat upper surface, the formation of shock waves is delayed to give a higher M-crit, and the shock waves are much smaller and weaker when they do form. So the advantages of the supercritical over the conventional section are less sweep angle required, greater stiffness, and greater fuel capacity. The extra fuel capacity will allow a greater payload to be carried over the same distance, or the same payload over a longer distance. The disadvantages of the supercritical over the conventional section are More complex high-lift devices are required. There is more trim drag. And if the aircraft experiences high-speed buffet, any oscillations will be more severe. None of the disadvantages outweigh the advantage of a higher critical Mach number. So all jet transport aircraft will have a wing with a supercritical section. If the true airspeed of an aircraft is faster than the local speed of sound, the aircraft is moving faster than the weak pressure waves it is generating. To illustrate this concept, we need to imagine a source moving through the air, generating some representative weak pressure waves, and then stopping. The length of this line represents the true airspeed. Imagine we are plotting this on a piece of paper. If we draw a straight line from the point where the objects stop moving to form a tangent with the weak pressure waves, we have drawn a Mach line. The Mach line represents the limit which all the weak pressure waves have reached when the objects stop moving. A line drawn from the position where the object started moving to the Mach line represents the local speed of sound. The angle between the true airspeed vector and the Mach line, mu, is called the Mach angle. You remember that the formula to calculate Mach number is the true airspeed divided by the local speed of sound, which, using trigonometry, is the hypotenuse divided by the opposite. Therefore, 1 over m equals the local speed of sound, the opposite, divided by the true airspeed, the hypotenuse. Now let's see how the Mach angle relates to the Mach number. The sine of the Mach angle is the opposite divided by the hypotenuse. The opposite represents the local speed of sound, and the hypotenuse represents the true airspeed. Therefore, the sine of the Mach angle equals 1 divided by the Mach number. The conclusion to all these deliberations is that the greater the Mach number, the smaller the Mach angle. To put it another way, the Mach angle is inversely proportional to the Mach number. A written exam question may require that you remember that the Mach angle continues to decrease with increasing Mach number. Remember that weak pressure waves are spherical, and if we draw a series of Mach lines all the way round, we would end up with a Mach cone. The area inside the Mach cone is called the zone of influence. When flying at supersonic speeds, the Mach cone represents the limit of travel of the pressure disturbances created by the aircraft, and anything forward of the Mach cone cannot be influenced by any pressure changes taking place within the Mach cone. None of this has any operational relevance for a transonic jet transport aircraft, but there are still 1 or 2 questions about it in the written exam. To finish off our study of high-speed flight, we'll take a look at the sonic bang. When an aircraft is flying faster than approximately Mach 1.2, it is classified as a supersonic aircraft. The bow wave and trailing edge shock waves on a supersonic aircraft cause a sudden and massive rise in air pressure. If these shock waves reach your ears, you will hear a very loud bang. In fact, a double bang. Breaking the sound barrier, as flying at supersonic speeds is called, used to be common at air shows back in the 1950s and 60s. But in the UK, the practice was stopped because of the damage caused to windows and people's nerves. As you can see, the shock waves, and hence the sonic bang, travel over the ground at the true ground speed of the aircraft. No jet transport aircraft on the civil register in 2011 can fly this fast. Nevertheless, a question about the speed at which the sonic bang travels over the ground exists in the written exam. During the design phase of an aircraft, the overriding consideration is to keep the structural weight to a minimum. But the designers must also make sure the structure is strong enough to withstand the loads to be expected in service without damage. The other thing the designer must bear in mind is the stiffness of the aircraft structure, which relates to adequate control. For the structure to be both light and strong, flexible but not too floppy, requires very clever design and an acceptance that the aircraft can only have the minimum acceptable strength. Buildings, bridges, cranes and other engineering structures have a large factor of safety built into their design. The factor of safety is the difference between the loads to be expected in service and the applied load at which the structure will fail. A typical factor of safety is between 10 and 20, but for an aircraft, the factor of safety is only 1.5. So, when flying an aircraft, you must be gentle and treat it with respect. Typically, the loads an aircraft will experience come from either the pilot maneuvering the aircraft or from gusts and turbulence. We will look at maneuvering first. If you were to suddenly pull back on the control column, the lift will increase. Viewing the aircraft from the rear, we can see that in straight and level flight, lift equals the weight. If you suddenly pull back on the control column as before, you can see that the resulting increase in lift will bend the wing upwards. If you pull back on the control column too violently, the wing will snap off. We are therefore very interested in the ratio between the lift and weight, which is called the load factor. The official symbol for load factor is lowercase n, but everybody uses G. Aircraft manufacturers, aviation authorities, airlines, even the examining body. Just keep in mind that the official symbol for load factor is N. Is suddenly pulling back on the control column an everyday occurrence? Probably not. The everyday manoeuvre, which will increase the load factor and thus bend the wing, is turning. As you learned when studying stalling and flight mechanics, increasing the bank angle requires that lift be increased to maintain altitude. If you increase the bank angle too much, you might exceed what is called the positive limit load factor and damage the aircraft. This will be examined in the next lesson. The maximum load factor that must be allowed for when manoeuvring is shown in a diagram of load factor against equivalent airspeed. This is called the VN diagram by the examining authority. The same diagram is commonly called the manoeuvre envelope. You will notice that this VN diagram is for a jet transport aircraft. From our study of stalling, we know that the stall speed increases with increasing load factor, plotted here as positive CL max. Level flight is not possible to the left of this line. We can also plot the negative CL max line. You can stall an aircraft in the negative sense if you violently push the control column forwards. Again, level flight is not possible to the left of this line. The positive limit load factor for a jet transport aircraft is 2.5 G. For a jet transport aircraft, flight at a load factor exceeding 2.5 is not allowed. The negative limit load factor of a jet transport aircraft is -1 G. This also must not be exceeded. There are also several design speeds which must be considered. Design speeds are used by the designers of the aircraft to ensure safety of the structure. They are not operating speeds, but the operating speeds that we will study later are based upon them. The first design speed we will consider is VD. the design dive speed, and the second is VC, the design cruise speed. Please note that both VD and VC are design speeds. VC is a speed used by the designers to make sure the aircraft is strong enough at a typical cruising speed. VD is the maximum speed that has to be considered when assessing the strength of the aircraft structure. It is based upon the principle of an upset occurring when the aircraft is flying at VC, resulting in a shallow dive, during which the speed increases until recovery is effected. From our study of high-speed flight, we know that it is possible for a jet transport aircraft to experience high-speed buffet in the cruise. To allow for this possibility, the maximum limit load factors are reduced at high speed by the inclusion of buffet corners. We have now drawn the complete manoeuvre envelope, but there are a few other items to consider, such as the 1g stall speed. Obviously, it's impossible to sustain level flight at any speed less than the 1g stall speed. But it must be appreciated that when studying any variables concerning the Venn diagram, the aircraft is assumed to start on the 1g line. Please note that the origin of the Venn diagram is 0g, in case the examiners ask you. There is another design speed, VA, the design manoeuvre speed, which we will examine in detail later. We will now take a look at limit load factors. We will now consider the various limit load factors. Aircraft are designated as being in one of three categories. A normal category aircraft has a positive limit load factor of 2.5g and a negative limit load factor of -1g. The majority of aircraft, including the jet transport, are designated as normal category. They are built to be strong enough for everyday flight, taking off, cruising, descending and landing. A utility category aircraft has a positive limit load factor of 4.4g and a negative limit load factor of -1.76g. A semi-aerobatic aircraft or certain cargo aircraft designed exclusively for heavy lift will be in the utility category. They are built slightly stronger than a normal category aircraft to withstand the higher flight loads that may be experienced. An aerobatic category aircraft has a positive limit load factor of 6g and a negative limit load factor of -3g. The strongest of all civilian aircraft are those designed for full aerobatics. It would not be economical to use an aerobatic aircraft for purely transportation purposes, because their required strength would make them too heavy. Let's take a closer look at the factor of safety mentioned earlier, and some of the operational requirements when flying. For this study, we will use a jet transport aircraft, most of which are in the normal category. As previously mentioned, the factor of safety of any aircraft is only 1.5. If you multiply the positive limit load factor of 2.5 by 1.5, the answer will be 3.75. This is called the ultimate load factor. You must never deliberately exceed the limit load factor. Even though a factor of safety is incorporated into the design strength of the aircraft, if the limit load factor is exceeded, permanent deformation of the structure could occur. This includes a permanent bend in any part of the structure, or lost panels and damaged fasteners. If the ultimate load factor is exceeded, pieces will break off the aeroplane. Big pieces. We will now take a look at the design manoeuvre speed, VA. In 1G flight at VA, if the load factor is increased, the aircraft will stall before the positive limit load factor can be exceeded. The definition of the design manoeuvre speed, VA, is the highest speed at which sudden, full elevator deflection nose up can be made without exceeding the design limit load factor. You may see manoeuvre envelopes with VA at the intersection of positive CL max and the positive limit load factor. The small margin on this envelope for large aeroplanes is to safeguard parts of the aircraft structure in addition to the wing. Large aircraft don't use VA operationally, but you will see a speed for VA quoted in the pilot's operating handbook for small aircraft. You may be told that if you fly at VA in turbulence, it's impossible for the aircraft to be overstressed. This is not necessarily true. It is less likely to be overstressed, a more realistic statement. If we set the manoeuvre envelope to show an aircraft in 1G flight at a speed faster than VA, we can see that it is possible to accidentally exceed the positive limit load factor. So, when flying faster than VA, the pilot must be very careful not to increase the load factor too much. We'll now take a look at how VA can be calculated. For these calculations, the assumption is made that the design manoeuvre speed is at the intersection of positive CL max and the positive limit load factor. The formula to calculate VA is illustrated. The two variables are the 1G stall speed and the positive limit load factor. The positive limit load factor of a jet transport aircraft is 2.5 G and the 1G stall speed is 150 knots. Calculating the square root of 2.5 and multiplying it by 150 knots gives a VA of 237 knots. 237 knots is VA at the maximum all-up weight of the aircraft, but it will be necessary to calculate VA for lower weights. Here is the formula to calculate VA at different weights. Take the square root of the new weight divided by the old weight and multiply the answer by the old VA. It doesn't matter if you are asked to calculate VA at a higher or a lower weight. The formula remains the same. The maximum all-up weight of the aircraft is 60,000 kilos and will assume a weight reduction to 48,000 kilos. The VA at 60,000 kilos is 237 knots, so the VA at 48,000 kilos is 212 knots. However, as with the calculations we've used for stall speed variations with weight, we can use the same rule of thumb here. The weight change is 12,000 kilos and the change in VA is 25 knots. The percentage change in weight is 20% and the percentage change in VA is approximately 10%. The rule of thumb is that the percentage change in VA is approximately 50% of the percentage change in weight. For example, a 19% reduction in weight can be said to give a 10% reduction in VA. We have discovered that the aircraft is safe to operate within the boundaries of the VN diagram. The design speeds VC and VD are used only by the aircraft designers to assess the strength requirements of the aircraft in various flight conditions. Pilots use operating speeds, which are quoted in the aircraft's flight manual, and it's the operating speeds that we'll take a look at next. The maximum speed at which a large aircraft is permitted to fly is VMO, or MMO, or VNE for small aircraft. We'll consider VMO and MMO first. VMO is the maximum operating indicated airspeed, and MMO is the maximum operating Mach number. Exceeding either VMO or MMO can damage the aircraft structure due to high dynamic pressure or buffeting. Also, the maximum stability and control limitations of the aircraft could be exceeded. At speeds less than VMO or MMO, the aircraft's flight characteristics have been confirmed by flight testing to meet the appropriate regulations. At speeds in excess of VMO or MMO, however, normal aircraft handling characteristics are not guaranteed. The regulations state that VMO is a speed that may not be deliberately exceeded in any regime of flight, climb, cruise or descent. The regulations also state that VMO must not be greater than VC and must be sufficiently below VD to make it highly improbable that VD will be inadvertently exceeded in operations. In other words, VMO can be the same as VC or slower. From our studies of high-speed flight, we know that VMO is an indicated airspeed, and with increasing altitude, the Mach number corresponding to VMO will increase. There will be additional limitations on the aircraft because of compressibility effects. So at the changeover altitude, in the climb, VMO will be superseded by MMO. There are usually two independent Mach airspeed warning systems fitted to large aircraft that provide a distinct oral warning, known as a clacker, at any time the maximum operating speed of VMO or MMO is exceeded. The warning clacker cannot be silenced and will only stop when the speed is reduced below VMO or MMO. As mentioned previously, the maximum speed at which a small aircraft is permitted to fly is VNE. On the airspeed indicator of small aircraft, there will be a red radial line on the high-speed end of the yellow arc. This is the never exceed speed, VNE. VNE is set sufficiently below VD to allow for speed upsets to be recovered from without damaging the structure. However, because of the very high dynamic pressure, the controls must be handled very gently. At the upper limit of the green arc is the maximum structural cruise speed, VNO. VNO is the normal operating cruise speed limit and must not be greater than VC, or 0.89 VNE, whichever is slower. Flights at speeds exceeding VNO within the yellow arc should only be undertaken in smooth air and with caution. The top of the white arc is VFE, the maximum flap extended speed. As a reminder, the bottom of the green arc is the stall speed, with the gear and flaps up, and the bottom of the white arc is the stall speed with the gear and flaps down. The landing gear is normally retracted as soon as possible after takeoff to reduce drag and increase the climb gradient. There is no normal requirement for the gear to be operated at high indicated airspeed, so the retract and extend mechanism, together with the attachment points to the structure, are sized for the required task. To design the gear to operate at high indicated airspeed would needlessly increase the structural weight. There are usually two maximum landing gear speeds: VLO, the maximum operating speed, either retract or extend, and VLE, the maximum speed at which the aircraft can be flown with the gear extended, which means down and locked. However, the example we will use to illustrate the maximum landing gear speeds has two operating speeds: a maximum speed for extension and a lower maximum speed for retraction. The illustration shows the landing gear limit speed placard, and that the maximum operating speed for retraction is 235 knots. The main landing gear usually retracts inward, and you can see that when the gear is in transit, the main landing gear doors are open. The vulnerability of the doors is the reason that VLO is slower than VLE. Once the gear is up and locked, there is no speed restriction associated with the landing gear. In our example, the indicated airspeed must be reduced to 270 knots or slower before the gear can be selected down. Once again, the main landing gear doors are open during transit. Once the gear is down and locked, the indicated airspeed can be increased to our example VLE of 320 knots. So, what is the reason that some aircraft have a slower VLO retract than VLO extend? If we take a look at the nose landing gear, it will become obvious. The nose landing gear retracts forwards, and dynamic pressure will subtract from the hydraulic force in the actuator while the nose gear is retracting. To minimize the size of the nose gear actuator, and therefore the structural weight, a lower airspeed restriction is required. As before, the maximum indicated airspeed for gear extension is 270 knots. When the nose gear is extending, the dynamic pressure adds to the hydraulic force, so the speed restriction is determined by the vulnerability of the landing gear doors. As before, with the gear down and locked, the maximum speed limit is, in this example, 320 knots. It may be necessary for the aircraft to be ferried to a place of maintenance with the gear locked down, so a high VLE is convenient, and is possible because the vulnerable gear doors are closed. We know that flaps are designed to reduce the takeoff and landing distance, and are only used when the indicated airspeed is relatively low. To keep structural weight to an absolute minimum, the flaps themselves, their operating system and attachment points, are not built to withstand the loads that would be applied at higher airspeeds. In addition, with flaps deployed, the aerodynamic efficiency of the wing is increased, so a gust would subject the wing itself to greater stress. To give adequate protection to both the flaps and the wing structure, there is a maximum speed at which the aircraft can be flown with the flaps down, VFE. To safeguard the wing structure, the positive limit load factor with flaps down is reduced to 2G. You can see, when flying at a typical cruise altitude at VRA in turbulence, there is an equal margin of safety to the gust stall and the maximum strength of the structure. However, the odd gust can make the stick shaker activate momentarily, called burping. Do not be tempted to lower the flaps, even slightly, with the intention of reducing the stall speed to stop the stick shaker burping. If you do lower the flaps, even slightly, the stall margin will increase, but you will have reduced the margin to possible structural failure. The stick shaker burping is only annoying. Possible structural failure can be fatal. Operate the flaps only in accordance with the flight manual. We know that aircraft are designed to be as light as possible. But lightweight structures tend to be flexible, and aerodynamic forces are able to bend and twist them. The stiffness of the structure is a fixed value, but aerodynamic forces are proportional to v squared. At low airspeeds, the aerodynamic forces are small and have no significant effect on the structure. But at higher speeds, bending and twisting of the structure will be greater. Therefore, at some high airspeed, the aerodynamic forces will become greater than the resisting stiffness of the airframe, and structural failure may occur. Aircraft must be designed so that the speed at which structural failure can occur is higher than Vd, the design dive speed. We will now consider some of the effects of structural distortion and how the designers can make the aircraft light but also strong enough for practical purposes. If an aircraft experiences an upgust, or the pilot maneuvers the aircraft, the lift will increase and the wing will bend upwards. When the gust stops acting, or the maneuver ceases, the wing will return to its original position. But it's not just wing bending that must be considered. When distorted by an aerodynamic force, the wing will also twist. We'll examine wing twist in the next lesson. We used the aerodynamic center when studying stability. The aerodynamic center is located 25% aft, and it's the point through which we consider a change in lift to act. The wing will have an axis about which it will twist, called the torsional axis. Let's introduce a true airspeed vector and an upgust, which will result in an increase in angle of attack. The increase in angle of attack will give a change in lift, acting upwards at the aerodynamic center. But because the aerodynamic center is forward of the torsional axis, the wing will twist as well as bend upwards. The resulting increase in wing incidence will increase the angle of attack further and generate more twisting. Eventually, the stiffness of the structure will stop further distortion, and the elasticity of the structure will start to return the wing towards its original position. Unfortunately, the wing will twist in the opposite direction, and a downwards aerodynamic force will add to the elasticity of the structure, resulting in oscillation. If the oscillations were to increase, the process would be called divergence. But the design of the structure ensures divergence cannot occur at any speed less than Vd. As mentioned before, an airspeed will eventually be reached when the aerodynamic forces are greater than the resisting stiffness of the airframe. Divergence will then occur, and structural failure will follow. So, what can the designers do to increase the operational airspeed, prevent structural failure, and keep the structure light? Make the wing stiffer is the obvious answer, but that would increase the weight. A far more elegant solution is to move the torsional axis forwards, courtesy of Pratt & Whitney, General Electric, or Rolls-Royce. Engines have to be hung somewhere, and pod mounting them beneath the wing allows them to act as a mass balance weight for the wing. The weight of the engine, forward of the leading edge, positions the torsional axis closer to the aerodynamic center. So now, when an increase in lift occurs, the wing only bends. There is no change in incidence and no increase in the change in lift. Consequently, when the change in lift is no longer present, the wing will return to its original position without significant oscillation. The wing will oscillate slightly in turbulence, but the elasticity of the structure will not increase the motion, and the stiffness in the structure will damp out the oscillation. How control surface flutter is prevented was explained when you were studying flying controls, but we will review it here. As before, we will use the ailerons as an example. The wing is the most flexible of the structures to which controls are attached, but control surface flutter can also occur with the elevator or the rudder. If an aileron is moved down, an up force will be generated at the hinge. This will twist the wing about the torsional axis, and due to the inertia of the control surface, the aileron will be further displaced. In effect, the control surface will lag behind the motion of the aerofoil. The increased displacement of the control surface will twist the wing further. The wing is being wound up like a spring, and like any spring, its resistance to further deformation will increase, and the aileron will start to catch up with it. The result will be rapid oscillation of the control surface and wing, which will lead to catastrophic failure. Control surface flutter can be prevented by moving the centre of gravity of the control surface forwards onto the hinge line. Now when the aileron is displaced, the wing will twist, but the aileron does not lag behind, the wing twist does not increase, and no oscillation takes place. The centre of gravity is moved forward onto the hinge line by placing a mass balance weight forward of the hinge line. During your study of stalling, you were advised to use the rudder to keep the wings level when flying close to the stall, because use of the ailerons could make the aircraft roll in the opposite direction to your input. Before going on to study aileron reversal at high speed, let's review low-speed aileron reversal. The wing is shown at a high angle of attack, close to the stall. If this wing were to start dropping, and you used the roll control in an attempt to stop it, you would fully stall the wing, and instead of raising the wing would drop faster. The result of your aileron displacement was the reverse of that intended, hence the name, aileron reversal. And because this took place at low speed aileron reversal. Let's now consider aileron reversal when flying at high speed. When flying at an indicated airspeed of about 220 knots, a downgoing aileron will give the wing an upwards acting change in lift to roll the aircraft as intended. But, as previously described, the wing will twist in the opposite direction to that of the aileron. The aileron has increased the camber of the wing, but the wing twist has decreased the incidence of the wing, which will tend to decrease the change in lift from the aileron. At low indicated airspeeds, the wing twist will have a negligible effect on the change in lift from the aileron. But at higher indicated airspeeds, the wing twist will increase for the same aileron displacement. Eventually, a speed will be reached when the wing twist has a greater effect than that of the aileron, and the aircraft will roll in the opposite direction to that commanded by the pilot. This is high-speed aileron reversal. Obviously, an unacceptable characteristic, which would limit the maximum operating speed of the aircraft. In the next lesson, we'll see how the designers can raise the high-speed aileron reversal speed above VD, so it doesn't affect the aircraft operationally. Ailerons are attached to the trailing edge of the wing as far outboard as possible to give the longest arm to the aircraft's centre of gravity, hence maximum effectiveness. On aircraft with more than one set of ailerons, the outboard ailerons can be called low-speed ailerons. Unfortunately, the wingtip, because it is furthest from the point of attachment, is the most flexible part of the wing, and therefore most vulnerable to high-speed aileron reversal. On aircraft that would otherwise be speed limited by high-speed aileron reversal, another set of ailerons are fitted, inboard ailerons. Inboard ailerons are also known as high-speed ailerons or all-speed ailerons. The inboard ailerons are attached to a much stiffer part of the wing, so the wing doesn't twist so far at a given airspeed. This increases the speed for high-speed aileron reversal to a speed above Vd, a speed never likely to be exceeded in service. The illustration shows an aircraft flying at low speed. We know it's flying slowly because the flaps are down. Both the inboard ailerons and the outboard ailerons move when the pilot initiates a roll to the left, stops the roll, initiates a roll to the right, and stops the roll. With the flaps down for low-speed flight, both the inboard and outboard ailerons work. Let's raise the flaps so we can accelerate. Now, when the pilot initiates a roll to the left, only the inboard ailerons move. There is a mechanism that progressively locks out the outboard ailerons as the flaps retract. And when the flaps are fully up, the outboard ailerons no longer move when the pilot makes a roll input to stop the left roll, initiate a roll to the right, or to stop a right roll. To summarize, the inboard ailerons and the outboard ailerons work when the flaps are down for low-speed flight. It is the outboard ailerons that either work or don't work. The outboard ailerons work when the flaps are down at low speed, but don't work when the flaps are up for high-speed flight. The inboard ailerons always work, at low speed or high speed. Understanding the details of your aircraft systems often has a practical value. For example, there is a known exercise that British Airways have used during a Boeing 747 flight simulator detail. Your 747 suffers an engine failure shortly after takeoff. After you've raised the gear and flaps, another engine fails. The 747 is now climb restricted at that weight with a double engine failure, and you can't clear the surrounding terrain, so you must fly down a winding valley. You will have great difficulty rolling the aircraft to avoid collision with the valley walls, and the instructor will expect you to lower the flaps slightly to regain use of the outboard ailerons and give the aircraft adequate roll response. Another control system commonly used to reduce high-speed aileron reversal on jet transport aircraft is roll spoilers. Spoiler surfaces are located inboard of the wingtip and are mounted on the rear spar, so they do not change the camber and twist the wing. They assist the ailerons with roll control by moving up on the side with the upgoing aileron and back to flush. Once again, up on the side with the upgoing aileron and back to flush. With the flaps up, they move up on the side with the upgoing aileron and back to flush. Up on the side with the upgoing aileron and back to flush. We have now finished our study of aircraft limitations and the methods used to increase the speed at which unfavorable characteristics can occur to speeds higher than Vd. The illustration shows a propeller rotating in line with its plane of rotation. A propeller generates thrust by accelerating a mass of air rearwards. The equal and opposite reaction from the rearwards acceleration of air drives the aircraft forwards. During this study, we will view the propeller from above. To show the detail, we need a closer look. Some of the following definitions will be familiar to you from your study of piston engines. Our first definition is the chord line. A straight line passing through the center of the leading edge and the center of the trailing edge of the propeller blade. Here's the plane of rotation, an important reference for the study of propellers. You can imagine the angle of the blade to the plane of rotation, enabling the propeller to accelerate some air rearwards. This angle is called the blade angle, or pitch. Operationally, the term pitch is used more often than blade angle. Let's have a look at an individual propeller blade. The blade is attached at the root. The blade tip is at the other end. The leading edge of the blade is at the bottom, and the trailing edge is at the top. The blade has an aerofoil section, which, from root to tip, is at different angles to the plane of rotation. When a propeller blade is shown in a diagram, the view is of the aerofoil section at the reference station, 75% from the root. You can see that the blade is twisted. The blade angle at the root is larger than the blade angle at the tip. The reason for blade twist is that the tip is moving faster through the air than the root. If there were no twist, the tip would generate more thrust than the root and would stress the blade. Blade twist gives an even thrust generation from root to tip. Once again, a view of the propeller from above. We need some room to show the next item, geometric pitch. Geometric pitch is the theoretical distance a propeller would advance in one revolution at 0 blade angle of attack. As the definition says, it's a theoretical distance and impossible to achieve in practice. A propeller is a very efficient machine, so, under ideal conditions, it could advance at its effective pitch. The difference between geometric pitch and effective pitch is called propeller slip. The angle between the actual path of the propeller and the plane of rotation is called the helix angle. The next lesson will outline details of the fixed pitch propeller. We'll now examine a fixed pitch propeller, the type of propeller fitted to the majority of small single-engine light aircraft. As its name suggests, the blade angle cannot be changed. There are two types of fixed pitch propeller, the first of which is the cruise propeller. A cruise propeller has a large blade angle to give maximum efficiency at the cruising speed of the aircraft. A large blade angle is called coarse pitch. The other type of fixed pitch propeller is called a climb propeller. This type of propeller is not very common. To give maximum efficiency at low speed, a climb propeller has a smaller blade angle than a cruise propeller. As an example, an aircraft used exclusively for glider towing would be fitted with a climb propeller. A small blade angle is called fine pitch. So that we can see some of the factors that affect the efficiency of a fixed pitch propeller, we have replaced the plane of rotation with a vector of propeller RPM. A propeller fitted to the piston engine of most light aircraft will rotate at the same speed as the engine. We've now added a speed vector that represents the true airspeed of the aircraft. The product of the propeller RPM and the aircraft true airspeed is the relative airflow. As with any aerofoil, the angle between the chord line of the blade and the relative airflow is the angle of attack. In this case, the blade angle of attack. We will now vary the engine RPM to see how the blade angle of attack is affected. 2300 is a typical cruise RPM. As the engine RPM is increased, the angle of attack of the blade increases. For simplicity, we have maintained the same true airspeed, although in practice it will begin to increase. Decreasing the RPM decreases the blade angle of attack. Let's now consider the effect of aircraft true airspeed on the angle of attack of a fixed-pitch propeller. At low forward speed, the angle of attack is very big. The illustration shows a typical light aircraft just after brake release on the takeoff run. One of the disadvantages of a fixed-pitch propeller is its lack of efficiency at low forward speed due to the large blade angle of attack. You could think of it as the propeller trying to accelerate too much air rearwards for the power output of the engine. We'll now see what happens as speed is increased to the cruise speed. Watch. The angle of attack decreases as the true airspeed increases. Now the angle of attack is optimum for maximum efficiency in the cruise. You could think of it as the propeller being able to accelerate just the right amount of air rearwards for the engine power output. If we look again at the fixed-pitch climb propeller, you can see that it has maximum efficiency at low flight speed. We'll now take a look at the forces of thrust and torque and how they act on the aircraft. Here, we can see a propeller blade with its angle of attack and the plane of rotation. Thrust acts forwards, at right angles to the plane of rotation. And torque acts parallel to and in the opposite direction to propeller rotation. Torque is the equal and opposite reaction to the propeller being rotated by the engine. We will see later that torque will generate a yawing moment about the aircraft CG. Next, we'll take a look at propeller efficiency. The illustration shows a plot of the efficiency of a fixed-pitch propeller, with aircraft true airspeed increasing to the right. It's a standard cruise propeller, the type fitted to the majority of small single-engine light aircraft. You can see that peak efficiency occurs at the cruise speed of the aircraft. It makes most sense to use a fixed-pitch cruise propeller, as most aircraft spend most of their flight time in the cruise. Unfortunately, a fixed-pitch cruise propeller is not very efficient at takeoff speed or climb speed, so use of a fixed-pitch cruise propeller is a compromise. In comparison, a fixed-pitch climb propeller gives maximum efficiency at low speed, but unfortunately is totally unsuitable for flight at a sensible cruising speed. For optimum efficiency across the required speed range, a propeller whose blade angle can be varied in flight is required. Fine pitch for takeoff and climb, and coarse pitch for cruising. This type of propeller is called a variable pitch propeller. The plot shows a variable pitch propeller at low speed with the blades on the fine pitch stop. This will give maximum efficiency during the initial takeoff run. And as speed increases, the efficiency increases. The increase in efficiency with increasing speed is due to the blade angle progressively increasing to maintain the optimum angle of attack. Therefore, a variable pitch propeller will give optimum efficiency and performance throughout the aircraft's operating speed range. The mechanism that changes the blade angle in flight was fully explained during your study of piston engines and will not be repeated here. The variable pitch propeller will be discussed in detail in the next lesson. An aircraft with a fixed pitch propeller has only two engine control levers, throttle and mixture, and you set the engine power output using the engine RPM. If your aircraft is fitted with a variable pitch propeller, an additional control lever and instrument is required. Please note that a variable pitch propeller can also be called a constant speed propeller. A throttle is still required to adjust the amount of fuel going to the engine. But instead of RPM, the engine power output is monitored with a manifold absolute pressure gauge. The gauge is calibrated in inches of mercury, so it's common practice to refer to engine power output simply as inches, but it is written as inches MAP. The additional control lever is labelled RPM, but everybody calls it the prop lever, even the examining authority. The forward position of the prop lever is used to increase RPM. The aft position of the prop lever is used to decrease RPM. But it's not quite as simple as that. As you learned when studying piston engines, the prop lever is only connected to the spring in the constant speed unit. It's better to think of the prop lever as a request lever. The constant speed unit will always try to give you the RPM you want, but under some situations it won't be able to, as we will see shortly. When an aircraft with a variable pitch propeller is on the ground, the prop lever is always positioned fully forward. The throttle is used to adjust thrust for taxiing, as normal. The illustration shows an aircraft lined up on the runway ready to take off. The brakes are set and the engine is idling. Under these conditions, the propeller will be in the fully fine position, with the blades on their fine pitch stops. Gently open the throttle. You can see both the RPM and the manifold pressure increasing to the takeoff values. Because the blades are at the optimum angle of attack, the propeller will give maximum efficiency. Now release the brakes. As soon as the aircraft begins to move forwards, the constant speed unit will start to increase the pitch. Otherwise, the RPM would increase. This is why the variable pitch propeller is also called a constant speed propeller. The mechanism maintains a constant RPM when the true airspeed changes. There is a maximum time limit of 5 minutes for full takeoff thrust. So as soon as any obstacles are cleared and the aircraft is established in the climb, the engine power can be reduced to maximum continuous. In this example, the manifold pressure is reduced to 35 inches. The climb is then continued to the chosen cruise altitude. You can see the blade angle being increased to maintain the optimum angle of attack. You now have to level off and reduce power output to the cruise settings. In this example, we'll use 23 inches and 2300 RPM for the cruise. The recommended practice when reducing the engine power is to reduce the manifold pressure first. Gently retard the throttle to give 23 inches of manifold pressure. Now gently pull the prop lever back to reduce the RPM to 2300. The advantage of a variable pitch propeller is that under most normal operating conditions, the optimum blade angle of attack is maintained, thus ensuring the propeller operates with maximum efficiency. But what would happen if the throttle is closed or the engine fails? There is now no shaft power. Trying to maintain the requested 2300 RPM, the constant speed unit will fine off the blades. But it can only do so until they reach the fine pitch stop, after which the RPM will decrease. The propeller is now generating drag instead of thrust, and torque is acting to keep the propeller rotating. In fact, the forward motion of the aircraft is rotating the propeller. The propeller is said to be windmilling. The drag from a windmilling propeller is known as windmilling drag. The engine controls have moved to the left, so you can see the next consideration. A single-engine aircraft with a variable pitch propeller does not have a mechanism to feather the propeller to reduce windmilling drag. However, it is possible to reduce the windmilling drag on a single-engine aircraft by pulling back the prop lever. You have requested a lower RPM, so the constant speed unit will drive the propeller blades towards course. This reduces windmilling drag. On a multi-engine aircraft, windmilling drag on the failed engine must be reduced to keep VMC as slow as possible. So a mechanism is incorporated to drive the propeller past the course pitch stop into the feathered position. The blades are now at zero lift angle of attack. There is no torque because the airflow is no longer able to rotate the propeller, and drag from the stationary propeller is minimized, thus reducing asymmetric thrust. We have learned that a propeller generates thrust by accelerating a mass of air rearwards. Unfortunately, a rotating propeller will also create significant yawing, rolling and pitching moments. These moments give rise to 4 turning effects, which must be anticipated and compensated for by the pilot. The majority of piston engines fitted to single-engine light aircraft rotate clockwise when viewed from the rear. This is called a right-hand propeller. The first turning effect we will look at is torque reaction. Because the propeller is rotated clockwise by the engine, an equal and opposite reaction, called torque, will give the aircraft a left rolling moment. During the takeoff roll, the left rolling moment will apply a greater download to the left wheel. The increased rolling resistance from the left wheel will give the aircraft a left yawing moment. You must compensate for the left turning effect from propeller torque by applying right rudder in anticipation. At low airspeed and takeoff thrust, the left turning effect from torque is very noticeable. In flight, propeller torque will generate a left rolling moment, but this can be compensated for by using aileron trim. The second propeller turning effect we'll look at is spiral slipstream. Because the propeller rotates clockwise when viewed from the rear, the mass of air it accelerates will also rotate clockwise. The rotating mass of air meets the fin at an angle from the left, which produces a left yawing moment. In flight, the designers compensate for this by fitting a fixed trim tab to the rudder. But during the takeoff roll, at low airspeed and takeoff thrust, the left turning effect from spiral slipstream is very noticeable and must be compensated for by the pilot using right rudder. The third propeller turning effect is the gyroscopic effect. You have learned in other subject areas that one of the properties of a rotating mass is precession. If a force is applied to the circumference of a rotating mass, the reaction to that force will act at 90 degrees in the direction of rotation. A propeller is a rotating mass, so it too has the property of precession. Let's pitch the aircraft nose up. This will incline the propeller disc. A forward force has been applied to the bottom of the propeller disc. Precession causes the reaction to act at 90 degrees in the direction of rotation, forwards on the left edge of the propeller disc. This will generate an aircraft right yawing moment. The gyroscopic effect of pitching the aircraft nose up is a right yawing moment. If you pitch the aircraft nose down, a forward force has been applied to the top of the propeller disc. Precession again causes the reaction to act at 90 degrees in the direction of rotation, but this time it is forwards on the right edge of the propeller disc. A left aircraft yawing moment will be generated. The gyroscopic effect of pitching the aircraft nose down is a left yawing moment. Now yaw the aircraft to the left. A forward force has been applied on the right side of the propeller disc. As before, precession will cause the reaction to act at 90 degrees in the direction of rotation, but now it is acting forwards on the bottom of the propeller disc. A nose-up pitching moment will be generated. The gyroscopic effect of yawing the aircraft to the left is a nose-up pitching moment. Now yaw right. A forward force has been applied on the left side of the propeller disc. Precession causes the reaction to act at 90 degrees in the direction of rotation, but now it is acting forwards on the top of the propeller disc. A nose-down pitching moment will be generated. The gyroscopic effect of yawing the aircraft to the right is a nose-down pitching moment. Rolling the aircraft does not give a gyroscopic effect, because the propeller disc is not being inclined. At low indicated airspeed, the propeller shaft will be angled upwards from the direction of flight. Because of the upwards inclination of the propeller shaft, the downgoing blade will also be travelling slightly forwards. Consequently, the angle at which the relative airflow approaches the blade will be slightly modified. The downgoing blade has an increased angle of attack, and will therefore generate more thrust. The effect on the upgoing blade will be the opposite. The upgoing blade will be travelling slightly backwards. Consequently, the angle at which the relative airflow approaches the blade will also be slightly modified. The upgoing blade has a smaller angle of attack, and will therefore generate less thrust. If we view a single-engine aircraft from above, we can see the result of asymmetric blade effect. More thrust on the side of the downgoing blade, less thrust on the side of the upgoing blade. Therefore, the thrust line is displaced slightly to the right of the propeller shaft, which generates a left yawing moment. Of the four turning effects we've looked at, the gyroscopic effect has perhaps the smallest influence on a single-engine light aircraft, because of its transitory nature. The other three turning effects, torque, spiral slipstream, and asymmetric blade effect, all cause a left yawing moment. As mentioned previously, their influence on the aircraft will be greatest at low indicated airspeed and high angles of attack. We will now consider the significant influence that asymmetric blade effect can have on the safe operation of a light twin-engine aircraft following an engine failure. Both engines are rotating clockwise. As we saw previously, the downgoing blade generates more thrust than the upgoing blade. The thrust line from the right engine acts to the right of the propeller shaft. The propeller on the left engine also generates more thrust on the side with the downgoing blade, and its thrust line is also displaced to the right of the propeller shaft. If the left engine fails, the thrust from the right engine is acting through a longer arm to the CG and generates a large yawing moment to the left. But if the right engine fails, the thrust from the left engine is acting through a shorter arm to the CG and generates a smaller yawing moment to the right. So if the left engine fails, the pilot must use the rudder to compensate for a larger yawing moment than if the right engine fails. In this case, the left engine is called the critical engine. The critical engine is the engine the failure of which will generate the largest yawing moment. The majority of light twin-engine aircraft do not have a critical engine, because they are fitted with engines which rotate in opposite directions. The left engine rotates clockwise, and the right engine rotates anti-clockwise. The length of both thrust arms is therefore the same, so the yawing moments are the same. As mentioned previously, propellers that rotate in opposite directions on separate shafts are called counter-rotating. This brings us to the end of our study of propellers.